happen to sit here, you can, turn on one of the fields, whether it's magnetic field, electric field, stress field, temperature field. With a little bit of a nudge, you get a huge susceptibility, and you can begin to think about the coupling between different order parameters. And in this instance, that would be a multiphoric material. But just in general, looking for interesting phase boundaries is a good strategy if you're working with smart materials. So that would be sort of the a theme of the rest of my talk: how to find interesting phase boundaries. So in many smart materials, phase boundaries are where the best materials reside, whether it's a shape memory alloys, morphotropic phase boundary, piezoelectric materials, magnetostrictive materials, etc. So it's a pretty simple idea. We're looking for structural phase boundaries. Okay, so let me show you quickly how we do the experiment. So like I said, if you're familiar with the thin film technique, so you know how to go sputtering, the idea here is that we deliberately tilt the gun heads in such a way so that we maximize the compositional variation. And then we do deposition on the 3-inch wafers, we grid it, and then we map each compositional point using electron probe. And then we can now go at it and measure different physical properties as a function of composition, etc. And of course, these days, you hear a lot about how computational approaches have advanced over the years. And some of these techniques are also done in a combinatorial high throughput way as well. So we try to work, as closely as possible within many of these groups. And so, for example, they may have a prediction. This would be a good point compound. And so then we would do our experiments on the validation mode to try to look for that compound. Or we could do the other way around. We take our data, map structural distribution of different structures as a function of composition, and then feed that information to our computational colleagues. Okay, so this is an old example, but we still do this kind of an experiment. So we look for new magnetic materials, and the tool that we use is scanning squid, which is a superconducting device. But the way this scanning probe is set up, you can actually get information of the materials at the room temperature. So this is what the raw data might look like. And so you can make out the silhouette of that gridded wafer that I showed you. This is the 3-inch wafer. This is the raw image. And then, so from this, you can see immediately which region is magnetic, which region is not. And then we can take this field information, convert it to quantitative magnetization information. So in this case, we were looking for ferromagnetic shape memory alloys. So taking nominally similar wafers, but deposit it now on the cantilever arrays, we could do mapping of a martensite, which regions are shape memory alloys. So that would be 2 different measurements done on 2 composition spreads, where the platform is slightly different in this case because we had prefabricated these arrays of micro machine cantilevers. And then together we can combine the information, and we end up with what we call functional phase diagram. And so you can see which region is most strongly magnetic and which region is the display martensite. And then sometimes, so we could get that information, and like I said, 2 wafers. That could take sometimes a week or 2. But then we can compare with a published phase diagram if it's available. And then in this case, we were able to say that, this is a high temperature phase diagram, but it's the beta phase that at low temperature becomes a martensite. So that's sort of experiments that we do and the mapping that we do. Okay, so let me switch gears and talk about finding new superconductors. So like I said, we've always been interested in working with superconducting devices. And in fact, because we're doing material discovery, finding a new superconductor is always, we think of that as a major reward if we can do it, And then, like I said, when we do this kind of thing, we like to be guided by theoretical predictions, computational work. And it turns out it's very difficult to predict new superconductors. And so here are a couple of examples of early papers that we were reading. And then, so this one we paid attention to, relatively simple. So the authors here, Alexei Kolmogorov et al., they predicted if you make iron tetraboride, it could be and should be a superconductor, is the prediction. This is the prediction paper. So we did, okay, why not? That's a simple binary composition spread. And we made few wafers, and then we measured different spots on the wafer. And lo and behold, we were able to find one chip where, well, okay, so first of all, it's
Professor,
going from, yes.
Sorry to interrupt you.
Oh,
Actually,
you
your audio is like keep going low and high.
Oh, okay, okay.
Various...
Okay, how about now? Is that better?
Yes,
no?
Yes.
It is better? Okay.
Yeah, it's better now.
Okay, all right, thank you, Kamala. Okay, so what I'm plotting here is, so we can measure a resistive transition of 16 spots at the same time. So this is temperature versus resistance. So you can see on the given chip, we measure 16 spots at the same time. Most regions are just metallic, resistance goes down. Some of it is semiconducting and insulating, and to insulating to even measure room temperature. But we did detect in a couple of spots on the wafer, small regions where there is a definitely detectable clear resistive drop. So then we would carefully extract this part out. And then, so this is only a partial resistance drop, right? Because it stops, it only drops this much. Zero is down here. But just based on this though, we can tell that it's a superconductor because we can apply magnetic field to suppress this transition. And then just from this information, we can even get upper critical field information and then conclude that it's a type 2 BCS superconductor. So the point is we have this experimental technique. If there are good predictions, we can do this, okay? But like I said, there are not too many good computational predictions. So when that's the situation, what researchers have done in the past is to go work with an experimental database, if they exist. So that's another challenge, in fact, in many fields, well-curated, mineable databases don't exist, at least in many functional materials areas. So you end up having to make your own database, for example. And but that's the thing to do. When there is no theoretical guide, you want to turn to experimental database to look for trends. So this is an early work back in the 80s, the heydays of cuprate superconductors. It's the famous work by Villars and Phillips. They looked at all known superconductors at the time, and back then there were only about 600 of them. And it turns out what they call three golden coordinates, three chemical descriptors. So they're ionization energy differences, ionic radii differences, and the valences. And so if you just use those three descriptors, they said they're able to completely cluster all known superconductors at the time. And then based on that information, they were also able to make some predictions of new superconductors as well. Okay, but that's back in the 80s. The field of superconductivity has changed, drastically in 30 years. So luckily, there's a database called SuperCon within MatNavi, which is being curated at NIMS and Tsukuba in Japan. And until recently, actually, you were able to download this. And so if you go to this database, there's something like 29,000 entries. And so it doesn't mean that 29,000 different superconductors. There have been 29,000 instances of reports, experimental reports. So many of them are duplicates. So we went through this, we got rid of the duplicates, and there's still about 14,000 entries, completely different from 35 years ago. There were only 600 superconductors. So with that, now we're able to do machine learning, do supervised machine learning to build a model. So we would use a chemical descriptors originally developed by Wolverton et al., these magpie descriptors. And we used random forest is a technique, which is a common technique, supervised technique to make a model. And one thing that became kind of tricky was that if you want to build a model for superconductivity to predict superconducting transition temperature, for example, you want to include in your database non-superconductors, right? So that intuitively makes sense. Is my audio okay? It's okay.
It's okay.
Okay.
You can hear.
So, okay. So it turns out if you do random forest, because of the structure of this decision tree that you do, you could actually handle non-superconductors. The tricky thing about non-superconductors, which you want to include in such an exercise, is that their TC is decidedly not zero, right? It just doesn't have a TC. So how do you handle that in this model? Well, you could do that using decision tree, because at every point you can ask, is the TC of the material higher than 20 Kelvin or below 20 Kelvin? Okay, below 20 Kelvin, is it higher than 10 Kelvin or below 10 Kelvin? And in that way, you can still keep binning, you can keep handling the non-superconductors in the model. So that's the strength of the random forest. And of course, there are disadvantages to random forest as well. It's notorious for the difficulty in interpreting the model, but nonetheless, you can build a model of the transition temperature. So what's shown on the left here is, it's a supervised technique. So we would take a large fraction of the data to train and build a model, and then we test it on the rest. So this is the rest of the data, right? On the rest of the data, we apply a model, and then we come up with a prediction of the TC in natural log versus the actual TC. And you can see the fit is not too bad. R squared is 0.88, which is, I've seen better, but I've seen much worse, right? So this tells you that you're able to build models that, more or less track how the TC changes as a function of composition. And then if you look at the details of this, so even though we don't understand the mechanisms of, say, cuprate superconductivity or even iron-based superconductivity, you know who they are. So you can separate them into groups, and you can do an exercise like train the model using a BCS superconductor and then apply that to cuprates. And you see that that doesn't apply because the mechanisms are different. You could do that with any pair. Train a model with cuprates and apply it to iron-based superconductors. Again, it doesn't work. So this says that these models are able to somehow capture the essence of something about the mechanism of the superconductivity, so that you can build a prediction of the transition temperature. So based on this, actually, we were able to come up with the predictions of potential new superconductors. And the idea here is that we went to ICSD, which is the largest database of all known compounds. It's got the structural information. And so the idea is that there are perhaps compounds that have been known, but has not been studied or tested for superconductivity. So in this publication, we came up with a list of compounds, and now we are exploring them experimentally using the combinatorial approach, as well as one by one solid state chemistry kind of approach. Okay, so let me now talk about doing experiments again. So like I said, an important screening task is mapping of the structural distribution across the wafers. So we do this as much as we can at a synchrotron beamline. So we work closely with Apurva Mehta at SLAC, and over the last, actually, it took us 10 years to develop this, but now we finally have a setup. So this is a drop-in station. You can just drop this into the beamline, and you can turn it into a high throughput diffraction measurement system. And then so you can see we have some standardized sample holders. And finally, we can measure about 300 spots in about 2 hours. And it's all automated. And like I said, it took us about 10 years, but it works really nice. So if any of you are interested in doing high throughput experiments, we do this so that we get about 2 weeks of beam time every 3 to 4 months. And we do have, people from around the world joining us. Like I said, we try to standardize the wafers so that we can all do similar measurements. And so this is where this community approach really helps, because without people working together, we wouldn't be able to do this kind of work. Okay, so one of the ways in which we started doing machine learning about 12, 13 years ago was when we realized that now we're collecting too much data. And so, you look at any collection of diffraction patterns like here plotted together. And the challenge here is that now we have too many diffraction patterns. Because we are trained as material scientists, what we're trained to do actually is just pick one of these patterns and study every peak to death. That's what we were trained to do, right? But we can't really do that anymore because we have hundreds of diffraction patterns, literally. And then incidentally, the problem is the same if you're doing any kind of measurements, spectral data measurements. And of course, the situation gets much worse, exponentially worse if you're doing higher dimensional data, such as if you're taking images, obviously. And so we started doing simple, what turned out to be unsupervised machine learning, just clustering. And of course, back 12, 13 years ago, we didn't know we were doing machine learning. It's pretty simple. The idea is we take every pair of diffraction patterns, X and Y, and then we calculate something that looks like an inner product. It's called the Pearson coefficient, and we normalize it. And then, so it's an inner product, so you can use that to characterize how similar the pair is to each other. And then you can further normalize it. And so this is actually easy to understand. If you take two diffraction patterns, and if they're identical to each other, the inner product would be maximum, and you subtract that from 1, and then you can say the distance between them is 0 because it's sitting right on top of each other. On the opposite end, when they're completely dissimilar, you can say the normalized distance is maximum 1, right? In this way, you can calculate the distance between every pair of diffraction patterns. And then you can collapse that information together in what we call multidimensional data scale. So what's plotted here is every single spot is a diffraction. Every point is a diffraction pattern. So you can see from the natural clustering which patterns are similar. And we can also cast them into what we call dendrogram. So here, each entry is a diffraction pattern. And you can see how they get grouped together. So what we're able to show here is that, so this is, as you can see, is a purely statistical process. There's nothing to do with material science, except that the data is from material science. We were able to construct something that begins to resemble a structural phase diagram. And then really the rest is up to you to take this and make sure that the phase, if this is the correct phase diagram or not, anyway. So this is pretty useful. So we do this extensively. And in fact, this is a common technique that's practiced by many combinatorial material science groups around the world. And then about 5-6 years ago, so Gilad Kuzni is my former postdoc, and now he has his own group at NIST. He said, so you could do this analysis, but you take your data at synchrotron beamline, and then you come home, and then you do your analysis post-mortem, right? Post-mortem. And then you realize, oh, shoot, some of the library wafers were not very good. Oh, there was a region that was really interesting. We wish we took more data, So he said, why don't we do the data analysis dynamically on the fly as you're taking the data? So we do this now clustering after each measurement. So what Gilad does is he remotely accesses the data repository. And after each measurement is done, we run this cluster analysis. And then it keeps getting updated. So what this lets you do is after 300 measurement points are measured, you have a rough idea as to what the phase diagram looks like, structural phase diagram. And then once you have that, it's up to you again. You can say, because we're still at the beamline, you can say, oh, we want to measure this again, focusing on this particular region. Or we can say, oh, these samples are not good. Let's skip to the next set of wafers, et cetera. So this is pretty useful. And then, so this is sort of what led to our recent foray into this autonomous experimentation. So this uses this branch of machine learning called active learning. And the idea is, as the name suggests, you are actively controlling the way in which you're doing the learning. So here, what we do is initially we do the same synthesis, but instead of measuring every single point, we do initial sprinkling of the measurements, and then we do the clustering, and then we apply active learning, and so that we update and increase the knowledge with respect to whatever the thing that we're trying to optimize. In this case, the information that we're trying to get is distribution of the phases. So this is a semi-supervised machine learning, in that whatever we measure up until now is your training data, and then you project that to the future. You build a model and project to the future. And then you again, select each experiment, the algorithm selects it so that you maximize the knowledge. Okay. So if you look around though, so the idea of autonomous experimentation is beginning to be kind of prevalent. A few groups have been able to demonstrate it. And many of them actually do this in the chemistry space. So you can kind of see though, if you were able to do a tabletop system, it's self-contained, and you can think about how this autonomous experimentation is done. Again, so in the usual way, if you want to do this, you want to do the synthesis, measurement, analysis in a single cycle, and then you go around and around. And again, the key though is that you let the algorithm decide what to measure next. Okay. And what this lets you do, the advantage of this, why you want to do this. Well, many of you may realize what's good about autonomous experimentation. It's kind of like autonomous vehicle, obviously. You let the robot drive your experiment. And when you do this, it turns out you can significantly reduce the number of experiments you have to do. You get to the correct answer much, much quicker, okay? And but as I'm saying, this is easier, I would say, if you're doing wet chemistry. And but in the case of inorganic material, structural material, this is more difficult to combine synthesis with characterization in the closed loop. So as an initial attempt, we are applying active learning just to the characterization part of it. So because we do synchrotron diffraction, that could go pretty fast. But if you had to do this in-house, and we still do a lot of in-house diffraction, that could still take a lot of time. And there are also many other characterization where admittedly, we like it to be high throughput, but it's not, it just takes time. In that case, it's much better if you only had to measure a fraction of your wafer instead of measuring the entire thing. And again, the goal is to minimize the number of characterization runs, and then you get to the correct answer quickly. So here's how, in theory, how this, this is how it works. So we do Gaussian processes to do Bayesian optimization. And so say the black dotted curve is the function that you're after, and that's unknown, and that's what you're trying to uncover. So this could be materials composition, and that affects superconducting transition temperature. And you're trying to get to this point, right? So X marks all the measured spots, okay? So after each measurement, you can do the Gaussian process fit, and that's the blue curve here, okay? And so what the Gaussian process gives you is that it estimates the uncertainty in each range. So this blue shaded area is the uncertainty, okay? And then after each measurement, it updates the fit and the calculation of the uncertainty. So you can see immediately around here, there's zero uncertainty because you measured 2 points here as well. But around here, you have no data points, so the uncertainty is maximum. So the way active learning works is, after you do the Gaussian process fit, you just say, what do I want to do next? Do I want to maximize the knowledge? In which case, you go where the uncertainty is maximum, or you just want to go straight to the answer. I want to find where the estimate says is the maximum value of the superconducting transition temperature. Okay, so this is how active learning works. And then you can do this against a variety of functionalities. Again, what we're interested is mapping of the structural phase diagram. So this is actually a simulation, but using a real experimental data. And so what's shown here is that, so on the left, as the data spots are being filled up, so these are the points that are being measured. And on the right, what's shown is that after each measurement, we do clustering, and that's why the color keeps changing, because where the regions are clustered together is one region. And so what's interesting here is that, so there are about 200 points here. So by the time you get to 100 points, hopefully the classification error is zero and you can stop your experiment. But even long before that, let's say we stop here, let's say 1/10 of the way into the measurement, and you look at the results of clustering, and it turns out it's not too far off from the final answer, And again, it's up to you to decide as a material scientist if this statistical exercise makes or not ultimately anyway. So what this says is that you don't really need to measure all 100% of the points. 1/10 of the way into the measurements, you have more or less the correct phase diagram. And but what's more interesting here is that, okay, if you look on the right, so the big squares that pop up, right, you see them? So those are the regions that are being measured. So those are the spots that the algorithm said, go measure there next. And it turns out, if you look at where they're landing, they're all landing at the phase boundaries. And that makes sense, right? So because the goal here is to maximize the knowledge with respect to which phase each composition belongs to or not. So what this does is that, at this juncture, only say 1/10 of the way into the measurement, it tells you where the phase boundaries are. And as I said in the beginning, that's the answers you're looking for. If you're looking for piezoelectric materials, shape memory alloys, heterogeneous magnetostrictive materials, etc. So we have an algorithm that tells you the answer only a fraction of the way into the measurements as to what you're looking for, what the functional material, where they might be. Okay, so recently we were able to take this a step further. So now we combine mapping of the structural phase diagram together with the optimization of the physical property. In this example, we were trying to optimize the band gap.
Sir, you have 2 more minutes.
Okay, yeah, I'm almost done. Phase change memory material. So we do this closed loop. It's the Bayesian optimization. We have a prior data that we fit into it. And in this manner, we minimize the chance of getting stuck at a local optimum, right? You want to find the global optimum and not the local optimum. So this lets you do that because it gives you the information about phase distribution as well as the physical property. And so we did this actually. We ran the live experiment while we were running a synchrotron diffraction in Slack. We were also extracting data about the band gap difference between amorphous and the crystalline phase of phase change memory material. And lo and behold, we were able to actually find a new material that, as far as we could tell, appears to be better than the common GST225 for the properties that we're looking for. And it happens to sit right at the phase boundaries as we expected. Okay. So anyway, so this shows we've done this experiment many times to validate the discovered material GST467 is better than 225 for photonic switching applications. And now we're actually making electrical devices as well. So what we were able to show is that we could let the autonomous experimentation drive the sequence of experiments. And that actually led us to, what appears to be a completely new composition, which is useful for electronics now. Okay, so maybe I'll skip this. And I just wanted to tell you that not only do we exercise and practice machine learning, we also teach it. And we run a summer camp, a week-long summer camp at Maryland. And but this past year, we actually had to go online. And that worked out pretty good. We had the largest crowd, 180 people. I can't remember if you had anybody from India. Of course, from India, it'll be difficult. But if you're interested, please let me know if you can go to this website. We record all the lectures, so you can attend it at night. Okay. And I'll stop here. Thank you for your attention.
Thank you, Professor Takeuchi. It's very nice work. And this paper is open for discussion and comment from audience. Do you have any question?
Yeah, Professor, okay, there is a question in the chat box.
Yes.
From Dr. Chandramohan. He has written, if I understood correctly, the wafer is having variable element composition along XY direction. My question is how to precisely grow experimentally such a combinatorial thin film system on a wafer scale?
Okay, very good question. So there are different ways to do this, but because sputtering, we actually just let the sputtering happen, and then we measure the composition afterwards. And so, if you went to like a few millimeters, so within that sample, there would be composition variation. but then you can cut them up too. And so in that way, and then we can measure composition of every single spot pretty precisely in using different techniques. That way we can map the composition region of interest. So that's one way of doing that.
So there is a similar question: how to tune the composition of magnetic material?
So yeah, so like I said, we would then take magnetic elements, and then we decide which region of binary or ternary spreads that we want to map, and then we do composition spreads. And then in fact, if we do pulse laser deposition, there are different ways in which you can control this much better. And but the important thing is you measure the composition afterwards to make sure that what you think you have on the wafer is indeed what you have. That's
Okay, Professor Takeuchi, I
yes.
think 2 questions from chat board.
Yes. Okay. So we started with MATLAB. Actually, MATLAB is you know it's a good introduction, but now we switched to Python. In fact, we teach our camp using Python and Google Colab, which is really useful. So Python has all these packages, PyTorch, you know, everything you want to do with machine learning is there. You know, you just have to download the library. It's pretty useful. And then if you attend our camp, we'll show you how to do it. Maybe there's another one.
Yeah, there is an audience. Want to ask a question? Rudra, please go ahead.
Yeah. Sir, it's a very nice talk, and thanks for this talk. I have a question which is based on the one part of your talk, not machine learning, but the combinatorial high throughput.
Yes.
When we design a material and predict a material using combinatorial process, one problem face that, I mean, what's the stability? Obviously, using HTC, we cannot study the dynamical stability because it's hugely time consuming. And we have to stop by up to the chemical stability, the energy, and up to that.
Sure. Yeah, good question. So, yeah.
Yeah, so how we can deal with that without dynamical?
Okay. So if you want to study the dynamical process, okay, you're right, that would be hard. Although we do like diffusion study, we deposit combinatorial binary, and then we let it diffuse, and we do diffraction as we slowly change the temperature, etc. But you know, you need control. Control is really important. So you want to make sure ahead of time that the system that you're studying generally is stable, because if you don't have a control over your chemistry or material, then you simply cannot do this. So there are, you know, material systems and topics we avoid doing because it's just so difficult, you know. But many material systems we learn to we know which ones to work with, and that's important, you know, which topics you can tackle. If that answers your question.
Okay, if I ask one more question.
Please.
Okay.
Yeah, no, and the question is, so suppose I'm trying a simple ABX type of system.
Yes.
Combinatorially.
Yes.
Now, in that case, I mean, so you mean we have to shield we have to guess which system are will be tough to optimize, and we have to shield them before going to the optimization.
So you have a general idea as to which composition region that you want to map, and then you make a combinatorial library. Yeah, if you don't know, so it's always good to be guided by, I mean, to have some rough ideas as to what you're looking for. If I go to this region, I should find this or that interesting material. You cannot do things blindly. And that's true with any materials experiments, you know, whether you're doing combi or individual experiments, I would say. So the more you know about the materials, the more you will get out of this kind of study.
Okay, sir. Thank you.
Okay, I'm very sorry to have limit the interesting discussion on this paper, and with what we have to keep on schedule. Professor Takeuchi will be available to answer for the question after the session is over. Professor Takeuchi, thank you very much. Very nice talk. Thank you very much.
Thank you.
Thank you, Professor.
Thank you very much.
Nice talking to you after a long time.
Yeah, good to talk to you.
Okay, we will move on to next speaker. The second speaker is Professor Yuri Kivsha from Australian National University. He will talk metaphotonics and metasurfaces. Professor Kivsha is now most cited scientist in physics, and is the pioneering research on non-linear localized mode in optical systems, optical solitons, and vortices. Many of his achievements have been summarized in books and were highlighted in journals of physics today and Review of Modern Physics. Professor Kivsha, are you ready?
Yes.
Okay. Thank you. Welcome, Professor Kivsha. Welcome.
Good morning, India.
Yes.
We have a 5.5 hours difference. So it's really morning for you, but for us, it's already afternoon. So many thanks for inviting me. I know many respected scientists are talking about material science, computation, and very heavy stuff. But I'd like to talk about science and about physics. So quite elementary and basic, which we observed in the last few years, how this field is developing. It's a field of what we called metaphotonics and metasurfaces. If you go to optics meeting, the word metasurfaces are very, very often now, and I just try to explain what is that and why metaphotonics makes sense. First of all, currently I sit in Australia. You know, Australia had only 5 cases yesterday. It's completely locked. We don't have a COVID completely, but it's still very high hysteria, but we are just isolated. But you know, Australia is a very huge territory, much larger than India, with about 25 million people. So in particular, we have a large Indian population, not as large as we like to. So many of people, please consider moving to Australia. But we have in Australia about 30% of people born overseas, including myself, and including my very good friend, Professor Jagadish, so the most famous Indian scientist in Australia. So what else we have in Australia? Of course, we have population of different nations, particular huge population of Greeks who moved after Second World War. We have many beaches, which is expected. And we have a huge population of camels. So that's a very surprising news for me. It was some years ago, because camels escaped from explorers of desert, and we found the second second place to expand substantially, and now we're taken to Saudi Arabia for camel raising. Anyway, back to serious things. I'd like to mention that many groups working in optica exploring properties of plasmonic and metal dielectric material structures. This is a very expanded field with enormous number of applications which deserve tens of presentations. Just to remind some people who are not familiar with that, so we're looking at the subwave length localization of electromagnetic waves at the boundary between dielectric and metal, and hybrid excitation of electrons and electromagnetic waves create localized states, for example, here propagating along the surface, or localize particular interfaces, different type of plasmon modes linked to actually interaction of wave with the free electrons in the metallic conductors. So usually plasmonic is driven by so-called electric resonances, electric field resonances. And meta appeared when people try to add to plasmonics some magnetic response. Of course, if it's magnetic material, it's not a big surprise, but we are talking about magnetic response of non-magnetic material. How this can be made? So basically, it was one of the first suggestions. We made this splitter resonators made of metal, so electrons oscillate there. Electrons oscillating electrons create a magnetic moment, and basically this elementary unit allows you to create a local magnetic moment in structures which are not entirely composed, not at all composed of magnetic materials. So in this optically induced magnetic moment, which is induced by incoming electromagnetic wave. Then if you combine this magnetic response with usual electric dipole response, we may think of creating structures which will be composed of electric and magnetic resonators and basically change properties of materials. So that's how matter came. Matter came with magnetic response, and actually the entire field of metamaterials in the first years was concentrated on different ways to actually change magnetic and electric properties, so creating structures which do not exist in nature. So the first suggestion for such materials or kind of materials was made in 1968 by Russian scientist Veselago, Victor Veselago. Unfortunately, he passed away just recently. And he also came with the idea of this Veselago flat lens. And of course, this field was rapidly not developing, not rapidly, but just was absolutely stuck. Since 68, it was no single paper published until, as you see, 2000, when the first experiment was reported by David Smith and co-author from San Diego, who actually employed the splitter resonators combined with these rods, metallic rods with supporting this electric resonators. Splitter resonators supported magnetic resonator and created a structure which was interesting, which has a very interesting property. It allows to actually create a material with both epsilon and mu negative. I just remind you that epsilon and mu are constant which usually characterize material. We enter Maxwell equation, and usually if there are no materials which are there are some exceptions, but generally there are no materials which have negative index of refraction, both negative epsilon and mu. So that was a lot of interest attracted to that point. And just to mention what was the first concept of that in that field, that people tried to actually mimic nature, creating structures which are composed of this resonator, electric on magnetic, and basically create properties at will. So if you want particular values of epsilon and mu, most interesting, for example, epsilon and mu going to 0, which is very hard to find in nature, almost impossible. So we may just create electromagnetic structure from this structuring with a local, different local response to change macroscopic response of the structure. And it was a lot of activities at that time after these discoveries in different directions. Particular people, of course, discuss optical magnetism, as I mentioned, negative index of refraction, when wave bent in completely different wave as described in textbooks. There was a lot of hype with clocking possibility to actually hide objects. And why metamaterials is important there? Because you need to change both electric and magnetic properties to employ this transformation of Maxwell equation, and particular open space when you can hide objects. A lot of different applications, optical circuitry, supin lenses, Happer lenses, including of chirality. Initially, it was structures with Spix properties. Then people move into active, tunable, reconfigurable material. The only problem was that it basically was for microwave and terahertz. 5 years ago, as I mentioned, was started 2000. 5 years ago, 15 years after that first paper was published, David Smith organized a conference when he tried to actually summarize what was happening during that time. And at that conference, it was clear that a lot of commercial interest and the application interest to this type of structures and the man-made materials And around that time, it was several companies created with support of Bill Gates, where David Smith was involved, and few of them I list here. And we basically involve such areas like security, satellite communication, radars, but you see nothing from optics. And the reason is that if you go, just as example of one of the, probably not that very important example, because it's a screening of security in airport. So airport is not that much populated as used to be, but that was a prototype suggestion to remove completely this bottleneck for screening and screen and go, basically checking less than 1% of passengers in an airport. But probably they should completely revise their idea, checking for COVID on the passing instead of some dangerous elements. So basically what was happening, there was a lot of structures created. This is an artist's impression of different structures. And all the structures actually involved, as I mentioned, two types of elementary local resonances, electric and magnetic resonances. Magnetic first were introduced through the split resonator, and they gave a birth of the word meta. But even these structures already have these elements, because if you look at metal dielectric metal structures, so nano-Burger type of elements, we can have in-phase and out-of-phase modes, which will be defined exactly electric and magnetic responses of such structure. So it was very clear how to engineer that. It bring all electrodynamic, particular radar physics and microwave physics to much higher level. So like antenna arrays would be controlled much better, assuming that we understand how to tailor electric and magnetic resonances. But it was still not clear how to move to optics. And the reason is that if you look at all the structures, you see all these metallic elements, and similar to plasmonics, metals demonstrate heating, free electrons can be excited, so a lot of detrimental effect. And losses which usually exist in plasmonic structures, was not clear how to make very nice and very perfect structures without metals. So that was the main idea, main question some years ago. The answer came some years ago, relatively recently. It was actually termed by editors of Nature Photonics like metronic error. And it was associated with the possibility to excite me resonances. It may look like a joke, but me resonances have a history more than 100 years, but it just came again into play to actually revise completely this concept of metamaterials. I just remind you that me was a German scientist who solved exactly Maxwell equations more than 100 years ago, and it was, of course, it was not as easy because it was no Mathematica, which you can now use. So he introduced special functions and wrote these expressions. You see these big crocodiles, but that's all pictures taken from his paper. And then basically, as physicists, we're interested in this dimensionless parameter. So this is the ratio between geometric size and wavelength. So what is very interesting is that we can have many of the phenomena described by this me formulas, and me actually solutions are very popular. Many libraries exist to actually program me solutions for different parameters, but we are mainly interested in resonances. Some of the resonances shown here, but I will explain why this is important. If I take a particle, relatively small particles, like 50 nanometers, and try to look at the response, this scattering response, scattering cross sections, and basically what I will find that, of course, I see very clear plasmonic resonances, which appears at the interface between metal and dielectric, this for such a small size. But of course, nothing is seen from dielectrics of semiconductors. If I increase size of particles, of course, the picture is completely changed. First of all, metals don't have, metallic particles do not have very sharp resonances, because plasmonic resonance is associated with surface effect, and they're sharp only for small particles. But instead, for dielectrics, we see this very sharp peaks. It's not that sharp as we want to, but still it's much better than metals. So the reason for that at this particular peak, we hit Mi resonances. What kind of resonances is that? This is example calculated for silicon nanoparticles. And then what kind of resonance? Imagine that we have electric magnetic wave which interact with the dielectric particles, and of course wave penetrate inside. So when wavelength inside, which is lambda over n, where n is refractive index, will coincide with geometric size of the particles, we will see these resonances. And it's really interesting because what we may observe here, we may observe both magnetic and electric resonances. So electric resonance, like electric dipole resonance, is very well known. It's a dipole electric field. Magnetic is just complementary, but for magnetic field. So basically we're manifested like peaks in this scattering cross-section diagrams. So basically in a simple dielectric particles, but with relatively large n, remember n, and we need to squeeze the wave inside of this particle, we can have both type of resonances, and we can actually come to the idea of metamaterials. That was initial effort some years ago when people tried to employ average parameters and derive some homogeneous type of effective structures based on these resonances. But in fact, we discovered some years ago that resonances is what is the most important in the structures. Why this is important? And people who work on plasmonics, they know that usually when people study plasmonic particles, they are small and they are described very well by dipole approximation. Discrete dipole approximation can be applied for like oligomer structures of these magnetic particles. But in dielectrics, instead, we have particles much larger size. It's a few hundred nanometer. So and we can excite different multipoles, electric dipoles, magnetic dipoles, quadrupoles, magnetic quadrupoles, and they can be all excited in the same particle. The only condition is that if you want to have a good particle in optics, few hundred nanometers, you need to have a material with relatively high refractive index to actually excite that resonance. So if you have different multipoles, what we can see multipolar interferences. And that's really amazing things, because if I take electric dipole and magnetic dipole excited simultaneously, the structural field is such that if amplitudes of these multipoles will coincide, I will see the so-called Kercher effect. If magnetic and electric dipole of the same intensity superimpose, the interference pattern actually give us unidirectional scattering. It's a very amazing things, because if you look at the textbooks, to see interferences, you need one source, another source, and they should be placed on a distance of quarter of wavelength. It's a textbook. And now we can superimpose two dipoles in a single point and still see very strong interferences. So we can dramatically control emitted radiation from this nano object. One of the examples of this exotic particles transverse Kercher effect, when incoming wave excite dipole and quadrupoles and actually can scatter transversely with almost no wave reflected or transmitted. So many exotic stuff can be actually described, but the other interesting big things here is the possibility to excite material, because wave penetrate inside. We can actually see many interesting effects from these dielectric particles at resonances, particular magnetic dipole resonance as first resonance, and a particular enhancement for nonlinear effect. Nonlinear plasmonics was claimed like a very rapidly developing things, but in reality, effect of nonlinear plasmonics was very, very, very small. And the reason is that the efficiencies of harmonics or self-action effect in such structures are extremely, extremely low, because field sits at the surface. And the third big things which we very recently discovered is the possibility to have high Q resonances. That was a kind of unexpected things which many people believe not correspond to Mi resonances. And the reason is that everybody knew that Mi resonances are low Q resonances, Q of 10 or less, and that's why, of course, they can't compete with plasmonics where Q resonances can be much higher and being limited by losses only. So bound state in a continuum is something what is not usually known for optics people, but probably solid state people may know about that. It came from the paper by founders of quantum mechanics or pioneers of quantum mechanics, who published a very strange paper, very short paper in 1929, which just solved exactly Schrödinger equation, scalar Schrödinger equation, found a very strange exact solution for oscillating potential. I will not repeat their paper because it's quite unclear, but I will give you a cartoon which will explain physics of that, what they actually describe. If you go to textbook in quantum mechanics, of course, everybody knows that we can have a localized energy level which correspond to trapped particles and propagating wave functions which correspond moving particle, and an energy picture, this is a continuum or discrete levels. That's extremely well known. Now imagine that we can have a different potential. This potential will be waved at the edges. Now we see that there is another domain in between the maximum and minimum. When I will propagate wave here, it will experience reflection and transmission, so tunneling in the quantum mechanic language. And if I make all phases right, I can construct solution which will compensate all phases and will be fully localized. And that's exactly physical picture of the solution which was accidentally found by von Neumann and Wigner. And it's now recognized like a localized stage sitting in a continuum. So you can immediately say, come on, this is an absolutely mathematical curiosity. So we can break this symmetry and destroy all this nice condition. But I should tell you that in optics, this mode sitting above the light line, this corresponds to the novel physical mechanism or physical mechanism which allows you to actually squeeze light in the open resonators and get it localized. Of course, that solution was noticed, and the people started to play around that, particularly in mathematics. So we published a lot of mathematical papers, as you may see. Just let me make a pointer, better pointer. And we studied the solution, and then some years ago, this notion came to optics, but it was purely theoretical. And again, about 10 years ago, was the first experiment done for waveguide array by Morty Segev group, when we actually get light scattering from one defect, second defect, and superimposed to get them localized. You can also get reflection from GH, and the most interesting field when this notion we'll actually explore was in photonic crystals. Photonic crystals are slab of dielectric materials with some periodic structure like here, these holes. And in such structures, it was noticed that there are different types of so-called dark modes, which correspond to very, very high Q values. Of course, in reality, they are not infinite, but because in really localized solution correspond to infinite values of Q, but in reality it's smaller, but it's still, you see that there is some very strong localization. In fact, we realized now that there are many systems which support this type of modes, but even the very, very simple system of so-called optical gratings support this type of solution. So how this solution appears? If I look at the usual waveguide, so waveguides support right or left propagating waves, and now they're just leaky because of index index difference. And then what I do, I introduce periodicity here at the waveguide boundaries. I create gratings or doubly periodic waveguide. And these particular gratings, what will happen is due to Bragg scattering, we open a gap, and this H mod, which correspond to 0 gamma point, 0 K0, correspond to those two H mods, and one of them actually it's experience constructive interference from these two leaky mods become coupled here, and the other one destructive interference. So basically, one point at the gamma point here we correspond to a mod which becomes fully localized. So this is fully localized mode, which like a standing mode, not radiating. It non-radiating because of a special inversion symmetry, time reversal symmetry, and this is so-called symmetry protective bound state in the continuum, which are in short called BIGs. But there are several more, at least three or four different types of BIGs, which I don't have time to discuss here. I just mentioned that the other BIG was discovered in 1985, and it was discovered and described, of course, it was known and many problems, through interfering resonances. If you have two different resonances and they experience strong coupling, in a strong coupling, we observe usually repulsive interaction of dispersion curves, and usually people observe so-called dark modes. So these dark modes correspond to the condition that incoming radiation do not couple to this resonance state. And this is exactly bound state in a continuum. And that bound state in a continuum can very often be found in many problems. Just look at the problems which people call dark states. Why it's interesting? It's interesting because as soon as we realize this possibility, you can describe this type of states in a very simple dielectric resonator. Imagine I have a resonator which made of dielectric, epsilon large enough to excite me mods. And now I will play with the height of this resonator. If I play with the height of this resonator, first I hit quarter wavelength, and basically I enter this family of so-called Fabry-Perot modes. Now, combination of me-like modes and Fabry-Perot modes actually create a very complex structure. It looks like a very simple system, simple resonator, open resonator, but it's really quite complicated. So conditions for what I'm looking for two leaky modes to be excited in this resonator. So usually if radiation comes to interact, just because of large epsilon there is a kind of maximum and then leaking. But if I excite two leaky modes simultaneously, then I can compensate their tails and then energy largely localized in the resonator. Of course, I can't get Q infinity because I need to take epsilon going to infinity to get full reflection from the bodies. But in fact, that in a real, like silicon-made resonator, that can be observed. If I draw this like a size parameter, dimensionless parameter associated with wavelength for aspect ratio, you see aspect ratio, this is exactly interplay between radius and height. I see this point with repulsive interaction of dispersion curves. Each slope actually remembers the origin of the curve, me or Fabry-Perot, and I observe these points which correspond to bound state in a continuum with substantially suppressed leakage of the modes. That's what we've predicted in 17, and then later was several observations. So we did the observation recently in microwaves when trying to play with the height of this resonator. Then in that case, microwaves, we see huge Q factor associated with different types of this crossing point. And also last year, we observed it in near infrared for aluminum gallium arsenide resonator when we saw substantial enhancement of the Q factor and up to 200, and actually observe the record high generation of second harmonic from such resonator, which are up to 1% of conversion efficiency, which is 10 or more orders higher than any of the plasmonic system reported so far. Why we are interested in that? That's a very good question, because we are looking for sub-wavelength nanophotonic type of structures. Of course, if you're dealing with micro-ring, micro-optical objects, we know that like in that micro-ring, we can have a very high Qs. But if you look at the footprints of such structures, they're still relatively large. So normalized resonator mode volume much larger than 1. So plasmonics provides actually very, very small footprints, but Q factor is relatively low. So with me modes, we are pushing it a bit high, but still we substantially increase mode volume. So this beak, or we call quasi-beak, because we are not really bound state in a continuum, but a physical bound, quasi-bound state in a continuum, we can push it much, much higher. And recently combining several resonator, we were able to actually show much higher Q factor, up to 10 in the power of 4 or 5, and with mode volume very close to mode volume of this dimensionless 1. So this is a way to go, to combine interferences with the possibility to localize energy in resonators, of course, exciting me resonances and playing with their hybrid structures. I switch to the second part of my talk, which is about metasurfaces. Metasurfaces, it's a very, very hot topic. And of course, we are interested in specific classes of metasurfaces, but first of all, how people define metasurfaces. This is from very old slide of Federico Capassa, who presented it like a possibility to actually change wavefront by making sub-wavelength structures of a particular interface, and that particular structuring very similar to diffraction grating, but because it can be done in a different way with a different period, with different patterns, it basically associated with effective K vector, and this effective K vector changed Snell's law. So that was a great excitement some years ago, because making metasurfaces with sub-wavelength structures, we can change many properties of waves propagating through these metasurfaces and dealing actually with flat optics, relatively flat sub-wavelength type of structures. In my group with collaborator, we follow 2 steps. We just use different type of resonances to achieve unidirectional scattering, or we employ resonances, kind of bound state in a continuum, to achieve very sharp resonances. We'll mention few of this example. And for example, how to actually tailor resonances, because we need multi-mode resonances actually acting together. If we change in a me theory from sphere to nanodisk, of course, we don't have exact solution, but we can solve it numerically. And in nanodisk, we can move resonances and make them overlapping. That was first observation we made. To our big surprise, that the resonance is moving differently when we change size of the system. And the first metasurface periodic structure of these elements we created allows to superimpose magnetic and electric dipole and actually achieve unidirectional scattering. This unidirectional scattering associated with 2 pi phase, because it involves 2 resonances. Each resonance brings pi phase change, and it has extremely high transmission because of this effective Kerker effect. It's basically very similar to what was suggested by Huygens about Huygens source, which does not reflect back and propagate ahead. But of course, this is for special conditions, how to make them broadband, because it's only realized for specific frequency. Broadband, again, I don't have time to discuss, but again, we're playing with height, similar to what I described for bound state in a continuum. When we play with aspect ratio, we can basically introduce the second modes, and for multi-mode in coupling, you can actually bring them to very, very high performance level and be in broadband. For here, it covers at least 3 telecom bands. And in the few years back, we actually made this table which shows evolution of efficiencies of these metasurfaces, particular meta devices based on metasurfaces like specific functional meta devices, starting from the first demonstration in 2012 up to 17. You see, this is plasmonic, very high, very low transmission efficiency. Then people switch to dielectric, showing different devices: vortex beam deflector, Q-plate lenses, what they call meta lenses. And if you do it multi-pole approach, which we actually know how to do, we can achieve the highest transmission efficiencies of these meta surfaces, which are very close to transparency of glass plate where we plate our resonator. So what we can do with these highly transparent meta surfaces? Remember, they're highly transparent, almost 90% transparency, and they can imprint different phases. So it's a lot of possibilities people working in optics can imagine. So one of them is just to talk to fiber optics people and, for example, use this meta surface to imprint different modes in the multi-mode fibers. That's what was done by us a few years ago. You see that this is performance of these 4 different pieces of this meta surface composed of this elliptic shape rods, cover 3 telecom bands, and basically may improve different modes and transmit employing mode multiplex communication in that case. Of course, now people start talking to quantum people because of high transparency. You can use them for quantum, for separate photons, photon pairs generation. There are different streams, but particularly combining 2-dimensional materials, another type of quantum emitters. And that's summarized recently in our review paper with my second Indian friend, Girish Agrawal. I have first friend, Govind Agrawal, with whom I wrote book on solitons. Now, the second scenario which I mentioned is using resonances. This is also extremely interesting because these meta surfaces with a variety of resonators can be employed for creating a different type of highly resonant structures. Of course, I'm not talking about nonlinearities today, just only linear response. We noticed that it was a lot of efforts to actually describe high transparency, and basically they were associated with meta surfaces composed of meta atoms or these elements with broken symmetry. This is a different example of them. So broken symmetry actually remind us specific properties of coupling of incoming light to guided mode at the point which is usually called a dark mode, dark point. And we demonstrated that all these meta surfaces associated with another type of bound state in the continuum. And this bound state in the continuum can be characterized by radiative quality factor, which is in square inverse of a symmetry parameter. And then if you know physics, if we can engineer different points of that curve and make highly transparent or highly reflective surfaces and engineer their particular frequency characteristics. These structures are now...
Professor, sorry to interrupt you. You have 3 more minutes.
Yeah, that's good. These structures are being fabricated. There's a few examples, which particularly we use that one. And the Q factors which you can achieve enormous for this type of structures, it can be going to 18,000. And what we can use here, I will show this last idea, we can use it for many, many applications. And one of them is so-called pixelated meta surface for biosensing. We create a pixelated structure. Each of these elements consists of this tilted bar. Each tilted bar corresponds to bound state in the continuum resonance, 1 peak. Because we're pixelated, we're scaled, we have a comb of these resonances. And this comb of resonances from that meta surface can be used for sensing. So we put any substance there. So this vibrations of molecules in mid-air will produce this specific structure of absorption, which can be easily measured without any sophisticated devices, just in transmission. They create a barcode of almost every elements corresponding to the vibrations, this molecular vibration of the substances. That's a very simple idea, but I just mentioned that it's important to cover relatively big area, so very sharp resonances will not work. So resonance around Q factor 150 was very, very useful in that our work, which we did some years ago in collaboration with Hatice Altuk from EPFL Lausanne. Of course, we can do another type of surface enhanced spectroscopies. I don't have much time to discuss it. So angle resolve spectroscopies, or even hyperspectral biosensing, that's all related on resonances. But this bound state in a continuum bring a lot of interesting discoveries. As last example, two examples I will show, possibility to create singular beams, because around a point of bound state continuum, we have singularity associated with polarization, singularity which create usual normal vortices, and that can be used for switching. This is the simplest type of photonic crystal type of bound state in a continuum, but made of perovskite, because we are interested in seeing lasers. And the final example is that with this lasing, of course, we have a very high Q mods, which we can employ for lasing. And this relatively new idea by taking several bound states in a continuum, merging them, allows to drop substantially threshold for these nano-lasing structures. In the structures which are no more than 10 by 10, it's already sufficient to drop substantially threshold of lasing with a passive, very high Q factor of that dielectric structure. So I come to conclusion. Chair is very sharp. So what I wanted to tell you, that the field metamaterials, which you probably heard about, now experience some rebranding or reshaping. It transforming in meta optics or meta photonics. It still has meta to reflect that we are interested in magnetic response of such structures. Meta optics and meta photonics means that we're already in the quantum world, and the structures actually associated with the possibility to use high refractive indices. I did not discuss specifically, but materials like silicon, aluminum gallium arsenide, germanium, they're very, very useful for this type of games. And of course, we are in the process already to create, and it's many papers coming from many groups about creating specific designs of dielectric structures, like meta surfaces, meta devices based on them, hybrid structures which combine meta surfaces and two-dimensional materials. And very recently, this concept of bound state in a continuum allows actually to deal with very sharp resonances and employ the sharp resonances for many interesting applications. I gave you only a few examples, but you can imagine, I think you can imagine many more applications which I don't have time to talk about. Thank you for your attention.
Thank you, Professor Kipcha. Now let's open question and comment from audience. And do you have any question?
I see one question.
Yeah, there is a question in the chat box. What properties of 2D material?
Yeah, I'm reading. Okay. You should read loud, right? So, what properties of 2D material like molybdenum disulfide we can explore, consider it meta surfaces in mind? That's a very good question. It's now going, and the reason is that the meta surface is flat, and we can easily deposit two-dimensional material on that, so creating hybrids. So one property we can use these two-dimensional materials to actually create quantum emitters. We can deposit them in layers. We can take a thicker structure and explore exciton resonance. So it's a lot of possibilities which we can explore. Of course, nonlinear properties. What we recently did, usually nonlinear response of 2D materials are very weak, but we can enhance nonlinear response of 2D materials by placing them on a meta surface. So what we did, we put two-dimensional material on silicon meta surface and observe high second harmonic generation. Silicon does not produce second harmonic, at least of that strength, but because it localized field and coupled to 2D materials in enhanced second harmonic from 2D material layer, single layer, by 5 orders of magnitude. That's how we can use bound state in a continuum. There's a possibility to create hotspots in dielectrics, which are usually associated with plasmonics, and get energy localization in particular places with particular frequency domain. Second question, optical properties of mathematics just drastically for 2 3D. How thick your sample will? I'm especially interested. Okay, that's very interesting, but meta surfaces completely ignore three-dimensional structure in that sense that when people are talking about three-dimensional materials, we assume averaging, we assume description by average parameters. Here, we don't care about average parameters. So our resonators are sitting on one surface. So it's basically, in that sense, metamaterial properties are not much relevant. We are interested in the kind of array of nanoantennas, and we're interested in superposition of interaction of these nanoantennas between each other. So how thick is sample? It's also a good question, because I was mentioning about resonator. So we need few hundred nanometers. Why? Because we need actually several multipoles in that structure to get it highly transparent or make a very strong influence of radiation pattern. So if I take plasmonic structure, you can have a very thin metasurface, but it's not very useful. It may be used for beam deflection, but still efficiency will be very, very low because of losses. But of course, I'm talking about visible or infrared, mid-infrared. But for the electrics, you need a bit higher, this post. People do not mention that, but in reality, they're like a quarter of wavelength thickness, but still it's sub-wavelength. One more question. Regarding constructive interference to leaky mode, I would like to know how exactly phenomenon. Okay, I may send you email. I can't explain it in 1 minute. But the idea is that this concept of bound state in a continuum does not eliminate leaky modes. It's very special, ideal mathematical points when you can eliminate leaky modes completely and get Q going to infinity. That's not happening in the real world, but this is a mechanism actually to suppress leakage. Why leaky modes are formed? They formed because it's open resonator, just no mirrors. So it's like imagine cavity without mirrors. Of course, everything will leak, or transparent mirrors. What is the typical length of metasurfaces is possible to have data communication? Good question, very good question. So people struggling to make them larger. Few of my collaborators actually make in the micron size of metasurfaces standing on membrane and fabricated by CMOS compatible way, but this is not yet published. So, but people are working on that. Many groups try to make it to industry and application. So many motivation. Imagine smartphone, and you will have, instead of camera, a few cameras, you will have a sensor. Just every day you can check your blood sugar, or you can take any sensing just with a small opening mirror of a window in a smartphone. That's or create a holographic imaging when you talk on a Skype or Zoom, whatever. So it's a lot of interesting questions for motivations. Whew.
Thank you, Professor Yuri, for your wonderful talk.
I finish with all, yeah.
Yes. So on behalf of ICON 2021, I would like to thank Professor Park for chairing this session.
Yes. Thank you, Professor Kipchat. Very nice talking, and also we are very interesting, and I'm very sorry to have to limit this interesting discussion on this paper. But we have to keep on schedule. The Professor Kipchat will be available to answer email.
Yeah, sure. Send me email.
Yes.
Thank you very much.
If the session is over, thank you, Professor Kipchat, again. Thank you very much.
Thank you.
Okay. I'd like to thank both the keynote speakers and the audience for providing such a very nice, interesting talk and discussion. Okay, this session is now closed.
So now, I hand over the session to Professor Sasidharan. So thank you, Professor Park. Thank you.
Thank you very much.
Professor Yuri. Sir. Sir.
Hello. Excuse me.
Hello.
Hello. Can you hear me?
Yes. Just
Okay, so this is Kurosh. I am the next speaker. Do you know what we should do? We suddenly close the session.
Hello, Professor.
Hello. Hello.
Hello.
Yes, I'm online. Yes.
Yes, sir. So welcome for ICON 2021. Actually, now I will introduce chairperson for this keynote talk, and now after that you can continue, sir. So actually, this keynote talk going to share by Professor Yams, research professor, HOD chemistry research from SRM Institute of Science and Technology. So actually, his research interest are actually development of catalyst, electrocatalyst, specifically for electrochemical energy conversion and storage, and synthesis of electrode materials and electrolytes for lithium-ion battery and sodium-ion battery and metal-ion batteries. Actually, as per as well as supercapacitors and the development of fuel cell catalysts, including ORR, HER, and OER, and awards like JSPS and CSIR UGC, AIST Fellowship from Japan, JST Fellowship from Japan, and also JSPS Research Associate Fellowship. His H index is 32, citation index is about 3000. So with this short introduction, so I hand over this session to our chairperson, Sitaran sir, so you can carry on.
Professor Sachidhar, we could not hear you. Please check your audio, Professor Sachidhar.
Mic is off, so can you? So we couldn't.
Excuse me. Can you hear me?
Yes, Professor Karosh, we are hearing you. We are waiting for chairperson to start the session. There is some problem with his audio.
Okay.
Professor Yuvraj, in case if there is an issue with Professor Sachidhar, you please go ahead.
Okay.
You can introduce.
Okay.
Yes.
So, sir, can I wait for 2 more minutes, sir, or can I go ahead?
Since Professor Karosh is waiting.
Okay.
I think we can start because we are a bit over time.
Yeah. So, good morning, participants. Today we have, keynote 10. Actually, the title is Liquid Metal for Catalysis and Carbon Dioxide Conversion by Professor Koros Kalandar Jade from University of New South Wales, Australia. And so I will introduce about Professor shortly. So actually, his research interests are sensors, nanotechnology, and liquid metals and material science, electronics, and actually enterology and medical devices. And he received awards and achievements like actually many number of many awards like
Robert Boyle Prize for Analytical Chemistry, from Royal Chemistry of Royal Society of Chemistry, UK, very recently, and Clarivate Analytics, highly cited researcher for 2020, 2019, 2018, and actually, ACS award, and also advances in measurement science and the Institute of Electrical and Electronics Engineers, IEEE Sensors Council, actually Technical Achievement Award, and Academic Sharp Brain Award, and the finalist of the International AMA Sensoric and Mesh Technique, AMA Innovation Award. So like that, so we have several awards. So with this, short actually introduction, so I hand over this session to Professor Koros Kalandar. Sir, stage is yours, so you can continue.
All right, thank you very much. I'm wondering whether you can see the presentation.
Yes, we can.
All right, fantastic. So I can start. So thank you very much for the introduction. Yes. Today I'm going to, as you mentioned, talk about liquid metals for catalysis and CO2 conversion. So what these liquid metals are, basically, from past, we have some definitions. Any metal that holds the liquid form at nearly room temperature, which are mercury, the famous one, francium, cesium, gallium, and rubidium. So basically, they are flexible, they have fluidity, and they alloy with other metals. They can make low temperature, low melting point temperature alloys. They have high thermal and electrical conductivities, similar to other metals. But apart from those, including looking at this family, two of them are really useful. We're talking about mercury and gallium. The rest are not practical to work with because francium is radioactive and cesium and rubidium are explosive. Unfortunately, mercury is highly toxic. Nowadays, we are talking about completely banning it from most of the research, which is very sad. What remains is gallium. But establishing a whole family, a whole field based on one single element is very limiting. So me and my colleague, we cheated a bit. We said any metal that has melting point less than 330 degrees, that are the post-transition metals, are defined as liquid metals. Basically, indium, tin, lead, thallium, and bismuth are included in this family as the members of this family. When we say 330 degrees is an interesting number because basically when you go to your kitchen, that's the kind of temperature that you have access to in an oven or in a kind of professional kitchen. So it can be, processes can be done at home, not easy. Now let's go back to the representative of this family, gallium. Melting point is around 30 degrees. You put it on the palm of your hand, it melts. You can play with it like that, very similar to mercury. It can alloy with basically other post-transition metals or the zinc family metals at high concentrations like indium, tin, bismuth. They make very interesting alloys. For instance, one of them is E-gain, 75% gallium, 25% indium. And the melting point goes down because entropy of this alloy is higher than gallium itself. It goes down to 15.7. And so at room temperature is actually a melt. Now, what is another interesting property of gallium is that when you leave gallium, very different from mercury, in ambient environment with 21% oxygen in the environment, it produces gallium oxide. It's two-dimensional material, very similar to graphene. It's very strong across the plane. And basically, because of that, you can make droplets that go on the top of each other. This two-dimensional material holds these small droplets. You can print them three-dimensionally for about 2-3 centimeters on top of each other. It's not Newtonian or your logical characteristics that allows all these things to happen. Can we observe this two-dimensional material? Can we start looking at it? Yes. Make a droplet of this gallium, start shaking it. When you shake it, basically you see these kinks and the surface, and if you shake it more, they come off the surface, they restack on top of each other, make, of course, other stacked nanomaterials. But basically, using a scanning electron microscope, you can see them, these two-dimensional materials, or TEM. Now, I'm going to talk about different capabilities and properties of these liquid metals. It's just a few of them. There are so many more. I talk about this two-dimension on the surface, then I go to the bulk. Now, sorry, before talking about the two-dimension, I just want to say that, look, you can shake them, shake this liquid metal, very similar to when you put two immiscible liquids next to each other. They don't mix. You have to shake it and make an emulsion in one another. So if you put liquid metal, for instance, in water, start shaking liquid metal, sonicating it water, start breaking down to small droplets. The good thing about this droplet is they are stable. They're two-dimensional gallium oxide, stabilize them very quickly. So they are formed, they remain stable till you break them again by sonication. So here I show you an example of how to use this, for instance, small liquid metal droplets. You can put them as on the surface of an electrode, and you use this electrode for sensing heavy metal ion, because you can do stripping voltammetry, apply a voltage, swallow, for instance, cadmium or lead, which are heavy metal ion around, and then you reverse the voltage and send these ions out. It gives you a current. Current is proportional to the amount of ion that goes in. Actually, this is a very good, super sensitive heavy metal ion sensor. At the moment, it's commercially used in some reservoirs around the world. So going back to the two-dimensional material, now everybody is talking about two-dimensional materials. It's like 2 decades now, nearly 2 decades. And high, large-scale production of this two material has remained a problem. Why? So we are talking about molecular beam epitaxy and ALD, which is possible to make very good quality two-dimensional materials, but they're very expensive, and generally cost of making wafer scale using this kind of processes is very high. Chemical vapor deposition of some of the metal oxide and metal dicagonal came actually from my lab. Many reactors are now sold based on this method commercially all around the world, but still they have their own problems. You want to, for instance, deposit molybdenum disulfide or molybdenum trioxide on the surface of silicon substrate and use them for electronic devices. Here you see in the picture on the corner top that they start from the nucleation center, they grow two-dimensionally, but again, the dimensions are limited. For instance, 200 and 300 micron on side. They go on the top of each other, they make multi-layers. Even if they go on the top of each other, they stitch. So we have scattering points. So imperfect scattering points and imperfect surfaces, there are problems. You can resort to liquid metals and two-dimensional material, which is naturally formed on the surface, like gallium, indium, bismuth, and tin. We let this oxide to form on the surface, and if you bring a secondary substrate, bring it and touch those two-dimensional material, they stick to that substrate because the van der Waals force is higher to the substrate, and we can harvest them. The good thing is the material that you obtain, you can make it single crystalline, the size of a wafer, because the oxidation happened based on Mott-Cabrera oxidation procedure. There is no grain boundary, and it's a low temperature process. As these materials, they are formed into liquid form in very low melting point. Look at one of the examples. This is tin, melting point of around 270 degrees. You melt it, and it's not self-limiting like gallium. It becomes thicker and thicker in time. You can make it self-limiting if you reduce the oxygen in the ambient. As you see, we took a glass stick and just remove all the oxide formed on the surface. Very easy. It doesn't stick, the oxide doesn't stick to the surface of liquid metal, and you can harvest it. Instead of the glass stick, you can bring a substrate near the surface, take the substrate away, and if you control the ambient oxygen, you can produce thin oxide monolayers again and again and again very quickly, and this was done by hand. As you see, also the dimension is about 1 centimeter diameter. It's quite large. Okay, what's the practical usage of these things? Here, one of them that you can see, gallium nitride, two-dimensional one. The mobility of it is quite large, 20 centimeter square per volt second. Gallium nitride, if you may know, is used in LEDs, which are used in low energy lamps that or bulbs you use at home. Basically, if you remember, we can make two-dimensional gallium oxide, we can harvest it, but that's oxide. You can use actually the oxide to make transistors. That's another question, another story. Here we expose it to a precursor of nitrogen. At 800 degrees, we transform that gallium oxide to gallium nitride. As I mentioned to you, is a fantastic mobility, is highly crystalline, and we made some LEDs that it actually works. So practically, you can take this for commercial application. Another thing that's moving towards commercialization is this example, making ITO glass. If you're carrying a mobile phone with you at the moment, the conductive, transparent material in the mobile phone, in the display, is ITO. So they deposited using different kind of techniques like printing or sputtering. The problem is some lack of transparency. We want it to be more and more transparent. Also, we want to have flexible mobile phones. At the moment, we have some examples, but they're not real flexible mobile phones. The main display doesn't flex. So anyway, let's make this ITO happen. We combine indium and tin together at different concentrations, and we have the liquid metal. We squeeze it between two substrates. We take away the substrate, and also this liquid goes away between the two substrate. It doesn't stay there squeezed out. What remains is transparent ITO. You can do it again and again. You have 1 layer, 2 layers, multi-layers of ITO on the surface. Transparency is fantastic, it's 98%. Imagine that you have a mobile phone with such an extraordinary transparency. Another thing is it's flexible because these are two-dimensional indium tin oxide crystals, like papers in a book. You can bend it forever without breaking it. The conductivity is actually as high as the conductivity comparable with the commercial one. So this is moving towards the commercialization, as you see, a process that came from a simple harvesting of the two-dimensional material from liquid metals. Now, can we do other magic using this? We are moving now towards electrochemistry. For instance, this is another example. I can make two-dimensional graphitic materials like graphene oxide on the surface of this very active liquid. But we did some DFT. We realized that if you have CH bonds, bring them to near the surface of liquid metals, we can dissociate the CH bonds. And we tried many different precursors: methanol, ethanol, isopropanol, glycerol, acetone, acetonitrile. Some of them are very simple carbohydrates. Some of them the materials that have nitrogen in them, and put them into different electrochemical settings, and we started applying the voltage across against a reference electrode. If we have no precursor in the environment, just an ionic environment, as you see, liquid metals start deforming, nothing is formed on the surface, remains highly reflective on the surface. Now we add precursor, which one of these simple carbon hydrogen compounds, some with nitrogen, some without nitrogen. And you see very quickly you have these graphitic materials formed on the surface. All right, what have we created? We started characterizing it, as you see, from Raman characterization, we have B and G band. It says, yeah, it's a graphitic material, but they're very broad. So it's a graphitic material full of defects. We zoomed in using transmission microscopy, and we say, yeah, it's not smooth. It's wholly graphitic material, and it's sort of a graphene oxide with lots of holes. We can use it as an electrode material. You have to reduce it. It's wholly, so it's an ideal material for making lithium-ion battery electrodes, and we did it, and it was fantastic. But we continued our talk that can we make it even smooth surfaces? Yeah. For instance, if you paint gallium on the surface of another substrate here, we paint it on copper, it doesn't deform anymore. As a result, those stretches doesn't happen to make holes in them. As you see in the AFM image here, is quite perfect now. It's a graphitic material from Raman measurements. As you see, they are highly crystalline. And interestingly, from FTIR, you can see that if we use a precursor that includes a nitrogen, we can also have doped nitrogen graphitic material coming out. As you know, doped graphene is a highly catalytic electrode. We continue towards non-crystalline nanoparticles and crystallization. What so far I talked about is about harvesting these two-dimensional materials from the surface of liquid metals, because they're different from normal liquid. Liquid metals become layered and lose their entropy when they are near an interface. You expose it to ambient oxygen, ambient sulfur, you produce molybdenum, you produce that metal oxide, metal sulfide. But if you supersaturate the bulk of these liquid metals, and then you create the crystals, the secondary crystals of the additional material into this liquid metal, it's very similar to when you add sugar to water. You add more and more sugar to water, you heat it up, you supersaturate it, you let it cool down, you see the crystals of sugar comes out, and you have the crystals of candy crystals that you can eat, of course, very enjoyable. Here it is. Oh, sorry, going back. The problem with liquid metal is liquid metals are, the surface tension is very high. Harvesting this material, this small crystal which was formed inside liquid metal, is very difficult. You have to break this tension of the surface of liquid metal. How can we do this? One of the ways of doing this is to apply a voltage across. When you apply it, this two-dimensional gallium oxide, titanium oxide, whatever tin oxide which is formed on the surface, they go away. You can use a voltage together with an acidic or basic environment to etch away this. Or you can form two-dimensional material on the surface. You can play a lot. It depends on whether you apply an anodic voltage or cathodic voltage. Doing that, then you start shaking it using the same voltage, you're passing it out, you bring all these nanomaterials inside the bulk of the liquid metal to the surface, and basically you spit them out. Take a look. Here we add some tin into the bulk of the gallium, and then we apply the voltage. As you see, they're coming out. Here in another example, we added indium, and it comes out in a different form. Each metal comes out is in different form. It's very interesting. So we suddenly have a reactor to create these nanomaterials. Here are characterization of these nanomaterials produced. For instance, the right side is zinc. Another example, the left side is tin. Tin or indium, they come out with a core metallic, and the surface is a metal oxide. Zinc comes and get templated on the surface of liquid metal, comes out as these hexagonal sheets, which are oxidized very rapidly in the liquid. Now, we can put everything inside, extract them. We can create things on the surface of liquid metals, the two-dimensional structures. What if we add secondary material into the liquid metal and start characterizing it and see whether we can make functional systems for conversion? Here, our interest at the beginning was CO2 conversion. So we knew that cerium is a good catalyst, and cerium oxide as well, for breaking down CO bonds. We added cerium, supersaturated the liquid metal gallium at high concentration of cerium of 3%. Solubility of the cerium into gallium is only 0.1%. And we shook it. We made the small particles to be able to TM these small particles and see whether we have the crystals of cerium or not. And as you see, we had beautiful nanocrystals of cerium, for instance, 5-10 nanometers, very close to the surface. And surface was cerium oxide. I'll show it to you in the next slide. That is slightly substoichiometry of cerium oxide. And it seems that this cerium also remains metallic, but very close to the surface. So we thought, why don't we something very interesting? We put this droplet, a large droplet of cerium oxide on the surface together with lots of cerium, and we immersed everything in an electrolyte. We applied a voltage and we bubbled CO2 around it, and it works. CO2 come to the surface. It produces cyclic process. It oxidizes surface from substoichiometry cerium oxide into a stoichiometry cerium oxide, and also leaves the carbon sheets on the surface. And these carbon sheets, because the surface of liquid metal, they don't stick to the surface. That cocking that should happen normally on a solid electrode, you see in this figure here, figure B, and reduces the current very rapidly to zero. It doesn't happen. The current remains high, so this process happen forever, and these carbon sheets come off the surface and float into the electrolyte. We characterize these carbon sheets, they're actually graphene oxide, and the onset voltage for this to happen was very low, only 0.3 volts. Although Faraday efficiency was very low at about -1.8 volts, the Faraday efficiency is around 80%. It was a first system that shows that yes, electrochemically we can produce basically graphitic material from conversion of CO2 without cocking the electrode. Now, there is a problem. The surface area of liquid metal is very limited, and as a result, you have only one bulk and some layers which are produced on the surface. Faraday efficiency is very high, but the total efficiency is very low. How can we increase it? We decided, okay, we shake this our liquid metal and we make some droplets. Initially, we thought, okay, if we have these droplets around one electrode, and if we are in the percolation limit that they touch each other, that means we sonicate this electrode all the time, we should be able to make a functional electrode of liquid metals with very large surface area. It didn't work, but amazingly, we saw that with some specific condition that I don't explain to you too much about, we could convert just by sonicating it. CO2 bubbled into the liquid around liquid metal into the oxygen and graphitic sheets. Now, just briefly tell you that some of the condition didn't work, some of the condition worked, and one of these conditions produced silver 2 gallium rods. So anytime that we had rods and droplets together, the system worked and converted the CO2 that was bubbled into the environment. We're very surprised because we did all the calculation, it couldn't be catalytic. The calculation based on catalytic conversion of CO2 never added up. And we continued characterization of the system for almost a year. We realized we have nano electrochemical system. This silver gallium rods together with the liquid metal droplets, they were making nano electrochemical systems. So what happened that anytime these nanorods were touching the surface of liquid metals, the CO2 that was dissolved into the electrolyte was coming out of the solubility, because that friction was producing a slight increase in temperature at that point, and they were going against each other. and we had some electric charge produced because of this separation. The electric charge was electrochemical cell. It produced, it basically produced gallium ions and CO2 minus, as you see. And this actually continues. Gallium goes there and produce carbon monoxide and further gallium ions, and further continues produce gallium sheets. Gallium ions and carbon sheets. And the other product that's produced is oxygen. And of course, we have lots of electrons produced as well. But it's an electrochemical cell. It's closed down by the rods. And these rods basically take the gallium ions, take the electrons, and produce gallium liquid. That gallium liquid doesn't stick to silver to gallium because it's saturated, comes off the gallium rod, gallium silver rod, and goes back as droplets of liquid metal. So the system is closed. It's a closed loop, as you see. If you don't have those rods, it won't be a closed loop. It's not reversible. So we started to scale up, and it's working. Basically, it's a system. You just shake it, and what you obtain, as you see, become very black, loss of carbon and oxygen. We look at the properties for CO2 conversion. We could see 92% oxygen conversion. That means 92% of all CO2 molecules that were going in. Of course, some could escape, but the rest were converting to carbon and oxygen. Amazingly, the total input energy was only $50 per ton of CO2 conversion. This is a record. I think this can be of a great, it can be a great solution for carbon conversion. Hopefully it'll be commercialized very soon. We're in the process of doing this. Now, if you go to, this is the last part of my talk. If you go to conventional liquid metal metallurgy and see whether we can use those kind of conventional tricks for making electrodes for carbon conversion or any other catalytic activity. Here, I'm showing you the example of bismuth and tin. Basically, tin melts at 232 degrees, bismuth at 271. We mix them together at different ratios. The eutectic ratio, which is the lowest melting point temperature of this combination, is at 57% bismuth, which is the melting point, which offers us the melting point of 139 degrees. So make all these melts, then we sonicate it, and we let them solidify. So when we solidify, the surface become oxide, and the core become metallic, or we can anneal it further at 600 or 700 degrees, make sure that everything becomes a semiconducting metal oxide. I show you that we can use those kind of metal oxide also for photocatalysis, but let's go back to electrocatalysis when we have the semiconducting and this oxide on the surface and core metal. Okay, if you don't shake these two material and just mix them together by hand without any extra shaking and make a bulk and solidify it, we're talking about classical metallurgy. So for instance, we have 20% bismuth and 80% tin. We have rods of, we have lots of rods of bismuth into an ocean of tin, crisscrossing. If you have 20% bismuth, 20% tin and 80% bismuth, then you produce classical plates of bismuth and tin crisscrossing each other. When we go to eutectic, entropy is high. Instead of producing this very highly ordered structure, we get non-ordered structure when we solidifying it because it happens at a very low temperature, and it's kind of fibrous structure that you see. Now, there is an advantage in producing this fibrous structure. Basically, if we do the sonication of different ratios and then let them solidify at lower temperature, we realize that when we are talking about using the eutectic system that produces inside those kind of fibrous structures, we get loss of defects and edge locations and increase boundaries, both on the surface and the core of the materials that are obtained after sonification. Now, on the surface, we obtain tin monoxide, tin dioxide, and bismuth oxide. Okay, we put everything for a test. As I mentioned to you, we're doing classical formation and conversion of CO2. We made electrodes using different concentrations of bismuth and tin, and we realized that the electrode that we used and we made out of the eutectic system had the highest conversion efficiency. Here, Faraday efficiency was about 80% again, and the low voltage of minus 1.1. And the format conversion was very efficient. Again, we associate everything, this high efficiency, to that extra, let me go back, fix edge dislocations and increase boundary condition that we obtain using the less ordered eutectic system. You can do really cute things with it. For instance, here I show you an example. One day we were very bored. We said, okay, what if we start with fused metal? Fused metal is a famous combination of tin, indium, and bismuth that melts at around 61, 62 degrees. We sonicated it at high temperature. We obtained these balls. And we said, okay, what if we have this slurry of these balls and put it in a solution of sodium bicarbonate and HCl and see whether it bulged into a small foam shape or not. And actually it did. We put it at different concentration of HCl, the acid, at 1 mole, 10 mole, 0.1, at different temperatures that I'm not showing it to you. And we look at, for instance, the surface area. As you see, 1 mole, you get these highly porous structures, which is very rough. Roughness decreases, you get more larger nanoparticles on the surface of the pores at 0.1 mole, but at 10 mole, it seems that things are etched away, and we don't see those small secondary formation of the nanoparticles on the surface of the pores. Let's show you how it works. You put a slurry into 1 mole, gradually it foams, it becomes bigger and bigger and bigger. You have to wait for like 10 minutes for that foam to reach the size of the beaker. If you make it if you make this at 10 mole, highly acidic environment, this foaming happens much faster. Okay, these foams are very important, metallic foams, for catalytic properties, catalytic activities. First of all, we characterize what we obtain, and then we use it for practical application. For instance, if we have 0.1 mole, everything is happening very slowly. We get the combination of indium oxide and tin oxide, and on the surface, these small nanoparticles, and bismuth oxide underneath, and the metallic and semi-metallic part underneath. Combination changes because at very high acidity, basically indium oxide are etched away from the surface. Now, very interestingly, we did some theoretical calculation. We realized that foaming happens at high temperature, and it's a temperature that's produced during the foaming by the reaction. And according to this characterization, the temperature should happen at around 200 degrees. At that temperature, we obtain those oxide, metals in the core and oxide on the surface, according to the theory. We did then a measurement of the temperature. We realized that, yes, everything was good. Now, we put everything into practice. We use the foam electrode as the working electrode, and we put a counter electrode, and we see what will happen to, for instance, catalysis of some dyes, polluting dyes. We realize that we can do electrocatalysis. After, for instance, 2 hours, we go to 50%. We can do photocatalysis without any electrode. We go to about maybe 55%, but we can do electrophotocatalysis because very porous light was penetrating into the core and getting absorbed by it, and the efficiency was going up about 80%. We did CO2 electroconversion again. And actually this time, because everything, all these nano-sized structures that we made, were very well connected to each other, the applied potential could go lower, and Faraday efficiency even went higher. It was a very good efficient system for CO2 conversion and formate production. Could even do bacterial electrofiltration. For instance, if you see before electrolysis of water happens as less than 0.8 volts, we could get 45% efficiency. We could put a few of these in series and completely eliminate the bacteria in the environment. You can look at how to reduce the cost. One of the problems with that, for instance, foaming, was that indium is very expensive. We realized if we eliminate indium, foaming doesn't happen because the nanoparticles of bismuth and tin never got attached to each other. That indium, if we could add it at 1%, even less than 1%, act as a glue. And it was very interesting. Indium was winning the competition during melting coming to the surface, and when foaming was happening, this surface indium was were making stretchy contact points between the nanoparticles. So we could reduce even the cost for practical applications. Reality is you can do other things as well. For instance, you can anneal all these nanomaterials that you produce. But before annealing, it's very easy to process and obtain what you want. For instance, here we added silver at different concentration to the environment, to the liquid metal. Look, silver melting point is very high. So if you want to process silver, produce something, or for instance, you want to add titanium melting point is very high. But they dissolve at low concentration or at specific concentration into liquid metal, gallium, into liquid metal indium, into liquid metal tin, or bismuth. So basically, if you add this kind of material, say secondary, tertiary metal at high melting point, you can process everything at very low melting point, and then you start your cooking, looking at different concentration. Here, for instance, we look at silver at different concentrations, and you can tune it towards the material that you want to obtain, either a metallic material or metal oxide material. After annealing, you obtain the metal oxide. Here is the example of metal oxide. For photocatalysis, basically, we could, by changing the concentration of silver, we could make it a specific methylene blue or Congo red and make it less or more efficient. So basically, you can make catalysts with very targeted pollutants. Okay, so basically today I talked about some of the applications, some of the properties of liquid metals, and a few examples of what you can do with liquid metals. These are very small applications. There are so many other things you can do. Basically, sky is the limit. You can use your imagination. The process can be done at very low temperature, under 330 degrees. If you mix them together, we're talking about even lower temperature, melting point temperature. You can do it. It's very accessible. Some of these materials are very cheap as well, like tin and bismuth. And basically, it opens up a new field. It's a very rewarding field. And I actually suggest many of you to look at these possibilities of entering the field and see what else, the things that I haven't presented today with these post-transition metals at low melting points. I would like to, first of all, thank you for listening to me, and of course, thank my collaborators, my past and present postdocs and research, and also research students, and also international collaborators at UCLA and CSU, and the grant providers in Australia. Thank you very much.
So thank you, Professor. So it is actually really fascinating, you're opening new field. And actually myself, I'm following your actually the sensor field and that nanoelectronics paper, measuring VOC from guts, So I actually, it's really fascinating. So I have one doubt, since Professor, so actually it is liquid metal. So actually, after after liquid state, so it will solidify, right? So it will solidify, right? So how we can use as a flexible electrode? So
yeah, so that's a good question. It's all about increasing entropy. For instance, gallium itself is not liquid at room temperature. But when you hold it in your hand, because the melting point is 30 degrees, it becomes liquid. So if you want to make an electrode that works on the body, on your body, right, it remains liquid. But then at room temperature is not liquid. What you do, you add other elements to increase the entropy. For instance, if you add indium to it, you decrease the melting point from 30 degrees to 15 degrees. You add a beta, for instance, tin, you decrease it further. They become more and more highly entropic, like mercury, and you can decrease even the melting point temperature less than 10 or 5 with adding different kind of metal.
Okay, so thank you. So I think before go to audience, so I have one more question. So actually, as a electrode in electrochemical application, how you control the area? So if bias, if electric bias, with the different electric potentials, there is any shape change. So how you control the area? So if, for example, if it is supercapacitor application, so we need the area, electrode area, right?
Yeah, correct. So that's a very good question. We are very lucky, as I mentioned to you, these liquid metals in the ambient environment, either in the liquid or in air, they produce that oxide layer on the surface. This oxide layer protects it, right? If the environment is not very acidic, it's not very basic, that remains there if it's more neutral. pH of between, for instance, 5 to around 9, 10, right? So if you want to do electrochemical sensing, there's no problem, because the droplets that you shake and you make very small size of them and you put them on the top of each other, you can make sure that they fuse at corners into each other, so you have electrical conductivity from top to bottom. At the same time, they're protected by that oxide around the surface, right? Now, you want to make a sensor, you have to punch holes into that oxide. You can add a secondary material, and then through that, you have ionic access from outside to inside. There are lots of tricks you can do, but you have to think about, okay, this is liquid, you have a two-dimensional material on the surface. Where should I punch through this two-dimensional material? Where do I want it? Where I don't want it?
Okay, sir. So now we can hear from participants. So participants. So if you have any queries, so you can raise hand. We will allow you to talk, or you can put it in chat box so we can read it for you.
Yes, so there are
questions
some
in the chat box.
Okay. Sir, actually, first question in the chat box, from Dr. Chandra Mohan. So how to control the layer numbers, whether nature of the surface of the substrate has any role involved in manipulating the layer numbers?
Yeah, look, this is also a very good question. The layer number is very important. Something like mercury doesn't produce any layer in ambient condition, 21% oxygen. But even for mercury, if you increase oxygen to 50%, you produce mercury oxide on the surface. Gallium oxide produces a self-limiting, produces self-limiting oxide on the surface. Very similar to aluminium. Aluminium in solid form produces a layer of aluminium oxide, protects the core of the aluminum from oxidation. Interestingly, something like tin, this oxide becomes thicker and thicker and thicker, and 21% oxygen in the ambient. Gallium doesn't become thicker. Now, how can we control it? We can increase or decrease the oxygen in the environment, put in a glove box, reduce the oxygen. We can control the thickness, right? You can electrochemically control the thickness. For instance, you apply voltage against it, put in electrolyte that oxidize the surface or reduce the surface. Then you can control the number of layers.
So actually, so from audience, Arun. So he asked if I want to mix bismuth and PB metal, actually lead material, melting point 327 degrees Celsius. So is it?
Okay, so for mixing them, you don't need to melt them, right? Actually, you can press them against each other. Mechanically, you can mix them. When you do this at relatively elevated temperature, it doesn't need to be 320 degrees, right? You can, at much lower temperature, you can mix them together. Now, the interesting thing is anytime that you mechanically put them together at, for instance, 200 degrees and push them together, they diffuse, and because the entropy goes higher and the melting point of these alloys is generally lower, of course, it depends on the ratios between lead and bismuth, then you don't need to go to very high temperature to do any of this process. At relatively elevated mild temperature, you can do it. Now, one thing about lead is, as you saw today, I didn't show anything about lead or mercury because there are heavy metal ions. Just in my lab, I try to avoid using them.
Okay, sir. So I think from audience, there is no any other question. So
Sure.
Thank you so much. So on behalf of organizing committee, I once again thank you so much for your timing. So it is really fascinating. So you're opening new directions. So thanks for that. So thank you, sir.
Thank you very much for inviting me. It was a pleasure to present here.
Okay, sir.
Thank you.
I thank the chair and the speakers for their valuable time spending for the ICON conference. We are really thankful. Thank you very much for your interest. Thank you very much.
Okay.
Now, it is time for the greetings from our associates of the conference and also our collaborators.
Ilyas.
Just.
So.
Good morning, everyone. I'm Professor Kiyoshi Ishii, the president of Shizuoka University. I'm delighted to deliver a welcome speech for the 6th International Conference on Nanoscience and Nanotechnology, ICONN-2021, which is organized at the SRM Institute of Science and Technology, India. It is an honor for Shizuoka University to join the hands with SRM IST in the academic and research activities. Shizuoka University has 6 faculties such as humanities and social sciences, education, informatics, science, engineering, and agriculture, and School of Regional Development. There are 3 master programs and 3 doctoral programs. In addition to that, we have Research Institute of Electronics and Research Institute of Green Science and Technology to promote the research activity. Shizuoka University's staff and students uphold the philosophy of freedom and enlightenment as a mainstay of education and research, and collaboration with society, industry, and overseas. Collaboration between Shizuoka University and SRM IST started in 2009 before the Memorandum of Understanding was signed in 2014. Since then, the current colleagues in both universities have been fostering the relationship steadily, which have led to the promotion of double degree program in the doctoral course and the most active framework among the collaborations between the other foreign universities and Shizuoka University. Shizuoka University has organized Inter-Academia Asia Conference since 2014. In 2016, the 3rd conference was held in India, and the community of Asian higher education institutions from Japan, India, Bangladesh, Sri Lanka, Hong Kong, Malaysia, Thailand, Vietnam, Indonesia gathered together and discussed the global education and research at SRM IST. Shizuoka University is grateful to SRM IST for their tremendous support as host of many joint conferences, including ICONN. I hope that as the speakers and researchers will enjoy the scientific discussions and strengthen the collaboration. Finally, I would like to express my sincere thanks to conference chair, Dr. John Sribarandash, all staff or organizing committee and participants.
Thank you, President Professor Kiyoshi Ishii, Shizuoka University. Now I request distinguished Professor Suresh Bhargava, RMIT, Melbourne, Australia.
Can you hear me from here?
Yeah. Yes, sir. Yes, sir.
Okay. Well, I can't see my video. Yes, I can see right now. Okay. Well, it's a great pleasure to join you, my colleagues. Actually, I will always consider India my home. And I must share with you that I was a participant in the Sangam program of the IIT Madras. And I enjoyed my video there. Probably you can see on the YouTube as well. But saying that, first of all, coming to the RMIT is the largest tertiary institution of Australia. Nearly about more than, at one time, nearly about 90,000 students enrolled with RMIT. And it has its presence in Barcelona. It has its presence in Vietnam, both capital of the Vietnams, the old capital of the Vietnams. And also it has its presence in Hong Kong, Singapore, and also in India as well in terms of the RMIT ACSR programs. RMIT has joined the Academy of Science and Innovation Research, which controls nearly about all the CSR labs. And they have a double PhD programs going on with that, and particularly the IICT Institute of Chemical Technology in Hyderabad. We are running this program for last 5 years, and nearly about 24 PhD has been graduated. In ACSR programs, the labs in Chennai is also associated with these programs, and also the other CSR labs are also involved, like NPL, NCL, IIP. They all are involved in this double PhD program as well. Saying that, we are also involved in Australia-India Strategic Research Funds in the Global Challenge Fund, $6 million. We just have one thing on the 3D printings with the mini DMA with the Institute of Petroleums, and also the industry, Indian industries, petroleum industries, BPCL, and CSRO here, Melbourne Union, RMIT. RMIT introduced a new concept of 3D printing in catalysis. And the first articles came from RMIT, from my group, which has gone viral, and it has been probably become the hot paper of the years. We are very active in research. In fact, I heard from my great friends and colleague Karosh, who was in RMIT, who grew up in RMIT. Actually, he's a dear friend, and he grew up with me as well. And then he moved to the University of New South Wales about a year ago. But RMIT is very strong in the nanotechnology, in the biotechnologies, and also in the catalysis areas. We have nearly about 4 professors in there. RMIT is also a pioneer in the 3D printings, additive manufacturing, and they are now applying this additive manufacturing in different fields. Starting from my side, I have a center, research centers known as ChemEth, is a center of advanced materials and industrial chemistry, which was established nearly about a decade. There is about 60 scientists and students work in the centers, and we make the translation research is our focus. Center published nearly about 130 Q1 articles every year. The citation of the center last year is over nearly about 99,000. If we added all the core members of the centers only. And it has a research in many fields, including applied electrochemistry, catalysis, nanotechnologies, sensor technologies. The most recently, the research came out from the sensor group is we developed a hydrogen sensor at the room temperature, at the lower temperature, at very low concentration, which has gone viral. It got the allometric scores about over 190. and the major companies like the contractor of the NASA and also the Safran who manufacture the Rafale and military aircrafts. Now they are in deep discussions with us, along with many other interesting parties from the globe as well. I have been active in India from the last about 2 decades. I have been advisor to the government of India many times, also a UNDP advisors, and also I have been associated with the IIT Bombay at the moment under the Basra programs. Before then, that IIT Bombay offered me, which I accepted as a distinguished professorship at the chemical engineering, which I am associated with that. I have been visited several times to the Chennai or IIT Madras, but my main research center or IICT. I wish that this ICON conference is really a great initiative, which brings the a lot of scientists from all over the world on the one platforms. And India is hosting in an amazing way. I can see it, that how many people and how good lecture the previous lecture course did it is in there, and also bringing the Japanese professors, the previous speakers. So what it does and what I want to see probably at the end of the day, it can create an intellectual infrastructure for tomorrow, for providing the best training for the young researchers and some output of the research. With these themes, probably I will congratulate to the organizers who has organized this conference very much in times. Thank you very much from Professor Kathy Gums, as also Yuvraj is in there too, and Sandeep as well. So there's a lot of good people to whom one day I will meet in face-to-face, hopefully. So good luck to you guys. I will be very excited for my lecture tomorrow, which I'll be talking about.
Yeah, thank you, Professor Suresh Bhargava. We are really excited to look towards your lecture, and the details that you elaborated. It was it's very interesting, and we expect the collaboration with you, RMIT, that grows further. Thank you very much. Thank you for your kind words. Thank you, sir.
How to say one small things very quickly. I just forget that there were the times when your current vice chancellor was in Jaipur, Rajasthan. So I am a good friend of him because I visited Manipal in Rajasthan when he was a VC. So if you have, or if he's there or somewhere, please convey my regards to him.
Thank you, sir. Yes, we will do. Thank you. Thank you very much. Dear participants, the first keynote session concludes here. Now parallel session that you can visit. So you all know that there are 7 sessions: 3A, 3B, 3C, 3D, 3E, and 3F, and 3G. So you know that link. Based on your link, please visit your respective sessions. Thank you. Thank you all. So participants, after the parallel session, that will be ending by 12:30. So again, come back to the keynote session. So now the parallel session will be from 10:55 to 12:30. After that, we will come back to keynote session. So keynote session will start by 12:30. Then it is keynote lecture 11, development of photocatalysis and solar hydrogen production system for a large scale application. Professor Kazunari Domen. So after the parallel session, let us assemble in the webinar at 12:30 p.m. Thank you all.
Hello, Professor Domain. Good afternoon. Can you hear me, Professor?
Hello, can you hear me?
Yes, Professor. Yes, we can hear you.
I like to try to share my screen, my data. Is it okay?
Yes, yes, Professor. So thank you for accepting our invitation, Professor. My name is Sandeep.
Okay, yeah, but sorry. I think I don't see that.
At the bottom of your screen, Professor, one green color share screen button is there at the bottom of Zoom. Yes, yes.
Yeah, now, okay.
Yes, Professor.
And then this is, I think this is
full screen.
Yeah, full screen. Is it okay?
Yes, Professor.
No problem. Okay, so should I keep this I should once stop the sharing?
Yes, Professor.
Yeah, okay. I don't know how to stop.
I will stop, Professor. I will stop it.
You can do that?
Yes, Professor.
Okay, thank you.
Yes.
Okay.
So in SRM, our group also works on water splitting, and we have been following your work very closely, Professor.
Oh, really?
Yes, yes, yes. And we are very, very grateful that you have accepted our invitation.
Oh, okay. Because this is a video
Yes.
virtual conferences. There's no problem to attend the meeting. Yeah.
Yes, yes, Professor.
So are there many people working in the photographic reactions in India?
Yes, yes, Professor. Yeah, there's a very large community in India working on photocatalysis, artificial photosynthesis for various applications, nitration, CO2 conversion, water splitting, as well as pollutant environmental remediation as well.
I see, I see.
Yeah, so our group works on both environmental remediation as well as water splitting.
So what kind of materials are you using?
Yeah, we have been using with graphite carbon nitrate and metal oxide, and with carbon support. Yeah, yes. But we have been following your work on oxynitrides very, very closely. Yeah, recently you achieve nearly 100% quantum efficiency.
Yeah, yes, it's so lucky.
Yeah, I mean that is like a breakthrough. Yes. Professor Satish Krishnamurthy is also there. Hello, sir. Yeah, your mic is.
Yeah, good morning. Good morning, Dr. Sandeep, and good morning, Professor Kazuri Doman.
Yes, good morning.
Good morning. Good morning. My name is Satish. I work as a professor in UK, and it is actually 7 o'clock in the morning. I presume it's night for you.
Oh, it's very early morning. We are now 4 p.m.
Yeah, I know. Good. Yeah, it's a pleasure to meet you. and particularly like we have grown up reading your papers. Probably since 1980 you have been publishing. I don't know.
Yeah.
Some people,
That's the first paper.
First paper, yeah, on photocatalysis.
Yes.
And some people grow up seeing the sun. Probably you have the sun by itself in you. We're doing such a really fantastic knowledge transfer job, actually. And
thank you. Yeah.
We have lots of people have benefited, and probably one of the beneficiaries me now also. So we have got now a very big European Union project.
Yeah, I know.
Wastewater treatment. And this is particularly focused on textile industry, and we would be using photocatalytic materials to do that. One of the arm is to use photocatalytic materials for dye degradation and also coat on optical fibers as well. So there are quite a lot of big consortiums happening.
That's interesting. That I once invited to such a kind of advanced oxidation processes, including the photocatalysis. I enjoy it very much.
Yeah, absolutely. And I think you have James Durrant is also one of your collaborator, I guess.
Yeah. We know to each other very well for a long period. Yes.
Professor, yeah.
His group is very, very good at measuring the time resolver spectroscopy. So we are collaborating frequently. Yeah.
So I think you have a very busy schedule. I was surprised to see your name. I'm pleased to see you here. And this is really fantastic. And I think lots of younger generation people will really get benefited from your talk.
I hope so.
Yes, that is so true, Professor. Yes, we are extremely blessed to have you here.
I see. Thank you.
No, I don't know how Sandeep you have got him, because he is like very difficult to catch him.
It was just pure luck and blessing that Professor accepted our invitation. Yeah, so I said because I have been following Professor's paper for a long time, and so I just thought maybe let's see how good our luck is. So I sent a mail to Professor Domain, and thankfully he accepted our invitation. Yeah.
Yeah, actually, I have been to India maybe several times, and I already enjoyed the meeting. It is a little bit hot, but it's a big country. Yeah.
Yes.
1 billion people with different languages, different culture.
Yeah.
I don't know, different requirement as well. And they are blessed with a lot of rivers. That's most important thing. I think that's the only country in the world has plenty of rivers. Fantastic place.
How about the solar energy? Amount of the solar energy in India? Do they have a lot of energy in India? Plenty of solar energy.
Yeah. We have been working on solar energy project as well, but one of the challenges which we are working is Rajasthan is one of the places where they get plenty of solar energy, but also they get plenty of dust as well. So we are working on self-cleaning materials for the glass for solar cells, and it is something very interesting, Professor. It's like when the sand goes and sits on the glass, it forms two different varieties as the time. Two different chemical reactions are happening. One at the very top of the layer, it becomes really sticky, and the top is very fluid. And we were characterizing through XPS as what are all those components and what is the chemical functionalization we need to put on glass, make it transparent to make it make the water drops float on its own.
I see.
Self-cleaning gas. So it's a nice project funded by Global Challenges Research Fund. So yeah, it is. We are working on that, and solar energy is plenty. That is the reason why they are working on, even there's a project on Clean Ganga. That is also they wanted to work with solar.
You know, unfortunately in Japan, we do not have so much solar energy. We have a lot of rainy day and a lot of snow and something like that.
Yeah, but if you see the amount of research funding, England does not have solar at all.
Yeah, I understand.
Maybe once in 6 months or whatever. But the amount of research funding on solar is plenty here. Whereas I think the India has to really increase their funding on solar, to focus on solar and extra. I think there are lots of challenges, I think.
Yeah.
And the private universities like SRMs are really doing well, having a dedicated scientists. They have employed dedicated scientists exclusively for research to pump up the research. So it's, I think, probably in another 10, 15 years, I think there will be a different change.
Yeah, and definitely we would like to have a Professor Domain for next ICON, visiting SRM Institute of Science and Technology in Chennai.
Yeah. I like to.
Because Professor Satish Krishnamurthy visited our campus, I think, couple of times.
Many times. We have an MOU with you as well. And I am also an adjunct professor at SRM.
Chennai is the second largest city in India. The biggest city.
Fourth or fifth big.
Okay.
Yeah. So we have four metros here: Mumbai, that is Bombay, Delhi, Kolkata, and Chennai. So these are the four largest cities.
I see.
Yeah, like Tokyo. More crowded.
Your population is about 10 times larger than that.
Yeah, somebody, Sishandu, has commented solar energy is very intense in Gujarat, in India in summer.
Will get start on time?
Yeah, I think we should start on time. I like to start on time and finish on time.
Yes, Professor. Another 2-3 minutes we will start.
So can I put this slide in or this one?
Yes, Professor.
This is a little bit old picture for me.
We want to keep you young. We want to keep you young.
A little bit young, yeah.
So I will at 40. You have a 45 minutes, Professor. So I will give you a nudge at about 35 minutes first nudge, and then the 40 minutes second nudge, and then you can wrap up. Is that okay?
Yes.
Yeah. And
I try to do that. Yeah. I try to be in time. Yeah.
I think we have to start now.
Yes.
All the participants are okay.
Good afternoon.
Good afternoon.
Yeah, good afternoon from India, Professor Satish Sir and Professor Kajanuri Doman.
Thank you very much. Good afternoon.
Yeah, I welcome you all for this, afternoon session from India. Actually, I would like to. Now we have a keynote lecture, that is 11, development of photocatalysis and solar hydrogen production system for a large scale applications by Professor Kajanuri Doman, University of Tokyo, Japan. Before that, I would like to introduce the chairperson, Professor Satish Krishnamurthy, School of Engineering and Engineering, the Open University, UK. His research interests are preparation and characterization of various nanostructured films and metal nitrides and oxides for electronics, optical, and energy applications. Synchrotron-based photo emission, X-ray emission, X-ray absorption, and X-ray excited optical luminescence to study the electronic and optical properties of carbon, silicon, graphene, nanoluminescence to study the electron particle properties of carbon, silicon, graphene nanostructures, and bulk film. There are many achievements and awards that we have listed a few. Fellow of Royal Society Chemistry, Fellow of Materials, Minerals and Mining, Vice President of Indian Chamber of Youth Entrepreneurs. Sir, please take over the session. Yeah, thank you.
Yeah, thank you very much, Professor Karthik. And it has been really, really absolute pleasure to welcome Professor Kaznuri Doman. I think I call him as an energy man. Probably he's having a lot of solar, even though Japan doesn't have much sun. I think he's a man of sun and energy. And we all grow reading his paper since 1980. He has been working on photocatalysis. People even don't know what is photocatalysis that time. And from that time onwards, probably over 800 publications. I think 700 original review. I think it has now crossed 800. And there is no accolades or nothing can beat him. I think he's a man works all the time and inspiring people and younger generation over the years throughout his journey. It has been really absolute pleasure to welcome you, sir, for this wonderful ICONN occasion. I think I'm pretty sure SRM and all the people who are listening here, I think we have more than 132 people already in stage to hear your lectures in this pandemic time. And also, I know how busy you are. And without any further ado, I would welcome you, sir, for the inaugural lecture. You have many accolades, and then it is very difficult to spell. And I would like to people to go and search about Professor Doman. You have to spend another half an hour to see his accolades and what he has done to inspire yourself. And over to you, Professor Doman. You can start sharing the screen, please.
Yes, it is possible to share the screen.
Yes, Professor.
Yes, Professor.
Now, I think it just a minute.
And I'll also take opportunity to welcome Dr. John Thiruvedigal. Good morning, sir.
Thank you, sir. Thank you for your presence. Thank you, sir.
Is it okay now to share the screen?
Can you please put it in the full screen?
Yes.
Brilliant, sir. Thank you.
Yeah, nice.
Okay. Thank you very much for your kind introduction. And the title of my talk today is Development of Photocatalyst and Solar Hydrogen Production System for Large-Scale Application. Here I show the content of my talk. After a brief introduction about water splitting reaction, at first I'd like to discuss about a particulate photocatalyst for water splitting reaction using these two examples. Then I move to the photocatalyst sheets and water splitting panels, again using these two examples. And at the end of my talk, I'd like to introduce our recent attempts concerning the construction of a prototype solar hydrogen production system. At first introduction, our target reaction is very simple. We like to split pure water into hydrogen and oxygen using solar energy on heterogeneous photocatalyst. Of course, the motivation is as follows. If hydrogen is produced from solar energy and pure water, it can be clean and sustainable energy carrier as well as chemical resource. However, from the viewpoint of technology, the situation seems to be more serious because we need to produce solar fuels on a large scale at a low cost in the near future. Actually, we are developing various kinds of different types of photocatalytic materials and applying mainly into two different ways. The first one is a particulate photocatalyst, as shown here, so-called photocatalytic water splitting reaction. And another one is application to the photoelectrochemical water splitting reaction, like this one. Actually, in the case, if we like to improve the efficiency, the photoelectrochemical method is easier to increase the efficiency in a laboratory scale. However, if we consider the large-scale application, this type of application has some difficulty to apply to the wide area. So recently, we are interested in application of the photocatalytic materials like these ones. So today, I'd like to focus our attention on the photocatalytic water splitting reaction, then photocatalyst sheet, and water splitting panel. At first, let me discuss about this system. This is a one-step overall water splitting reaction. This is the simplest way to split water into hydrogen and oxygen. But probably this is the most difficult way to split water into hydrogen and oxygen. Here I show the basic principles of this type of water splitting reaction. And this is a normal hydrogen electrode, so that of course that the proton hydrogen redox potential locates at 0 volt, and water oxidation potential exists at plus 1.23 volt. This is the band gap position of the particulate photocatalyst referring to this axis. Under photoirradiation, electrons in the conduction valence band are excited in the conduction band. Then the conduction band minimum locates more negative than this proton hydrogen redox potential. These photoexcited electrons are thermodynamically possible to reduce protons into hydrogen molecules. But in this case, I showed a so-called co-catalyst to facilitate the electrons transfer to protons and to generate hydrogen molecules, as far as we use N-type semiconducting photocatalyst. On the other hand, the valence band maximum locate more positive than this water oxidation potential. Again, these photoexcited holes are thermodynamically possible to oxidize water molecules into O2 molecules. In this case, I don't show any co-catalyst. Actually, in many cases, the surface of the photocatalyst itself works as O2 evolution site. However, of course, in some cases, it is more efficient to introduce a co-catalyst for O2 evolution. Today, I will discuss on both cases. Now, let me move to the next part, particulate photocatalyst for water splitting reaction. At first, metal-doped strontium titanate. As you know well, that strontium titanate is a white-colored powder, and the absorption edge is located at about 380 nanometers. So this material absorbs only UV light, that's a small portion of the sunlight. But the band gap position of this material is suitable to split water into hydrogen and oxygen. As you know well, this material has a so-called perovskite type structure, and A site cation is strontium 2+, and B site cation is titanium 4+. But as you know well, that both A and B site cations are very easily replaced by various kinds of other cations. Now let me show that some example for this type of replaced materials. In this case, we prepared our materials by a conventional solid-state reaction method, calcination in air. And this, pardon? Pardon, can you hear me?
Yes, Professor. Please continue, sir.
Okay, the bottom one is a stoichiometric strontium titanate and gallium 5% doped one, lanthanum 5%, both gallium and lanthanum 5% doped samples. In all cases, as you see, that we observe only single phase of perovskite type structure. And these are the SEM image of these samples. This is a stoichiometric one. This is gallium 5%, lanthanum 5%, gallium and lanthanum 5% doped samples. Judging from the SEM images, we cannot distinguish to each other. However, when we examine the overall water splitting reaction by introducing the co-catalyst for hydrogen evolution. Rhodium chromium mixed oxide is a very good co-catalyst for hydrogen evolution. Then we examine the activity of overall water splitting reaction. Here I show that the activity when we use pristine stoichiometric strontium titanate. This is hydrogen evolution and this is oxygen evolution. But then, so this is the reference activity. Then we replace B-side titanium 4+ cations by lower valent gallium 3+ cations. As you see here, activity was enhanced very much. On the other hand, if we replace A-side strontium 2+ cations by lanthanum 3+ cations, the activity was decreased very much like this one. The similar tendency was observed using different combinations. In this particular case, we use a sodium 1+ for A site and tantalum 5+ for B site. This is again the reference activity. Then when we replace A site strontium 2+ by lower valent sodium 1+, activity was enhanced like this one. On the other hand, when we replace the B site titanium 4+ by higher valent tantalum 5+, activity was decreased like this one. This kind of tendency can be generalized as like this one. Doping of lower valent cations, for example, A site strontium 2+ by sodium 1+, and B site titanium 4+ by gallium 3+, we can get higher activity for overall water splitting reaction. On the other hand, doping of higher valent cations, for example, A site strontium 2+ by higher valent lanthanum 3+, B-side titanium 4 plus by tantalum 5 plus, the activity of photocatalytic reaction becomes lower. So actually, the doping of a lower valent cations tends to increase the oxygen vacancy or decrease the titanium 3 plus species if exist in our strontium titanate materials. But to discuss the essential point of this type of behavior is a little bit complicated. So I do not get into detail today, but let me just tell you that although this lower valent cation doping is a so-called P-type doping, but our material, strontium titanate, still shows N-type character. Now let me move to the more concrete examples, aluminum-doped strontium titanate. In this case, this aluminum 3 plus replaces the B-side titanium 4 plus. So this is a lower valent cation doping. So we can expect that activity would be enhanced. In addition to the solid-state reaction, in this particular case, we also used a so-called flux method. Here I show the preparation procedure of a flux method. At first, we purchase a stoichiometric strontium titanate from Waco company. Then we add much larger amount of strontium chloride, then mix these two materials in an aluminum crucible, then calcine in air at 1423 Kelvin for 10 hours. By this treatment, actually, aluminum in this crucible dissolves to some extent to our strontium titanate. So we call this type of materials as a aluminum-doped strontium titanate prepared by flux method. And here I compare that some activity, and this is actually shows that strontium titanate modified by hydrogen evolution co-catalyst, rhodium chromium mixed oxide prepared by solid-state reaction. Although in this scale, the activity seems to be almost negligible. However, as I showed previously, this photocatalyst also evolves hydrogen and oxygen in 2:1 ratio. Then we doped aluminum by solid-state reaction. As I showed previously, in this case, again, the activity was enhanced like this one. However, when we apply the flux method, the enhancement is much better. And in this particular case, the apparent quantum yield at 365 nanometer was already 30%. This is considerably good quantum yield at this wavelength for overall water splitting reaction. Then we further modified our flux method. I mean that we intentionally added small amount of alumina into this strontium chloride. But I should say that this alumina didn't work as a dopant, but this alumina worked as a shape controlling reagent of strontium titanate. Let me show the evidence for that. Okay, left-hand side figure shows strontium titanate prepared by only strontium chloride as a flux. This is 5 micrometer scale, and then as you see here, but we obtained a considerably large particle size, and the particle size is not really homogeneous. And the amount of doped aluminum is 0.3%. On the other hand, if we add a very small amount of alumina in this flux, then we obtained much smaller particles like this one. And the amount of doped alumina was only 0.1%. That's why that we believe that this added alumina worked as a shape controlling reagent. Then we used this small particle size of alumina, and in this case, the apparent quantum yield was already exceed 50%. So this is a very good quantum yield for overall water splitting reaction at this wavelength. But so far, I have just focused our attention onto the improvement of the photocatalytic property of strontium titanate itself. Now I would like to discuss about the improvement of the co-catalyst. So far, we use only the hydrogen evolution co-catalyst. Then we added the oxygen evolution co-catalyst, molybdenum oxide. The loading amount in this particular case was only 0.01 weight%. But as you see here, the apparent quantum yield was already increased to very close to 70%. This is very good quantum yield for overall water splitting reaction in this wavelength region. However, more recently, we realized that when we switched the oxygen evolution co-catalyst from molybdenum oxide to cobalt oxide, more precisely cobalt hydroxide, and then all the component of the co-catalyst, metallic component of the co-catalyst, I mean that the cobalt, rhodium, and strontium were photodeposited, the apparent quantum yield was exceeded 90%. This is extremely high quantum yield for overall water splitting reaction. So I like to discuss a little bit more about this photocatalyst. Okay, this is the data that I showed in the previous slide using a bright line over high pressure mercury lamp. And actually we evaluated apparent quantum yields at different wavelengths using a xenon lamp and bandpass filters. And in these cases, in these wavelengths region, the apparent quantum yield was almost 95%. Actually, we evaluate our apparent quantum yield based on the total photon number which was introduced into our reactor. That means that some portion of the introduced photons are scattered out without being absorbed by our photocatalyst. So from such results, we consider that in this region, at least the internal quantum yield, I mean that if we evaluate the quantum yield based on the absolute number of photons, which is really absorbed by our photocatalyst, is very close to 100%. So I would like to say that it is now possible to split pure water into hydrogen and oxygen using particulate photocatalyst with a quantum efficiency of almost unity. Now, let me discuss a little more in detail of the preparation procedure. As I said, that all the core catalysts were photodeposited in an aqueous solution. And at first, we constructed the hydrogen evolution core catalyst, that is a rhodium-chromium core shell structure. At first, we constructed the rhodium metal nanoparticles by using photoexcited electrons to reduce rhodium-3+. Then we covered this metallic rhodium nanoparticles with a chromium 3+ oxide, that is mainly chromium hydroxide. Again, in this case, we use photoexcited electrons to reduce chromium 6+. Then by this treatment, we can construct a hydrogen evolution site with a core shell structure. But in any case, in this, we used, in these procedures, we use photoexcited electrons. So this is a so-called photoreduction procedure. Then we construct the Oz evolution co-catalyst, that is the cobalt oxide, more precisely cobalt hydroxide. In this case, we use photoexcited holes to oxidize cobalt 2+ into cobalt 3+. So in this case, we use a so-called photo-oxidation method. But during this procedure, I showed here that SEM image changes of our photocatalyst. This is the original unloaded photocatalyst. And after rhodium photodeposition by photoreduction method, as you see here on some facet, there exists a small nanoparticles. Even after coating with chromium, as you see here, these small particles are only distributed to some limited facet. However, when we added the cobalt oxide by photooxidation method, almost all surfaces actually have some particles. That means that cobalt particles were distributed on a different facet. This is more precisely examined result by high resolution STEM image. This is one particle of this photocatalyst, and this is the electron diffraction pattern from this part. And then we can determine that this facet is 110, and these facets are the family of 110 facets. And these are a little bit curved facets. This is difficult to precisely identify the faces, but roughly speaking, this curved facet is 110 direction. That means that photoexcited electrons are mainly flow to the 100 facet, and the photoexcited holes are mainly flow to 110 direction. So that electrons and holes are transported to different facets with almost 100% efficiency. Then the question is that, what is the driving force of this type of behavior? So at present, it is not possible to measure the internal electric field of our photocatalyst particles. So we carried out simplified two-dimensional simulations. And this is our model. And this is 100, this is 110 facet, and this is X prime, This is Y prime axis. And we assume that 100 and 1100 facet work function difference is 0.2 eV. That seems to be reasonable from the literature. Then we evaluated the internal electric field. This is the electric field along with X prime. This is the electric field along with the Y prime axis. And we evaluated the difference of the electrons and the holes density at these faces like this one. I don't get into detail of these numbers, but from this simulation, almost 100% of separation of electrons and holes are possible. So that this kind of internal electric field is the origin of the very efficient carrier separation. Now let me move to the next materials, yttrium titanium oxysulfide. This material has a so-called layered perovskite structure, and this red ball indicates a sulfur. This is a photograph of this materials. That is a dark brown colored powder materials, and the absorption edge is extended to about 640 nanometers. And actually, we prepare these materials in a vacuum evacuated quartz tube at high temperature, 800 degrees C, for a long period, so that the particle size becomes very big. This is 20 micrometer scale, so the particle size is 5 to 10 micrometer. That means that it is not really suitable to apply for as a photocatalyst. However, if we took the electron diffraction pattern from several points, as you see here, this particle seems to be almost single crystalline particles. However, when we examined more detail by high resolution stems, for example, this is a cross-section of one particle, and we observe this kind of holes inside of the particle. And we very often observe this kind of holes, and this white colored part is actually the defect, delocation. That means that our material has still very poor property. However, when we modify again that our photocatalytic materials by a hydrogen evolution, rhodium chromium quartz structure, also in this particular case, we use iridium oxide for auto-evolution co-catalyst. And as you see here, under visible light irradiation, both hydrogen and oxygen evolution takes place exactly in 2:1 ratio. But as you see here, when we continue the reaction for 20 hours, the activity will decrease to about 80%. This is not really due to the degradation of the oxysulfide photocatalyst itself, but some iridium oxide auto-evolution co-catalyst seems to be detached because we just attached adsorbed on the our photocatalyst this iridium oxide small particles. And another problem of this system is this one. Apparent quantum yield is at 420 nanometer is still about 0.36%. So we are now focusing our effort to improve the property of our oxysulfide materials and also to improve the preparation procedure of the co-catalyst. So far, I introduced two different types of photocatalysts, particulate photocatalysts, but we like to apply this type of particulate photocatalyst to a large area like this one. So to apply to this kind of large area, there are several methods. And today, I'd like to discuss about water splitting panel. That is more or less similar to the photovoltaics panel, like this one. Then to construct this kind of a water splitting panel, we need to fix this particulate type photocatalyst in 2 dimensions. We call such a kind of system as a photocatalyst sheet. So now let me move to the next part, photocatalyst sheet and water splitting panel. At first, let me introduce the photocatalyst sheet using 2 different types of materials, photocatalysts. That means that we use this type of 2-step overall water splitting reaction, or so-called Z-scheme type water splitting reaction. And the system that I introduced today is not our original system, but it was originally reported by Professor Kudo of Tokyo University of Science. And they used bismuth vanadate for auto-evolution photocatalyst, and they used a low limit of strontium titanate modified by ruthenium for hydrogen evolution photocatalyst. And these 2 photocatalysts were actually combined by iron 2+, 3+ redox shuttle. They actually put all these components together into the aqueous acid solution to make a suspended system. And they need to use acid solution because the iron 2 plus, iron 3 plus will be precipitated at a higher pH region. Then after optimizing the reaction condition, they obtain this kind of activity and solar simulator irradiation. As you see here, both hydrogen and oxygen evolution takes place exactly in 2:1 ratio, in this particular case for 150 hours with almost a steady activity. And the apparent quantum yield was 4.2% at 420 nanometers. This is actually the a typical value for the suspended system. Then we use these two materials for the our photocatalyst sheet. In this case, we modified a little bit more. We used a lanthanum rhodium core-doped strontium titanate for hydrogen evolution and molybdenum-doped bismuth vanadate for O2 evolution. All the colors are different, but the absorption edge of both materials are located at about 520 nanometers. Here I show that the preparation procedure of our photocatalyst sheet. At first, we mix these two types of photocatalyst in an isopropanol solution, then just drop cast on a glass plate to make these kind of mixed particle layers. The thickness of this layer is at most about a few tenths micrometers, very thin layer. Then we deposit a conducting layer, in this particular case, gold or carbon. And after annealing at a suitable temperature, we put another glass plate on top of that. In this case, this glass plate has a double-sided carbon scotch tape. Then after pushing, then peeling off, we can get this kind of structure. Then after removing the physically adsorbed particles by ultrasonication, we can get this kind of photocatalyst sheet prepared on a glass plate. In this case, the size was 3 centimeter times 3 centimeter. And this is the SEM image of our photocatalyst sheet. As you see here, this is the top view, and you understand that our the structure of our photocatalyst sheet is not really good order. And this red dot indicates the molybdenum-doped bismuth vanadate for O2 evolution. This green dot indicates the lanthanum rhodium core-doped strontium titanate for hydrogen evolution. And in this particular case, we use a gold as a contact layer. So this is the whole structure of our photocatalyst sheet. Then we put this photocatalyst sheet in a distilled water without any electrolyte and then irradiate just by a solar simulator. As you see here, both hydrogen and oxygen evolution evolves steadily, exactly in 2:1 ratio in this particular case for 10 hours. Another interesting feature is this one. When we change the reaction temperature, the activity changes very much. So we examine the effect of the reaction temperature. As you see here, when we increase the reaction temperature, both hydrogen and oxygen evolution activity was increased. This is the Arrhenius plot of this data. And from this data, we can estimate that the activation barrier of water splitting reaction on this photocatalyst sheet was 18 kilojoules per mole. And the quantum yield at 422 nanometer was about 33%. This is much better than the suspended system. And also the solar to hydrogen energy conversion efficiency was about 1.2%. I'll be back this value later, but let me just show you one typical experiment using videos. In this case, we use a carbon as a contact layer and the solar simulator irradiation. This is bubbles of hydrogen and oxygen evolving under almost atmospheric pressure in 2:1 ratio, like this one. Okay, in addition to that, we are also examining a little different, a little different preparation procedure. This is a work of a Toto company. They are also our collaborator in our project, and they use a so-called screen printing method, and they can prepare about 30 centimeter squares photocatalyst sheet very easily. And as you see here, and the similar reaction condition, both hydrogen and oxygen evolution takes place in 2:1 ratio. But in this case, that the solar to hydrogen conversion efficiency was about 0.4%. So there still remained to improve the activity. So they are now working to improve this type of photocatalyst sheet activity. Okay, now let me move to the different types of photocatalysis. Aluminum doped strontium titanate. This is exactly the same with this type of photocatalyst. However, in this case, we have to prepare a large amount of strontium titanate photocatalyst. So we just use a so-called impregnation method instead of the photo deposition method. The preparation procedure is very simple. Just mix our photocatalyst and also nano-sized silica particles and on a glass plate, and then dried up at about 6 degrees C. Then here we have a photocatalyst sheet prepared on a glass plate, and this is just distilled water in a 500 milliliter of beaker. Then if we put this beaker under the sunlight outside or irradiated by AMS 1.5G solar simulator, you will get this kind of bubbles coming out. This is the bubbles of hydrogen and oxygen exactly in 2:1 ratio, which was decomposed by using UV light included in sunlight. And in this particular case, solar to hydrogen energy conversion efficiency was about 0.56%. So this method is very simple. So we started to construct our water splitting panel. In this case, the panel size is 25 centimeter times 25 centimeter. And sorry. We used a 0.4 gram of photocatalyst and 0.9 gram of nanosilica by spray coating. And this is a side view of this our water splitting panel. Here we have a photocatalyst, and this is a gas outlet, and this is water inlet. And one of the characteristics of this water splitting panel is this one. The thickness of water layer is only 100 micrometer, 0.1 millimeter. Here I show a typical experiment using this water splitting panel and UV LED irradiation at 365 nanometer. I hope you can see that the small bubble is coming up and then goes very rapidly through this gas outlet. And actually the activity of this water splitting panel is exactly the same when we have millimeter thickness or 100 centimeter thickness of water layer. That means that 100 micrometer thickness of water is enough to split water efficiently. Then let me move to the last part, construction of prototype solar hydrogen production system. Actually, okay, here I show that the schematic structure of our water splitting system. Actually, we have a water splitting panel here, then evolved gas is collected and then carried to gas separation unit. Here we have a gas separation membrane with hydrogen and oxygen. Okay, at first we construct this kind of 3 square meter scale of water splitting panel outside, and in this case we use 48 water splitting panels. And this is a bubbles for hydrogen and oxygen, which is evolving from this water splitting panel. That is about 200 milliliter per minute of hydrogen and oxygen mixture. And STH was about 0.78%. This is almost a summertime, like this on September 7th. And then we extended our system to 100 square meter. And it is located at Kakioka Research Facility of University of Tokyo. And on a small hill, there is a flat place like this one. And then we extended our water splitting panels like this one. So from this one, this is a 3 square millimeter module. And we constructed 33 modules. And here we have 1 square meter. So totally 100 square meter. In addition to that, here we have a gas separation unit. It's a very small module. And this is bubbles of hydrogen and oxygen and from this water splitting panels. And in this particular case, the gas evolution rate was about 3.6 to 3.7 liter per minute. This is before the introduction to our gas separation membrane. Here I show that our gas, one of the examples of our gas separation membrane. We are now preparing different types of gas separation membrane. This is actually that polyimide hollow fiber membrane. actually it is possible to purchase from Uber industry that because that this system is not really designed for hydrogen separation, but they are actually designed for the compressed air dehumidification. But this polyimide membrane can separate hydrogen and oxygen. And here I show the example of such a kind of separation. This black line shows the one day, October 2nd, one day total accumulated amount of evolved gases. And this blue line shows filtrated gases. And here the hydrogen content purity is about 96%. And here the hydrogen content is about 92 to 93%. Here is 95%. So from these values, we can evaluate it. Hydrogen recovery was about 73%. And then, as you know, that explosion region of the content of hydrogen is in this region. So we have to make a pure hydrogen more than this purity. But some parts that it is still inside of the explosion region. But of course, as I said, that we use a commercial membrane so that if we improve the property of the membrane, we believe that it is easy to get into this region. And the recovery, hydrogen recovery ratio will become much better. Okay, so we constructed 100 square meters system, light receiving area, and the STH in the summertime was about 0.8%. And actually, we carried out this kind of experiment for 1.5 years, but we didn't observe any spontaneous explosion to damage our system. So it is very unlikely to cause such a kind of explosion. However, of course, we need to verify the safety total system operation. So we are now carrying out the intentional explosion at various points, including this gas separation unit. And we have found that so far, that any explosion cause any damage for our solar hydrogen production system. Okay, now let's summarize my talk. We are developing various types of photocatalysts, and for one-step water splitting photocatalyst, here I show several examples as shown here. And we are also developing two-step so-called Z-scheme water splitting systems. Here I show several combinations of those materials. Today I discuss these three materials. And at present, we are focusing our efforts to develop more efficient and stable photocatalyst sheet and water splitting panels. In addition to that, of course, we like to develop a safety total solar hydrogen production system. Here I show the image of the future practical systems. And we like to increase the area of the unit area to 100 meter times 100 meter, 1 hectare. And we like to improve the STH to 3 to 5% to make a practical point, and one hydrogen separation system like this one. The question is that, is it possible to achieve these numbers? Okay, here I show that photocatalysts that we have been developed. All of these photocatalysts are possible to split water into hydrogen and oxygen. And this red point shows this scheme water splitting system. This axis is apparent quantum yield in a logarithmic scale, and this axis shows the absorption edge. And today I discuss in detail about the strontium titanate, but to achieve the 3 to 5 or more STH, we need to use these types of materials. I mean that absorption edge is around 600 nanometer or even longer. But as you see here, the apparent quantum yield of these photocatalysts is now low. So for example, to achieve 3% STH, we need to achieve about 20% AQY. And to achieve 5%, we need about 30%. And if we like to achieve 10%, we need to improve the AQY to more than 50%. But important point is that we have already found that several materials which can reach to these values. The question is it possible to achieve these numbers? So let me show one simple calculation. The band gap energy of this material is 1.93 eV. So, and we need 1.23 eV to thermodynamically split water into hydrogen and oxygen. Therefore, that 0.3 eV or 68 kilojoules per mole. This is the excess energy we can use for driving force to improve the AQY or the rate of water splitting reaction. And we consider that it would be possible to achieve these numbers in the near future using this type of photocatalyst. Now, this is an acknowledgement. Professor Kudo of Tokyo University of Science and Professor Sakata, Yamaguchi University, they are our colleague for a long period. Here I show some name of my colleagues, and they contributed to our system and to my presentation today. And especially I'd like to thank to Dr. Wan Chen. She developed oxysulfide photocatalyst and also this scheme type photocatalyst sheet. And Dr. Takata, he developed extremely high quantum efficiency strontium titanate photocatalyst. And Professor Dr. Nishiyama and Dr. Yamada, they are in charge of the construction for the large-scale solar hydrogen production system. And this is a financial support from our government, and that is called ARPChem project, supported by NEDO. That is a funding agency of METI, Ministry of Economy, Trade and Industry. This project is a 10-year project, so we have 1 year to go. And after this project, we'll move to the second phase of this project. In that project, we plan to construct a practical system using a higher efficiency photocatalyst and larger area to split water. Thank you very much for your kind attention.
Yep. Yeah, thank you very much, Professor Izuri Doman. And I think there are more than 200 participants are there who are benefited by your talk, and it's a fantastic cutting edge research you have been throwing to us. And it's really overwhelming that amount of hydrogen production is happening with strontium titanate and also bismuth vanadate as well. There are about, like, I think thanks for making your talk exactly on time. I think we have another 5 more minutes for quick questions. So I have 3 questions on the panel, and would you be happy to take 3 questions, Professor?
Yeah.
Yeah. So one is Christian Pelecano. Good afternoon, Domen Sensei. The rhodium and other materials currently used are most expensive noble metal among platinum groups. Do you have any alternative HER co-catalysts in mind or developing? Thank you very much.
Of course, if possible, we like to switch rhodium into the other element. Now we know that we can switch to platinum or ruthenium, but they are also precious metals. But our colleague working together in our project, they say that as far as we use those materials as co-catalysts, the cost of the co-catalyst is not really the major part. Less than 10% of the total solar hydrogen production system. So that they now allow to use such a kind of element in our photocatalyst as a co-catalyst. If we use those materials as a major component, it is not be allowed, I believe. Yes. Is this okay?
Yeah, that's fine. That's fine, Professor. I have another question, it's from Peter. To large-scale production of PEC method facing difficulty. So I want to know the bit more details of how we can produce a large-scale PEC facility.
Oh, can you see my slide now?
Oh, yeah.
You can see that one? This
yet.
is okay. So I actually that we are also working on this type of photoelectrochemical system, but to get a better efficiency. However, please consider that if we extend this kind of system to, for example, 1 square kilometers, it is very difficult for us to devise a good idea. Actually, we extended to about 15 centimeter times 15 centimeter, but beyond that scale, it's very difficult to extend to wide area. instead, this system is very, very easily without any loss of the efficiency. So that's why that we are now trying to improve the efficiency of this type of system. Is it okay?
Yeah, that's okay. Thank you, Professor. And one quick last question from me, actually. So you have been working on strontium titanate and others, particularly on fixed ratio stoichiometries. And what about the defects that are induced in the samples and in the titanium and also on oxygen? Will there be any vacancies which will cause reduction in recombinations?
Yeah, as far as you have some defects, they very easily work as a recombination sites. That means that it will lose efficiency. So I believe that at least in the bulk, that we should have almost perfect crystal structure. But on the surface, it will be possible to introduce some co-catalyst or some other element to block such a kind of defect sites. And in some cases, defect sites seems to work a good site to dissociate or adsorb reactant molecules. But in the case of photocatalysts, I don't really think that such a kind of defect would be very suitable to be introduced to get a good efficiency. Is it okay?
Yeah, that's fine. That's fine. Okay. Okay, Professor, I think we are exactly on time. And
can I ask one question, sir, Professor Sadish, sir?
Yeah, Professor Napoleon. Yeah.
Yes, sir. Thank you for giving wonderful talk, sir. Just I have only one question. Have you used any sacrificial reagent? Like
okay, when we developed our photocatalyst, we use some sacrificial reagent for hydrogen and oxygen evolution. But today I showed only the system that without any sacrificial reagent. So in all systems, both hydrogen and oxygen evolves exactly in 2-to-1 ratio. That is really the photon energy conversion into hydrogen.
Okay, so why did not use a sacrificial reagent here?
Oh, if we use a sacrificial reagent, that will not be the energy conversion, solar energy conversion. To achieve the energy conversion, we need to split pure water into hydrogen and oxygen.
Yes, sir, but there is a 1/3 contribution comes from the sacrificial reagent. That's what we observed. Sometimes they are also contributing 3/4 of the reaction. That's why some other times there is no reaction in the absence of sacrificial reagent. That's what I wonder. Do you have any answer? What is the role of the that sacrificial reagent for the hydrogen production?
Oh, okay. If I catch your point correctly, I should say that if you use a sacrificial reagent, it is much easier to observe hydrogen evolution or oxygen evolution. So we can check that that has a potential to evolve hydrogen or oxygen, but it is not just a necessary condition. So it is not really a sufficient condition to split water into hydrogen and oxygen in 2-to-1 ratio. So you should be careful. If you use sacrificial reagent, it will not become an energy conversion reaction, but delta G change will be minus. Okay.
Thank you, Professor. Thank you for
Professor Napoleon, can you please introduce yourself so that he knows who you are talking?
Yes, I am Professor Napoleon. So I did my PhD at University Chennai. I worked with Professor Anpo, Osaka Prefecture University from 2002 to 2004 as a JSPS fellow, and also Professor Hiromi Yamashita. Now he's a professor in Osaka University.
Yes.
So where I have seen Professor Anpo always used to work on water splitting with a platinum-based TA with a catalyst, but they could not achieve for the STH, as you rightly mentioned. The STH is a big problem. Here also we are working same thing. But without any sacrificial reagent, we could not attain any STH. But it is interesting to know that what you have shown is more than 3.5 STH without any sacrificial reagent. That's what I wonder, if you use those material like lactic acid, methanol, ethanol, you can increase the STH more than 10. So that's why we are also working in that area. So I'm also working in splitting, water splitting for this hydrogen. So last 10 years in addition to sonochemical reaction. So I'm very happy to see you here. Thank you so much for giving a clear lecture for our conference. Thank you so much.
Thank you, and I will leave now the stage to Professor.
I don't want to take much time, so it's
no problem. Thank you, Professor Napoleon, and thank you very much for all the attendees in this. I think more than 200 attendees benefited, and excellent talk, Professor Kazuri Doman. In spite of all your busy schedule, you came here and delivered a fantastic talk, and thank you very much. And we'll give a good hands, virtual hands for always there for you. And
okay, thank you very much.
I will leave Professor Karthikeyan to wrap up the session. Thank you.
Thank you.
Thank you, Professor.
Yeah.
Thank you, Professor.
Thank you. On behalf of ICON Conference Committee, I thank Professor Vajinori Doman for the interesting presentation, and the chair, Professor Satish Krishnamurthy, for making the session interesting, and all the participants. Thank you very much for sharing your valuable time. Thank you, sir.
Thank you very much.
Now, thank you. Dear participants, it is time for the message by our associates and the collaborators for a long time with SRM Institute of Science and Technology. Now I invite Professor Corrado Di Natale, University of Rome, Tor Vergata, Rome, Italy.
Thank you very much. Do you hear me? Thank you.
Yeah. Welcome.
It's very nice. It's very nice to meet you, even in this virtual modality. And I've been at ICON in 19, so it's my pleasure. It's my pleasure to be here today, and it is my pleasure to greet all the participants to this conference. In particular, this conference is very important this year when we are facing this big global problem, and all the social contacts among people being broken. So we are just isolated in our labs, and this is not how science works. So it's very important. Then scientific conferences in particular are of big importance to bring people together, to foster discussions, to compare ideas. These are the vital elements of science, and we are missing this in this year. And so just for this reason, I'm very gratitude. My deepest gratitude to the organizers of ICON, because in this year they keep alive the conference, they keep alive the spirit of conference. This is a service for the community, and just with this spirit, I welcome everybody, all of you, to this conference, and I wish a fruitful days. And I think that the most important thing is just to be in contact. This is how science works. We are not isolated. We are not, let's say, hermits, but we live together. We live together in labs, and we need to exchange our ideas, our results, what we do, our way of thinking also together. And this, I have a very good memory of the previous conference, and I hope that this will be again. In the meantime, thank you for what you did for keeping alive this conference and give us the opportunity to join together. My pleasure.
Thank you, Professor, for the warmest greetings. We are really grateful. Thank you. Now I have another message from our associate, Professor Edward Hoi Chang, National Chao Tung University, Taiwan.
Hello, this is Edward E. Chang. I'm the Senior Vice President of National Chao Tung University in Taiwan. I have been to ICON conference for 3 times since the conference started 6 years ago. And through this conference, I have given talks and have feedback from the audience. And through this feedback, I have a lot of interactions with the universities in India, especially for SRM. So that means we have several joint programs and quite a few SRM students come and join NCTU. NCTU is the top semiconductor university in Taiwan, and we have been working with India for some time, and SRM is one of our primary alliance for this kind of semiconductor technology. So here, I hope that the conference this year will be successful, and SIM will continue to host this kind of conference and be an important university for India for this kind of solid-state technology. We will do our best to support this program, and we are willing to host your professors and students to come to Taiwan and to work together for the new technology in the future. Thank you very much.
Thank you, Professor. Thank you for giving your valuable time for the warmest greetings. Thank you very much. Thank you, participants. Now it is time for a break, and we will assemble here for the keynote talk at 1:45 p.m. Indian Standard Time. We have 15 minutes break. Thank you all. Please stay with us. Thank you. For participants, we have announcement. We will be starting again after the break, a keynote lecture 12 at 1:45 p.m. Please stay with us. And we have an important, very interesting lectures will be following. Keynote lecture 12, large size nanoelectronics for the Internet of Everything by Professor Edward White, by Professor Thomas Anthopoulos, Saudi Arabia. Followed by, we have keynote lecture 13, nanostructured thermoelectric energy conversion by Professor Kanishka Bisbas, Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, India. So we have these interesting lectures will be following from 1:45 p.m. You are requested to stay with the same link. Thank you all. Sorry, you have been made panelist. You discuss with the people. Yeah.
Hello. Yeah. Professor Muzumdar?
Yes, Dr. Away. Good afternoon.
Yeah. Good afternoon. Good afternoon, Thomas.
Good afternoon. How are you?
Yes. Nice to see you.
Nice to see you all.
Yeah.
Good afternoon, Professor Thomas. Sushil here. I'm chairing the session.
Great. Thank you. Very nice meeting you.
Pleasure.
So how is the conference going so far?
Yeah, it's well. We have like increasing participants every day.
Great.
Yeah.
Abhay, will you open the session?
So just I will introduce you and then we'll start it. And then you can take over.
Correct. Okay.
Yeah. So maybe another 2 minutes.
Another 2 minutes, you said? It's the 13:45 is the time. You want to have some early beginning, is it?
No, just to introduce you and then you introduce the speaker, which will be 2-3 minutes. Okay, we'll start at like 1:42.
Okay, sure.
Yeah.
Your choice. Thank you.
Yes. Right. So, Professor Muzumdar, shall we start?
Yes, sure.
Yes. Good afternoon, everybody, or whatever the time you is suitable for you. Welcome to this day 2 afternoon session. So in this session, we will have 2 keynote lectures, and this session will be chaired by Professor Sushil Muzumdar, who is a professor at TIFR Mumbai. So to introduce him, so he obtained his PhD in 2001 from RRI Bangalore, and then he gained 2-3 postdocs from Florence, Alberta University, Canada, and ETH Zurich, and then he joined TIFR in 2006. So his research interests are quantum optics, random lasing, near field scanning optical microscope, and classical and quantum optics of complex systems. So he has received several awards, P.K. Iyengar Award, Swarna Jayanti Fellowship, NASI Scopus Young Scientist, and Ramanujan Fellowship. So, Professor Muzamdar, I will hand over the session to you.
Thank you very much, Abhay, for your very kind introduction. And I will first thank the organizers of this fantastic conference for this great honor, allowing me to chair this session. The titles of the talks already tells us what a marvelous session this is setting out to be. Since we have a minute or two to go for the actual start time of the lecture, let me just briefly make a few comments to our esteemed invited speakers. So the talk time, I'm informed, is 45 minutes. And I'm advised to give a first bell at the 37th minute. I would rather not interrupt your presentation. What I'll do is I'll simply turn on my video. And from experience, it already acts as a bit of a distraction to let the speaker know that there are 3 to 4 minutes for wrap up, which will then leave 5 minutes for interactions. And if I have to give a hard reminder, I will do that roughly 4 to 5 minutes before the 45th minute, that is after 40 or 41 minutes. I presume that should work fine. And hello and welcome to all our attendees and panelists. The question answers, there are proper 5 minutes for the question answers. I would recommend you to do type in the chat box your question answers, and me and Abhay, we will pick them up at the end of the talk, depending on how much time we have. So with that, I will move on to do the honors, and it's my great honor to introduce to all of you Professor Thomas Anthopoulos, who is a professor at the Materials Science and Engineering, Physical Science and Engineering Division at the KAUST, which is the King Abdullah University of Science and Technology, Saudi Arabia. Professor Thomas obtained his PhD from Staffordshire University in 2003, after which he spent some time at the University of St. Andrews, UK, Phillips Research Labs in the Netherlands. He was a professor at the Imperial College London before shifting to KAUST. As is listed on your screen, Professor Thomas's interests cover device physics, large area electronics, materials engineering for solar applications, and he has worked as a Marie Curie postdoctoral fellow in Phillips Research Labs. He holds an EPSRC Advanced Fellowship and an ERC starting grant. He's got a substantial number of papers in Nature Publishing Group journals and advanced materials, and can boast of a staggering H index of 74. It's a great honor to be knowing you, Professor Thomas. Can I invite you to deliver your keynote talk, please?
Thank you very much for the very kind and very thorough introduction. So allow me to share my screen, and can you see my screen now?
Yes, Professor Thomas.
Yes.
Great. And great. So it is a true honor to have the chance of being here and have the opportunity to present in the ICONN 2021. Again, thank you very much for the organizers. Finally, managed to make it, even though remotely. Hopefully, in the future, we will have the chance of meeting in person with a lot of the organizers. And I'll tell you a little bit about the work we've been doing in the past 5 years or so in the area of large area nanoelectronics. And I will explain what this is all about. My group is doing a lot of diverse work, all the way from material development to applications in sensing, energy generation, and more recently, energy storage. But today, I would like to focus in this interesting topic, which is close to my heart and relates to how we can make large electronics small. Counterintuitive, but how we make large area electronics small. And what I mean by that is how can large area, for instance, printed electronics can take advantage of extreme downscaling. Can we do that? Essentially replicate the success of silicon electronics with within the area of large area electronics. And in order to explain better where I'm heading at with my research, I better look back in the past, which I strongly believe, knowing the past, we can better define the future direction of electronics. So this is very rudimentary history of electronics, starting with the tube rectifiers in 1904 to the invention of the first functional transistor, 1947, the integrated circuit, 1958, and to modern day electronics, the microprocessor, which is the culmination of these tremendous developments in the field of solid state electronics. We're now in a situation where essentially we have devices that if you can take them apart, you can count the silicon atoms from one side to the other. And this is just a cross-sectional TEM image of FinFET, the building block of the state-of-the-art microprocessor nowadays, with a 40 nanometer node. And I believe we're already now having products with 5 nanometers nodes. And these products, the state-of-the-art microprocessor, can often be found on mobile phones because they consume, of course, less power. But this is not the end. There will be still ways of getting them better. But how much better? How smaller can we go? Perhaps we can go a nanometer, but below that critical dimension, we start facing the physical laws of nature, limitations, for instance. So engineers and scientists trying to figure out what comes out after this down scaling of silicon electronics. What comes after the Moore's law? Will be more Moore or more than Moore? There are different approaches taken and different type of devices being developed to address exactly this big question that we are facing, and we haven't faced for over 50, 60 years now. So this is where essentially we are right now. This is a very interesting plot I took from the literature, where we see the evolution of critical electronic component development over the years. So with the most interesting one being this transistor per chip number, where we are essentially having approximately now several billions of transistors squeezed into a single chip of silicon. The clock speed, as you can see in this plot, has pretty much plateaued since the last 10, 15 years. The same for the power and the number of logical cores, which are increasing, of course, as an easy way of improving the functionality and value of what this microprocessor can do. What is also interesting is to note that the transistor that we can buy per dollar has actually started dropping. And the reason for that is as we're approaching this extreme dimensionality, making these transistors, it takes more sophisticated techniques, more expensive techniques, and as a result, we have to pay a little bit more per transistor. That's very interesting developments. But as already mentioned, is that there is clearly an end to this race of downscaling silicon microelectronics. What comes next? So every end comes with a new beginning, in my view, and it's very interesting because a lot of new opportunities are created for different fields of science and technology. So the question that arises is what comes next, and this is what's been happening the past 10, 20 years. We have seen the emergence of new forms of electronics, a new concept of electronics, few of which are summarized in these slides. For instance, in the year 2000 over, we've seen the emergence of larger area electronics in the form of big displays. One of these displays is in front of me, contains millions of transistors that are able to switch on and off these pixels that are used to build these displays. We see now more and more of these emerging forms of large area electronics penetrating our environment, our daily life, revolutionizing the machine-human interface, either through touch, speech, combination of software and hardware come together to provide solutions that we never imagined before. In the meantime, and more recently, the last 5 years, we also have seen new concepts being emerging. Quantum computers start getting there. I'm not sure whether we're ever going to have a quantum computer in our hands, definitely not in the near future, but definitely the quantum computers will come along, but probably most likely will be hidden somewhere in the cloud. We also have seen neuromorphic computing agents slowly making their entry into the marketplace, and we will see potentially neuromorphic computing engine being customized for certain type of functions. Again, providing solutions to where conventional electronics are either too complicated or too costly to be implemented. So this is, in my view, what we will see in the future. But the area of large area electronics, I believe, will be the one that will be dominating our daily life. We will see these new forms of electronics being seamlessly integrated with our environment, facilitating interaction with the machines and communication, and creating a lot of new opportunities. So what I expect to see, I would expect to see different forms of electronics being slowly making into the market, few of which are shown here: flexible electronics, super soft electronics, even transient electronics that can be implanted into a human body and slowly dissolve away when the function and performance been undertaken successfully, delivering either a monitoring task or a drug or a number of different functions that we can envision. Hopefully, what we are all hoping is that these electronics will be easier to make, have smaller carbon footprint, environmentally friendly, therefore. And this will be enabled because we will be shifting towards new manufacturing paradigms, creating new industries. And this is exactly the area where I believe we're trying to enable some of the new developments. But there is a lot of challenges, both economical challenges and technological challenges. We can't move to this direction if the economics don't work, or if the technology is not there yet. So what we've been trying to do in my group is trying to find ways of tackling the performance without compromising the cost benefits these large area electronics have to offer. But there is a problem. As we're shifting away from these high-end electronics that we have been mentioning, the silicon, which can deliver so much performance, to a larger form of electronics, we pay a huge penalty in terms of performance. These devices, large area electronics, for instance, cannot communicate with state-of-the-art silicon microelectronics. Always silicon is needed. So we're relying a lot on heterogeneous integration of technologies in order to enable a flexible sensor being communicating with the base station, which is ultimately has to be done by silicon. So in the future, we want to avoid that and create technologies that can be combined together, provide holistic type of solutions and products. So, and the question we were trying to answer in my group is whether we can actually combine the performance characteristics of what silicon electronics can deliver with the manufacturability of these new forms of larger area electronics, which can be potentially manufactured using additive scalable techniques. So the big question is that, could we, in the area of additive electronic manufacturing, could exploit the same benefit silicon has exploited by going aggressively and downscaling key device features? But how can we do that? How can we go from these very sophisticated silicon electronics and manufacturing techniques to additive manufacturing without compromising performance and economics? The answers are out there, but they're not simple. For instance, what techniques can we use that we can combine larger area patterning with extreme fidelity, the highest possible resolution? There are techniques out there that can deliver that, but usually once you have ticked the box of resolution, let's say you can make devices extremely small, you are compromising the scalability of that process. And this is captured in this diagram I have prepared here, which simply display the scale length scales in nature, starting from the atom size on the left, all the way to the living things, us, microscopic world we are actually living in. We know nature can use natural self-assembly to build us. It would be amazing if we could build in the future microprocessors or electronic circuits using the same self-assembly processes from bottom up. But so far we have been unable to do that, but slowly we're learning and we're developing techniques that could potentially deliver some solutions in the relatively near future. And here is exactly where the performance gap exists between state-of-the-art incumbent silicon electronics, which is essentially nanoelectronics in action. We're talking about devices featuring 5 nanometer size elements, and large area electronics, which offer the cost benefits in terms of manufacturing and potentially system level cost. So this gap exists, and the reason is very simple. Simply because we don't have a simple technique, a single technique, manufacturing technology that can span from macro to nanoscale dimensions. This all-scale manufacturing would definitely be an enabling factor in bringing things together. So what if we take a look at the existing technologies, we'll soon realize that photolithography, just conventional photolithography, can bring us from meter size down to a few microns, no problem there. And we are exactly what we're using today to manufacture optical displays and large area electronics. If we want to go sub-micron, then we have to rely on techniques like nanoimprint lithography, but of course that comes with added complications. I don't want to go into detail. We have E-beam, electron beam lithography, which can deliver nanometer resolution, but it's very slow and very difficult to scale up. And other techniques like scanning probe lithography, numerous others have been used. What we would like to do is not to rely on such sophisticated and area limited techniques, but instead combine the benefits of these techniques with large area patterning techniques like photolithography and printing. That's exactly what we are aiming. So my group has been developing kind of new approaches that we can either combine techniques and providing kind of new form of solutions that could deliver electronics with the performance that is required for future generation of large area electronics. And if we could do that, then there is a host of applications, a very wide range of applications that we could apply for. This includes existing applications, but also a lot of these emerging concepts in displays, electronics. I mentioned flexible, transparent electronics, ultra soft sensors or energy generating system for autonomous electronics or sensor nodes. We have seen medical applications where we essentially have this printed electronics being used for point of care diagnostic, all the ways to the emerging Internet of Things device ecosystem. It's very difficult to predict where IoT will go, but what we know for sure, as we are developing more and more devices, and new standards being adopted, this Internet of Things device ecosystem tends to converge. And one of the critical issues would be whatever technology you develop should be able to interface with the cloud. We should be able to intercommunicate with established electronics, conventional electronics that actually will be used to perform the computation behind all these information gathering devices that forms part of the Internet of Things. That's exactly where we are essentially trying to provide solutions, at least in my laboratory or part of the work we do. So what I would like to do now is to introduce a little bit of the work we've been doing on these new forms of patterning techniques, and specifically patterning techniques that allow us to make simple nanogap electrode arrays, and then using these nanogaps to create a number of functional devices. So over the past, I would say 8 years, we've been developing techniques called adhesion lithography. And the name comes from the fact that we're using adhesion forces. By modulating the adhesion forces on certain substrates and materials, we can essentially recreate some sort of a lift-off process we exploit in conventional lithography. And I will explain you how this simple technique works. In the simplest form, we start with a substrate. It can be glass or plastic, it can be actually any type of solid state substrate that is flat enough to pattern a metal on top of it. This metal can be patterned using conventional lithography or even additive manufacturing. There are a number of techniques that can be exploited. Then what we do, we use a self-assembled monolayer that is metallophilic in this instance and functionalizes, reacts only with the surface of metal one, and does not stick to the substrate. These sums essentially are a huge library of materials that can be used, and the chemical composition depends on the metal we want to attach it on. So typically we will have self-assembled monolayers, which will contain a tail, a spacer, an end group, which defines the surface energy of that surface, or that we are functionalizing it on, and the some head group, which is essentially an anchoring group, anchors to the specific metal we have chosen. So if we have, for example, aluminum, aluminum will tend to oxidize the moment you expose it to air, forming a native alumina. Then a phosphonic acid anchoring group can be used. This is very efficient of creating a very robust and dense SAM layer on top of aluminum. If it's gold, we can use a thiol-based chemistry to form these self-assembled monolayers. So you see there is a number of different technologies depending on the metal we have actually been using to form the metal one. Then what we do once we have a very dense self-assembled monolayer formed on the surface of metal one, we deposit a metal two. This metal two can be global, it doesn't really matter, or it can be patterned using conventional lithography or other additive manufacturing deposition techniques. And then at the top of metal two, we apply an adhesive tape, glue, the different type of adhesives we have been testing and actually proving that they work. And what then we do, we pull this glue once it solidifies, or the tape. And what we have discovered is that every overlapping metal two with metal one, because of the presence of the SAM, will be weakly bound to each other and will tend to delaminate very easily, while the metal two deposit on the surface of the substrate exhibits very strong adhesion forces and does not go anywhere. Instead, delaminates from the adhesive and stays on the surface. What we end up with, it's a metal one electrode with in very close proximity to a metal two, separated by a SAM. A SAM, the self-assembled monolayer, can easily be burned in a few seconds by exposing the structure, the wafer or the substrate into the oxygen plasma, for example. And this is pictures depicting the process I have described using those schematics, starting with metal one deposited and patterned on a substrate, a glass substrate in this case. Here, these metals contain the SAM as well, but the SAM is so thin you don't really see anything. Then we deposit the global metal two everywhere. Then we put the glue. In this case, we don't use an adhesive tape. We're using just the glue. Once the glue is dried, we can actually peel it off. And what you see here is that the metal two overlaps with metal one because of the presence of the SAM is easily removed, while all the other metal two remains on the substrate. We only overlap, we remove the overlaps between the two electrodes. The end result is, in this specific pattern that we have used just to demonstrate the technique, is we have coplanar electrodes of metal two, metal one, metal two, metal one, as shown and in this schematic here on the right. What we were not expecting to see is how close these two electrodes can be actually brought together. So this is a simple video describing those processes I've shown you in the picture. Where we are now, we are essentially applying the glue on top of the global metal 2 we have deposited on top of the SAM-treated metal 1. We let the glue dry, and then we go with a little tweezer, and we just peel that glue. And you see how easily that metal 2 that overlapped with metal 1 comes off. And the many different variations one can adopt to essentially implement this technique. This just few examples of we have been using from the old days just to fabricate these very, very high resolution nanogap devices. And what this adhesion lithography allowed us to do is to go also around corners, doesn't require straight electrodes. And this is one interesting way of demonstrating this idea. So what we have here, it's a aluminum electrode in the middle, surrounded by a global gold electrode. And all these features, the gold electrode from aluminum is separated by this tiny nanogap. It can be really resolved in this SEM image at the top here. It's because the nanogap is less than 20 nanometers. And this is a little bit more informative slide where I've shown you on the left here this kind of a skyline of London. We have created, we were creating light-emitting coplanar nano LEDs. And that's why we were creating these aluminum gold electrodes. The nanogap is tiny, and when we actually take this nanogap and use cross-sectional TEM, we see that the gap can be 10 nanometers, even less. But what we often see, what we typically see, is the nanometer is always less than 20 nanometers. And most of the times depends on the granularity of the metal electrodes we are using. essentially to the method we're using to deposit those two electrodes. That's very interesting and very telling about the techniques, how far it can go down in scale. So the smoother, the more amorphous, if you like, the metals can be made, the sharper that interface between the two metals becomes. And we can now scale up these devices. We can create interdigitated structures which retain the nanometer scale gap, but the width can be made very large. We made single wafers, 4-inch wafers, containing 1 nanogap, which is 200 nanometers long. Probably that is the highest aspect ratio nanogap ever created, just to demonstrate that this adhesion lithography can be scaled up. Most importantly, can be transferred to other material systems, both in terms of substrate, but also electrodes. Here we have nanogaps formed between aluminum and indium tin oxide, this transparent conductive electrode. So here the ITO is the global electrode, and aluminum is this disc-like electrodes shown, and they are separated from the ITO by this nanogap. And all these are made on PET polymeric substrates. More recently, we've been able to push the technology a bit more and simplify it even further. Nobody really wants to use glue or steps which are kind of unconventional for standard industry. So what we discover and we patent, it's a simplified process of removing these overlapping electrodes, metal 1 and metal 2. So we start with the substrate. Then we deposit the, let's say, aluminum electrode. We functionalize with a self-assembled monolayer. And then we deposit a titanium adhesion layer, what we using as a adhesion layer for the substrate, typically a glass or silicon dioxide, followed by a platinum. And what we discover is that when we make this titanium and platinum the right thickness, there is internal stress built up the moment those two electrodes are deposited on top of this some functionalized aluminum. So essentially, these two electrodes don't like to interact with that some functionalized aluminum surface at all. And at some point, what do we see? The deposit start buckling, fracturing, and rolling over, essentially creating these self-formed nanogaps, what we call self-forming nanogap. And this process is depicted in this image here, a little bit better schematic. We have the aluminum functionalized with the sum. Then we deposit the titanium platinum, and when the platinum electrode reaches a critical thickness, we start seeing the buckling, cracking on the side, and essentially creating a kind of a bend-like structure shown here. We call them nanocigars. The end result is that in this critical point here, we have the formation of a nanogap between the aluminum and titanium platinum composite electrode. And remember, what is the main parameter that differentiate many aspect or attribute that differentiate our technique from all other nano-patterning techniques is that we can deposit two different metals in nanometer proximity to each other. And why this is important? Simply because we can use one high work function with a low work function metal to create anode and cathodes, essentially creating many more functional devices than using symmetric metals like gold. E-beam is great, cutting small high resolution electrodes, but it's not able to actually pattern asymmetric electrodes. There are ways of doing it, but it's very complex putting two different metals next to each other. Our techniques provide a natural solution to this limitation other patterning techniques are facing. So this is how the electrodes are looking like when they're coming out of the chamber and you have deposited the critical thickness of the platinum. And when you clean this mess, which looks like that with an optical image, we end up with a clean wafer. So essentially what you see here, in this, if you zoom in, you see a nice array of nanogap electrodes being created. And what we need to do is just put it in a solvent, sonicate it, and essentially getting rid of all this buckled top platinum titanium electrode that has been created. So this is, if you took this image, this dirty looking like a wafer under a microscope and zoom in into these arrays, you will see all these nano features created. Essentially what this is the top electrode that has cracked from the other metal 2 electrode and created the nanogap with a buried metal 1 and the metal 2. And this is a perfectly nicely well-defined nano gap. And then what we need to do is to get rid of these residues by a cleaning process. And this is a video showing how easy it is. If we take this wafer, before this critical platinum thickness has been reached, then we are at the point where the wafer looks nice, but the moment we immerse it into a solvent and expose it to some mechanical agitation, we start inducing this spontaneous fracturing and crumbling of the top metal 2 electrodes. And essentially at the end, if you do that well, even by hand, you can see the formation of these metal 1, metal 2 nano gaps very nicely. So essentially we have avoided in this way to use the glue. And we call this a self-forming nano gap technology. But as already said, one important aspect of this adhesion lithography is that it does not require to be straight lines. It can take any shapes and you can perform the adhesion lithography step or the self-forming process step, and the second electrode will take very nicely the shapes around the electrodes. So what we have done here, we have used laser scribing to remove metal 1 from certain parts of the substrate and essentially create a structure like the one shown here on the right, and then deposit the metal 2. So forming essentially the nano gap between this metal 2 and metal 1. But because the device is actually pretty, the technology is pretty robust on the rough edges, it doesn't really matter. We still end up with a very tiny nano gaps, which can be shown in these images of AFM of a structure of a laser scribed nano gap structure shown here between a gold and aluminum. Even though the edge looks rough, the nano gaps remain tiny and typically less than 20 nanometers. So what do we do with all these structures? I have only a few minutes left. The reality is that we can use, and our imagination is the limit. We have so far used the technology to create radio frequency diodes, photodetectors, nano gap light emitting diodes, memory, self-aligned gate transistors, and many more. We even using nowadays these nano gaps to induce chemistry using electric field at the smart region. Because of the extremity of the electric field, we can apply across this tiny nano gap. But today I will show you a few examples, one of which, most important of which I think is the radio frequency diodes. Already mentioned the Internet of Things device ecosystem. And in most definition of this, you will find a diagram looking like that, where essentially we have devices and connectivity, data sensing nodes, essentially hardware that come together to acquire some information and then transmit this information to some sort of a base station where some analysis can be performed, if not possible to do it locally. But to do that, you need devices either for both to harvest some energy, so you can make these data sensing nodes autonomous, so we can deploy a sensor. You don't worry about the power that is going to be receiving, because you can harvest it from the ambient omnipresent RF, for example, signal, but also be able to communicate. And key elements to these tasks are diodes. Not the only ones, but they are very important. So what we've been trying to do in our group is to create diodes that can deliver the frequency performance. So essentially, even making them compatible with emerging standards of 5G frequency domain, and creating simple rectifying circuits like a halfway rectifier or full wave rectifiers for energy harvesting, but also telecommunication. And the important aspect here is how fast these diodes can be made to operate. We definitely need for these diodes to operate either at a NFC near field communication frequencies in the megahertz, high frequencies, but ideally, as we see the Internet of Things is developing, these frequencies would increase and potentially the 5G becoming the standard for the years to come. So we are aiming for a technology that can operate in multi-gigahertz frequencies. So typically between 2 and above, gigahertz and above. And this is exactly what we're trying to show. Can we really create these large area electronics using these additive manufacturing techniques and still deliver this very high performance? That's not an easy task. When we look in the literature, the only technologies that have managed to surpass that gigahertz limit is technologies or material technologies that offer high carrier mobility as a semiconductor based in either 2D materials or silicon or carbon-based materials like carbon nanotubes and graphene. And most of those high-performing devices are TFTs, which is not ideal for creating energy harvesting devices, for instance. Diodes are much fewer options with only some metal oxide delivering gigahertz operation, as well as a few examples of molybdenum disulfide 2D type of diodes. But making those a reality, a commercial reality, is still very, very challenging because they're relying on high definition patterning techniques. In our case, what we have done, we took these nano gaps between aluminum and gold, for instance. I've shown you earlier how we define them. You see the little nano gap. And then we solution processed a zinc oxide sol gel precursor solution on top, and then thermally anneal it at 300-400 degrees. And we discovered we can make diodes. Diodes are very, very nice, Schottky type diodes, because simply we have two asymmetric electrodes we're using. One is an ohmic contact and the other is a Schottky contact. When we tested at the NFC frequencies, we showed that we found that it can easily operate at 13.56 megahertz and can be made on plastic substrates if we use the right semiconducting in the gap. Remember, here is the nano gap that makes the difference and not necessarily the semiconductor. We have used the same approach, but using organic semiconductors, and we can still approach frequencies which are more much higher than the 13.56 megahertz. So we're tending essentially with developing a technology which becomes material agnostic, if you like. So the target, of course, is gigahertz, and more recently we've been able to go a step further and develop wafer scale manufacturing techniques, which essentially contain diodes which are RF design. We're using the GSG microwave probe techniques to characterize these nanogap devices. And indeed, when we get everything right, what we see is our devices can deliver exceptional performance. This is a handful of examples of V out of a circuit where we essentially inputting a RF signal and see what kind of DC output we are getting. And we see that we can get a DC output even at a multiple of 10 gigahertz. When we looking at the individual diodes, we see that these diodes can exhibit an intrinsic cutoff frequency in excess of 100 gigahertz. Essentially frequencies that are comparable or start becoming comparable with state-of-the-art silicon electronics. But there is nothing sophisticated about the techniques we have used to fabricate those diodes. And what is very, very intriguing with our approach is that we can start integrating everything monolithically or on the same surface. So for example, we can create structures like the one shown here, where some of the nanogaps are used to create diodes, diode 1, 2, 3, 4, equivalent circuit shown there. And some of the other nanogaps can be shorted to create these nodes. So this is a full wave rectifier that has been fabricated monolithically on a tiny on a substrate, and these circuits can take many different shapes and sizes. Some of the nanogaps can also be used to create capacitors or resistors. So we are gearing towards a fully monolithic technology that can deliver all important electrical components that will enable us to create these RF electronic circuits on arbitrary substrates using these scalable techniques. To make the story even more intriguing, what we have been able to do, we're also able to sinter the semiconductor that is in the gap using light. Instead of using thermal annealing, we simply flash, expose the device to a flash of light, the whole wafer if we want to, and part of the metals will absorb this light, heat up to a temperature, and because the nanogap is so tiny, only 10 nanometers across, the material, the sol gel material that we put in between there can be converted from the sol gel phase to a semiconductor phase. And this is some of the process we have been explaining you here. And the most important aspect is shown in this slide here, where essentially we see the temperature profile during this, which is simulated, but it matches very well with our experiments that happen across a diode, circular diode. This is metal 1 and this is metal 2. And the yellow region here is the nanogap. But if you see the temperature following a flash of a microsecond into, a millisecond, the temperature in the gap can easily reach 400 degrees Celsius, enough to actually convert the sol gel material we are using into its semiconducting phase. So this is exactly what we've done. And we have essentially, this plot here shows diodes created by blue and green by thermal annealing at 300 and 400 degrees shown here. And this orangey curve is the diodes created by a flash lamp in a millisecond. So essentially we can create these structures exceptionally fast and still without compromising the performance. So when we are actually testing out these diodes, what we also found is that the intrinsic frequencies that can be reached, in this case, we have used indium gallium zinc oxide as a semiconducting material. The intrinsic frequencies that can be reached is over 100 gigahertz. We're still fully trying to characterize these devices right now because measuring at those frequencies becomes very, very tricky. So in the interest of time, I think I will stop here. And I will not say anything more about our the rest of the devices we have been creating. It means photodetectors, LEDs, and memory devices. But I would like to close my talk with acknowledging my group that has contributed in different parts of the work, and the group members at KAUST, but also former members of my group from Imperial College. And I will thank you also very much for your very kind attention. I'll be happy to answer any question that you may have.
Thank you, Professor Thomas. I'm sure there's a resounding virtual applause at everyone's seat. This was truly a fascinating presentation. And it's obvious you have been timing yourself, because exactly at the time when I was supposed to ring a bell, you ended your talk. So thank you for that. I do have questions on the question answer box and one hand raised. And I encourage all participants to use the Q&A box. So if you would allow me, I'll open the Q&A box to read out some of the questions. So I have Sanjeet Kumar Paswan asking the following question. Dear sir, my question is that can we use the spinel ferrite and perovskite materials to develop this kind of devices using deposition method?
Absolutely. Absolutely. This is a very interesting area. And I didn't show you some of the applications that aiming at non-volatile memories where we're using ferroelectric materials to create ferroelectric tunnel junctions, and they work fantastically, including both organic ferroelectrics, but also inorganic ferroelectric, using exactly the same techniques I have shown you. So what we believe is the right material, the right chemistry coming together with a pattern technique and deliver tremendous solutions in terms of performance and simplicity of making them, realizing these functional devices.
Thank you very much. The second question on the Q&A box is from Dr. Chandramohan. Can we have control over the size of the nano gap? How can one vary the gap? That was my question too, sir.
Yeah, this is the question that I always get, and it's absolutely a valid question. So far, I've shown you that the self-assembled monolayer that we put on top, on the surface of metal 1, it has a length of a couple of nanometers. So these are our ultimate limit, of course, by not factoring the conformation that it takes when it functionalizes on the material. But recent reports using the same technique from former colleagues of mine have shown that they can go down to a few nanometers by adjusting the spacing of that self-assembled monolayer. The trick here, again, I will stress this a lot, comes down to how amorphous is your metal. If you end up with a amorphous, if you can call it a metal amorphous, then you can easily get to those limits will be defined by the self-assembled monolayer length. This is the ultimate link. If you want to make channels or nanogaps which are 10, 20, 30, 40 nanometers, I don't have a solution to this. Unfortunately, we can only control it at the very extreme end. We have a control over a longer length scales, but it's not something we can do it on a daily basis at will. We still haven't mastered the technique to that extent.
Thank you, Professor Thomas. So I go to the next question on the box here, and this one comes from Saurav Kajli. I hope I'm getting the name correct. Is it possible to fabricate arrays of 2 different electrodes on top of materials or nanotube by self-forming nanogap by buckling? I hope I have The question makes sense to you, Professor Thomas?
Yes. So I expect, if I get the question right, is whether we can create these nanogaps on either a specific materials, not a substrate, but potentially a functional material that either contains maybe the nanotubes or buckling also you mentioned?
Yes. So is it possible to fabricate array of 2 different electrodes on top of materials or nanotube by self-forming nanogap by buckling?
Yeah, I don't know if I get the buckling process, if the substrate is pre-strained, but yes, we can create the nanogap electrodes on top of functional materials. It don't have to go on the substrate. It all comes down to the surface chemistry that the specific system allows us to do. If we can still tune the adhesion forces between the semiconductor we're depositing on or the functional material and the metals and the self-assembled monolayer, then everything is possible. So in principle, it's very flexible, it's doable. We have done it for certain systems. Now the buckling, if that refers to a pre-strained substrate, I don't know. I don't know because the nanogaps are so tiny that any mechanical deformation, I bet the devices I've shown you, for example, the zinc oxide, are excellent nano generators if you could bend them. Is the ultimate system, you know, a Schottky diode, a piezoelectric material in between, if you like, or a pressure sensor. We never test them, but I bet because of the proximity, which is a blessing and a curse at the same time, you can't play too much with their geometry, if you like. That's the only limitation. But in terms of depositing on specific materials at different sequences, yes, it is possible. It's not as straightforward, but it's very possible. But bear in mind, what we have been exploiting so far, it's a very simple, the simplest, the lowest hanging fruits, if you like, from what this technology has to offer.
That was excellent. Well, people, we do have a couple of minutes more, so let the questions keep coming. One more question. Since I don't have a hand raised or a question in the box, maybe I can go with one of my own. So what I found fascinating was this self-forming nanogap is as good, if not better, than an intentionally made nanogap on lithography process. But then the question arises is, over hundreds of samples, how repeatable is the nanogap? Would you have a statistical deviation in them?
Yes, so we have a statistical deviation done on a wafer scale for adhesion lithography using the peeling off, which is actually more destructive than the self-forming. We have done a manual statistical analysis of the self-forming nanogaps, but this is why I've shown you 36 devices, which all shown are completely isolated. And we've done that because we have 36 devices on that little chip. We haven't got an automated prop station, which we could plug in. This is the simple answer to you. But it appears to be exceptionally a better quality than the nanogaps we are actually getting using the adhesion lithography with the peeling off process. Yeah, so this self-forming, it's a kind of an intriguing process, which is known, is nothing new about it. Actually, industry, semiconductor industry was trying to avoid that effect because they don't want things to delaminate, they want things to stick.
Okay.
That combination of materials is known to build up stresses. And what we have done is that the self-assembled monolayer on top of the metal electrode appears to interact a lot with the titanium and platinum, creating these tremendous compression stresses, which up to thickness, beyond which start breaking.
Okay.
Laminates.
Lovely. Very well, Professor Thomas. That was truly fascinating presentation. Thank you very much for that. And I've got lots of positive feedback on the Q&A box for you. And at this moment, I'll thank you. And on behalf of ICONN, wish you all the very best for the future research. Thank you very much.
Thank you very much for your attention and for everyone to attend my talk. Thank you.
Thank you. May I request you to unshare your screen?
Perfect.
Very well, everyone. So after that fascinating presentation, we are on course and on time to move on to the next keynote lecture here. If I can request Abhay to flash the introduction slide, please.
Yes.
Thank you, Abhay. So it's a great pleasure and honor of mine to introduce to all of you Professor Kanishka Biswas from the Jawaharlal Nehru Center for Advanced Scientific Research. And Professor Biswas obtained his PhD from the Staffordshire University, UK. I'm sorry, I'm having the wrong, yep. Sorry about that, Professor Biswas, sorry about that. He obtained his PhD from Indian Institute of Science, Bangalore in 2009. And then he spent some time at the Northwestern University, USA, and joined GNC ASR in 2012. So Professor Kanishka is interested in the solid state chemistry of metal chalcogenides or chalcohalides, thermoelectric materials, topological insulators, halide-based perovskites, and so on, and also interested in water purification. And I got a long and impressive list of awards and achievements, and I'll briefly skim through. So he's an invited fellow of the Royal Society of Chemistry since this year. Congratulations for that, sir. And he's also the MRSI ICSE Materials Science Annual Prize holder for this year. He won the Swarnajayanti Fellowship by the DST in 2019, and is also a IUMRS MRS Singapore Young Researcher Merit Awardee in 2016. I note that he is an associate of the Indian Academy of Sciences, Bangalore. He was there 2014 to 2017, and boasts of a very impressive H-index of 47. So with that introduction, Professor Biswas, can I invite you to present your keynote lecture?
Yeah, thank you very much. Can I share my slide?
Please.
Yes, yeah.
Is it visible?
Yes, Professor Biswas. May I just kindly remind you that for a 45-minute talk, after 37 minutes, I will switch on my video. That sort of acts as a reminder.
Yeah, sure.
Thank you so much.
So how do I keep this box?
It's perfectly fine. You're visible.
Yeah, but by slide, these things are visible. Like, yeah, it's fine. Yeah. So thank you very much for your kind introduction. And today, and also many thanks for inviting me for giving this lecture. So today I'm going to talk about nanostructured thermoelectric energy conversion, and I am from JNCSR Bangalore. So what is thermoelectric? So thermoelectric effect is a direct conversion of temperature difference and to voltage or vice versa. So it has divided in two effects. First effect in Seebeck effect, where we have externally provide the temperature difference, hot end and the cold end, and semiconductor material like P and N type semiconductor can generate voltage. And this is called Seebeck effect, which is known for last 200 years, almost 200 years. And the opposite effect is Peltier effect, where we externally provide the voltage, but this semiconductor material, P and N type material, actually generate the temperature difference, where this active cooling L can be used as refrigeration. So this is a typical thermoelectric device. This is the real device, and this is the cartoon, while we see that P and N type materials are connected in electrical series, but thermally parallel. So now the question is, so why we should do research in thermoelectrics, not only in India, but also all over the world? Because if you see total energy consumption in 2019 for India and world, so we consume energy in terms of coal, petroleum, and natural gas. So after use of energy in terms of, say, electricity, which we generate from combustion of coal generally, and or petroleum and natural gas combustion runs the transportation and industrial sector. So after use of enormous amount of energy in terms of all these things, 65% utilize energy, waste as heat. So we only use 35%. Okay, so what do we do with this waste heat? So if we can convert some of the waste heat to useful form? So actually this thermoelectric material can convert directly this waste heat to electricity. That's why thermoelectric research is extremely important. So what we are going to do, we are going to use this waste heat as a heat source, that is the hot end in the Seebeck effect, and this kind of P and N type material which we actually develop in our lab. So by this thermoelectric effect, by this Seebeck effect, we can convert this waste heat to electricity. Okay. So now, sort of the uses. So uses for direct heat to electricity conversion, it will be large scale in power plants like chemical, thermal, nuclear, and steel power plants. Medium scale, it is in automobiles. So basically, it can be used in car exhaust, and then also it has been already used in space power generation, which is very interesting. But I don't have much time to tell about this. But somebody can go in the web to check how these spacecraft are powered by thermoelectric generators. And also in new uses of this thermoelectric technology is basically solar thermoelectrics as well as waste heat recovery of lithium-ion battery. And for cooling application, already it is products are there in the market based on Peltier cooler, because many of our scientific instruments has Peltier cooler, as well as spot cooling devices, microprocessor, laser diode, and luxury vehicle cool and warm seat, it can be used. Okay, so now so what is the fundamental science behind this thermoelectrics? It depends on this equation where thermoelectric figure of merit is dimensionless, is denoted by Seebeck coefficient, which is in numerator, electrical conductivity, which is in numerator as well, and also denominator contains the thermal conductivity, how heat is conducted through the material. So heat is mainly conducted by electron or holes, which is related to the electrical conductivity by famous Weidemann-Franz law, and the phonon also carries the heat. I'll come in a details. Okay, so now basically we want material which will have high Seebeck coefficient, that is the property of semiconductor, high electrical conductivity, property of metal, and ultra low thermal conductivity, which is in the denominator, is the property of glass. So now we can see the challenge in this field. You have to combine the property of glass, property of metal, and property of semiconductor in a single material. So the material will be a combination of glass, metal, and semiconductor, which will be a good thermoelectric material. So that is the material challenge in this field, and chemist like me, who is solid state inorganic chemist, can develop new material which will have property of glass, metal, and semiconductor, and can have very high ZT. Okay, so now this is the ZT versus temperature versus ER plot for different state of art material discovered from even 2000 to 2000 in the current date, or up to the 2016 or 17, because this review is published in 2016. So if you see, like most of the materials are having the ZT below 2, which is second generation material, and after 2012 few materials are having ZT above 2, which is third generation material. But the problem is that most of the third generation materials are lead. For example, lead telluride, lead sulfur, lead selenide, or it will be like heavy metal based generally. So another grand challenge in this field, how to make new material which will be lead free for high performance thermoelectrics. And this is the efficiency, which is directly related to the ZT and the temperature difference. So ZT of 1 should have a efficiency of around 10%, which is market-based thermoelectrics material available for Peltier coolers and many other power generation applications. Now, I come back to the thermal conductivity, and especially part of the phononic part of the thermal conductivity, which is called lattice thermal conductivity, because this equation, if you see, this lattice thermal conductivity is the only independent part, because electrical part of the thermal conductivity related to the electrical conductivity. So that means we cannot control together one at a time. And whereas the electrical conductivity and Seebeck coefficient basically are also interrelated by carrier concentration by famous Mott equation. So only independent part in this equation is lattice thermal conductivity, and lattice thermal conductivity are mainly governed by the lattice vibration, which is quantized, and then the phonon which carries the heat in this kind of selenides and tellurides are having the mean free path of or wavelength of 1 angstrom to 100 nanometer. So there are two kind of phonon. First one is the acoustic phonon, which when the atom vibrates in the same direction, that gives rise to acoustic phonon, and that actually carries heat in a solid material. And there are another kind of phonon called optical phonon, which we generally can track by Raman and IR spectroscopy. So so basically we have to scatter this acoustic phonon, and which are having the mean free path or wavelength around 1 angstrom to 100 nanometer. So we have to have objects of the similar size to scatter them, so that the lattice thermal conductivity decreases heavily in this kind of material. So there are several concepts developed to how to scatter. The major concept which was known like 60 years back, creating grain boundaries and point defects. But grain boundaries are in the micron scale, and point defects are in the angstrom scale. So those does not scatter the important phonon which carries the heat. So we have to have nanometer size precipitates or second phases in the bulk matrix to have right kind of phonon scattering, which are having the size of 1 to 20 nanometer, and the phonon mean free size is around 1 to say 14 nanometer. So we have to have match of the size of nanoparticle size as well as phonon mean free. So this field first came out in 2004 when the science paper published, You see, this is the lead telluride, which is a champion material in thermoelectrics, shows the lattice thermal conductivity around 2.2 watt per meter Kelvin. So this solid solution point defect decreases the thermal conductivity to some extent, because as you see, this this only scatters the short wavelength phonon, but we need to scatter this mid wavelength phonon, which actually carries the heat. So what they did, they made this material for the first time in 2004, which shows the nanoprecipitate embedded in the lead telluride matrix, and this size matches with the heat carrying phonon and decreases hugely the thermal conductivity. After that, several papers came in this field. So this is picture is taken from this Nature paper, which is published in 2012, where it shows that like nanoscale precipitate as well as mesoscale grain boundaries and proper doping can give rise to an ultra high ZT, and this is the first time this paper showed a ZT of above 2 for a bulk material. And from Bangalore, we have contributed enormously in this nanostructure field. So some of the example I'm going to talk to you today. So now basically, as I told you, one of the grand challenge in this field to have lead-free material. So today I'm going to talk about tin telluride, which is a promising thermoelectric material because it has the exactly similar structure as lead telluride. This is nothing but a sodium chloride structure and almost similar electronic structure, but there is a slight problem in the electronic structure because there is a gap between two valence bands, which we have solved in 2016 to make it good thermoelectric by electronic structure modulation. But today I'm not going to talk about electronic structure modulation. Rather, I'm going to talk about how to tune the phonon in this kind of material. So this is the lattice thermal conductivity, phononic part of the lattice thermal total thermal conductivity of tin telluride, starting from 3 watt per meter Kelvin and goes to around 1.1 watt per meter Kelvin. So if we can calculate theoretical minima of this lattice thermal conductivity, it is to be around 0.5 watt per meter Kelvin, which is generally calculated if we know about the sound velocity, crystal structure, as well as this is good enough, and then the how many number of atoms present in the unit cell. So there is a plenty of room how we can decrease actually the lattice thermal conductivity of the tin telluride. So we thought it would be a challenging problem a few years back. So what we did, we purposefully added antimony in the tin telluride, and we added around 0 to 20 mole % of antimony in tin telluride. Okay, so let's see what happened. As soon as we put 4 mole % of antimony, thermal conductivity started decreasing, and then around 15 mole %, you see this green curve shows very low thermal conductivity and very near to the theoretical minima of the tin telluride. This is one of the lowest value reported for tin telluride thermoelectric. So this is our data. So let's see what happened. So first we checked transmission electron microscopy investigation of this sample, 4% sample, where we see small nanodots, which is already known from 2004 by the science paper from Northwestern University, which tells that basically these nano precipitates of the size of 2 to 10 nanometer are very good for phonon scattering and to decrease the thermal conductivity. But now the surprise is that what is happening to this 15% sample? So is that something different kind of nanostructure we can expect in this? Let's see the TM image, and when we have done the microscopy investigation, we see there are layered nanodomains. So this is the first example. This was the first example of 2D layered nanodomain in a thermoelectric materials. And then we try to understand what are those layered nanostructures formed in a bulk tin telluride matrix. When we have done electron diffraction as well as FFT of this HRTM image, we see there is a superstructure spot along the 111 direction. So tin telluride is a cubic rock salt structure. So now if the ordering is happening along the rhomboidal direction, we can expect there will be a layered compound because we have an idea that this kind of intergrowth compound can form in the tin telluride matrix. So this is a complex formula. So I'll simplify in a minute what are these compounds. So these compounds are basically SN-TEM and Sb2T3N. So basically by varying M and N, actually we can make different layered compound in this series, which actually forming in the matrix and scattering phonon heavily. So these two-dimensional nanostructures are much better in phonon scattering compared to the zero-dimensional nanostructure because that has intrinsic van der Waals gap in the material. So let's try to understand more what is this intergrowth compounds. So if I write now MTEM and M prime to T3N, what I wrote exactly, M can be replaced by M can be germanium or tin or lead. In last example I showed it is tin, and M prime can be antimony or bismuth. Last example I told this M prime is antimony. Okay, so now this is a homologous series, and homologous series is basically a concept of mathematics, and this was first shown in 1950s or 60s in solid state chemistry. So if we can define this kind of series in solid state inorganic chemistry, basically this is a compound generating machine. So by changing M and N, M prime, we can have this many series, and by changing M and N, we can have enormous number of new compounds which are actually having the layered structure. Okay, so I'll give you some of the example. So this is very interesting in terms of chemistry as well as material science. So if you see, this is the first example is SnBi2Te4, which is nothing but SnT1, M equal to 1 and N equal to 1. So we see this is, we all know the structure of bismuth telluride quintuple layer layered structure, and this inside the quintuple layer there is another layer intercalated inserted, that is the tin layer, and this compound become SnBi2Te4. So basically Sn, then Bi2 and one tin, one tellurium, and it goes here. So it's become SnBi2Te4. Okay. So now if I do 1:2, that compound become SnBi4Te7. So in between two SnBi2Te4 unit, we have one bismuth telluride unit. So this is also a new compound. So now if I do 1:3, so then I have SnBi2Te4, Bi2Te3, Bi2Te3, and SnBi2Te4. So this is basically 7 layer, 5 layer, 5 layer, 7 layer. So basically we can create enormous amount of new compound if we can carefully synthesize them. But synthesize them, it's very, very challenging. I'll tell you why. Because this is the layered bismuth telluride structure, one end of the phase diagram, another end we have rock salt tin telluride structure. Now if I change the ratio, basically doing 1:1 or 1:2 or 1:3, we create layer compounds, and these are the line compounds. But the problem is that these all compounds are incongruently melting. So incongruently melting meaning if we try to cool it from the melt, there will be phase separation, or if we heat it, there will be also phase separation. So the synthesis of this compound from high temperature solid state seal tube melting or any other technique, high temperature synthesis is extremely challenging. So somebody needs to do a kinetic synthesis. Kinetic means either bottom up or some different kind of kinetic synthesis has to be done to stabilize those compounds. So we have done one kind of kinetic synthesis, making it bottom up synthesis by very, very low temperature solution phase synthesis. This is the compound like say SnBi4Te7. We made pure phase, and this is the 757 layer, and you can see the HRTM image. This is exactly 5 layer bismuth telluride, and then you have SnBi2Te4, and this is the head of STM image. Exactly, you can see 7-5 layer stacking fashion, and you can measure from here or either here. You can see the bismuth telluride layer and the SnBi2Te4 layer are stacked, and this compound are different compound we have synthesized from this homologous series, and not only from this, we have synthesized from antimony analog as well as the lead analog, and we can do many things in this. And this pure compound shows ultra low thermal conductivity because it has van der Waals gaps and also a very high long unit cell with corrugated structure. So automatically phonon scattering happens and shows ultra low thermal conductivity. But good thing about these compounds are these are all predicted by theory as a topological insulator. Some of them are showed by angle resolved photoemission, like topological phases, topological quantum material phases. So this compound in the form of nanosheets shows very high carrier mobility, probably that surface state contribution increasing in the nanosheets or two-dimensional nanosheets. That's why it shows very high mobility. So now I go back to this slide here. So basically, these kind of compound actually matrix encapsulated and formed in the solid state matrix. So this is another kind of kinetic synthesis where these layered compounds are generally formed in the matrix. Okay, so by kinetic matrix encapsulation, so those compounds shows much higher phonon scattering, much stronger phonon scattering compared to the 0D nanoprecipitates, and that's why we see very low thermal conductivity. And this is one of the first example to show that two-dimensional nanostructure encapsulated in matrix are far better than zero-dimensional nanoprecipitate, which showed by 2004, conceptualized by 2004 science paper. So now I come back. So I come back to the talk again, and then I talk about now germanium telluride. So germanium telluride is another important material, very promising material in thermoelectrics, and this is also lead free. As you can see from summarized ZT versus temperature versus ER plot of germanium telluride, many of the germanium telluride actually showing the ZT close to 2 or slightly above 2, and which is a very important material for different reason, because it has unique crystal structure, unique electronic structure, and it has ferroelectric phase, and it has ferroelectric phase at room temperature. Because germanium telluride is basically one of the simplest ferroelectric, which shows great thermoelectric property. But the problem with germanium telluride was basically this germanium telluride, most of the all of the materials are P type, but you need P and N type legs both for actually P and N type leg both for making the thermoelectric devices. So that there was no N type material based on germanium telluride was reported till we started searching for N type material 2-3 years ago. Okay, so now this is the structure of rhomboidal structure, non-centrosymmetric rhomboidal structure, which is ferroelectric phase at room temperature, and high temperature it is as rock salt cubic phase, which is paraelectric phase. And rhomboidal structure, you see there is expression of 4s2 lone pair, and that's why there will be 2 types of bond, short bond and long bond. That's why we have a ferroelectric phase, and Fm3/m it's situates in perfect octahedra, and this lone pair is actually quenched, and it is not stereochemically expressed. While in rhomboidal phase, the lone pair is stereochemically expressed. So now this is the lattice thermal conductivity, which is also quite promising, and there is a clear signature of ferroelectric phase transition. And this is the phonon spectra of rhomboidal phase, and this is the cubic phase phonon spectra. If we calculate 0 Kelvin, you see there is a instability, a huge instability of unstable TO mode, and condensation of these 3 modes actually stabilizes the rhomboidal phase at room temperature, and we see ferroelectricity. So now we have alloyed germanium telluride with AgBi-Ac2, and AgBi-Ac2 is also a good thermoelectric material. We have alloyed starting from 0 to 50 mole % of AgBi-Ac2. You can see this is the 2 rhomboidal peak, double peak rhomboidal, and slowly it's merging to a single peak, so it's becoming a cubic sample. If we go from 10 mole % to around 40 to 50 mole % of AgBi-Ac2, and this is the temperature dependent powder excess diffraction, which clearly shows that the phase transition temperature significantly decreases, which is supported by DSC when we allow it with AgBi-Ac2. So this system is more like cubic at room temperature, which is supposed to be rhomboidal in pure germanium telluride phase. So then the most interesting plot is basically the band gap of the germanium telluride decreases and goes near to the 0, very near to the 0, and again increases with changing the structure from rhomboidal rhomboidal to cubic phase. And then this happens due to the effect of chemical pressure, and probably this phase could be a new topological quantum material. Somebody has to check by RPS or some other measurement technique that we have not done yet. So then you can see the most important part is basically the Seebeck coefficient. So Seebeck coefficient sign is positive, meaning Seebeck coefficient sign is positive, meaning it is P type, and Seebeck coefficient sign is negative, means N type. So these up to the rhomboidal phase, where we have around 20 mole % of AgBi-Ac2 alloys phase, it's P type. Whereas we suddenly get N type phase above around 30 mole % of AgBi alloy. So this is the first report of N type germanium telluride in the literature, which we published in 2019. And then we have done electronic structure calculation in details, also electronic DOS calculation with collaboration with Professor Wagmore, which shows that this N-type nature actually comes from the BIP orbital near the conduction band edge. So I'm not going to do the details of that, but if anybody has question, I'll explain why exactly it forms near the conduction band edge rather than valence band. Okay, so now we have measured the total thermal conductivity of these many samples, and this is the lattice thermal conductivity. And lattice thermal conductivity decreases significantly when we alloy it with AgBi-Ac2. This probably by entropy dependent solid solution point defect scattering, and also with nanostructuring. because we see several different kinds of nanoprecipitates with different size, which is good for phonon scattering actually. So you can see very small germanium precipitates and also AGT2 precipitate, very small precipitate below 5 nanometer precipitates, and also domain variants, which scatters the phonon and gives rise to ultra low thermal conductivity. And we could get both p-type and n-type in this material. To up to 20% its p-type around ZT of 1.2, 1.3, and this is the first report of n-type, and which is around ZT of 0.6 around the composition of 50%. So we have both p and n-type in the same material of germanium telluride. So so now we would think like, can we increase the ZT from 1.3 to a much higher value for this germanium telluride? Okay, so in order to do that, we have to understand these nanostructures are not always good. It's definitely very good for scattering phonon. As you can see, it can decrease the thermal conductivity tremendously, but it can scatter electron and hole, which can decrease the mobility and which can decrease actually the power factor to some extent. So we are somehow compromising with this electrical mobility and electrical conductivity when we are doing the nanostructuring. So can we do something where we can have low thermal conductivity at the same time very high power factor, so that we can have very high ZT. So we have to do that. We have to stop stop forming these nanostructures, and to understand that, we have to understand how these nanostructures form. So nanostructure in this material or in any kind of material forms by this simple thermodynamics, where delta H, that is the enthalpy of compound formation, dominates over basically entropy of mixing. So if compound formation dominates, that is the nanostructure formation dominates, enthalpy dominates over entropy, we can have nanostructures. But can we have a platform? Can we make a platform by simple chemistry where this delta S will be dominating over delta H? Okay, so we wanted to create this platform, and we have checked in the literature and seen that this kind of binary systems like PBT, PBSE, or GT, GAC, or PBT, PBS, basically PBT, PBS, we can have the nanostructure because delta H dominates over delta S. But can we create like pseudo ternary system where entropy may dominate? So we are interested to do work in, say, germanium telluride, germanium selenide, germanium sulfide kind of ternary system, where we'll have high entropy atomic mixing as well as high degree of disorder, and effective point defects will dominate rather than nanostructures. So basically that's what we wanted to do. And we have measured the thermal conductivity of different sample, and we showed that very low thermal conductivity in this sample, and this is a high entropy system where point defects dominates the nanostructure. We have fitted model, this lattice thermal conductivity, and fitted by Callaway model, and showed that actually this system is point defect rich rather than nanostructure. And we have cross-checked by TEM and microscopy that there is absence of nanostructure, but at the same time this sample has huge point defects, and that's why we could able to see without deteriorating the power factor, we could see ultra low thermal conductivity. And this is on the important slide where you can see the pseudo ternary system, is the black curve, shows much lower lattice thermal conductivity than the binary system, which is actually nanostructure. So excess point defect actually dominates over nanostructure. So that means entropy dominates over formation enthalpy. That's why we could see very good ZT, and this is one of the first first generation material, a third generation lead-free material made from India, and ZT of 2.1, and which is highly cyclable, and we have cycled several times, and it's highly reproducible. And we could see a ZT of 2.1 of this entropy driven system. So later we have followed up this system by not only cation side, also anion side disorder. So basically we have germanium telluride, tin selenide, and tin sulfide, because this has huge disorder, so the entropy should dominate over enthalpy, and we have more and more point defects, and it shows again ZT of around 2, and which is highly reproducible again. And we have made a device out of it now, single leg device, which shows very good power output around 160 milliwatt, and this is compared to the state of art. And please remember, this is lead free, and this shows ZT of 2 with a good device performance. So now I come to the last part of the talk. So how much minute I have? Around 10 minutes?
Yes, Professor Bishwas, you do have 10 minutes.
Okay, thank you very much. So now I want to tell you that this nanostructuring as well as point defect engineering is important to decrease the thermal conductivity, but to some extent it deteriorates the mobility and deteriorates the power factor of a material. So can we do something like that, making a sample from a furnace or some solution phase, whatever, like, but it will show ultra low thermal conductivity without doing any nanostructuring or point defect engineering or mesostructuring. So in order to do that, we have to modulate the chemical bonding and lattice dynamics. Okay, so I'll show you a last one example, last 5 minutes, and I'll try like to have more question. So so basically, low thermal conductivity of a material demands soft phonon modes. Okay, so soft phonon modes meaning it will have low energy optical modes, which will couple with basically heat carrying acoustic phonon. So that's the key, and that will have low thermal conductivity. Now this material science community already known that ferroelectric instability is a field of softening of polar optical phonon. Now fortunately, tin telluride, if we calculate like a phonon dispersion in a cubic phase is stable at room temperature, you will see very small ferroelectric instability, and this is due to the instability is due to the optical phonon. Okay, and this was that's why the low temperature Longwedel phase of tin telluride is stable. Okay, so now this has been known for a long time, like 1975. This is from a Japanese paper. It showed that below 70 Kelvin there is a ferroelectric phase of tin telluride, and above that it is rock salt cubic phase, which is having non-centrosymmetry. So now our motivation was basically, can we have this ferroelectric instability in a thermoelectric material near room temperature or slightly above room temperature, so that it will have softening of polar optical phonon, and this optical phonon actually will couple with the heat carrying acoustic phonon and give rise to low thermal conductivity. So the main motivation was basically we wanted to couple these two fields, ferroelectric instability and thermoelectrics. Can you do that? So let's see how to do that. So we have to know good chemistry of this system. So as soon as we saw tin telluride has this instability at very low temperature, we have purposefully alloyed or doped germanium from 20 to 30% in this material. So why germanium? So germanium is sitting just above the tin in periodic table. So it has 4s2 lone pair, which is like very active compared to the tin lone pair, tin 5s2 lone pair. So germanium will try to distort locally. Okay, and it will probably have a ferroelectric instability. For example, you see from the DSC curve, this ferroelectric transition comes to the near room temperature when you have 30% germanium doping in tin telluride. So we could bring this ferroelectric instability so near to the room temperature. That's the major observation. So now phonon dispersion curve, again calculated by Professor Umesh Bhagwan's group, shows that huge ferroelectric instability in this germanium doped tin telluride sample. And interestingly, we see instability except R point in all the other points in the Brillouin zone. So that means there will be a chain type local distortion of germanium lattice in the cubic tin telluride lattice. So what I'm meaning, I'll simplify it. So basically germanium is locally off-centered, okay, but the global structure is cubic, okay, but the local germanium off-centering actually creating this ferroelectric instability, because locally the centrosymmetry is broken, but the global average structure of the material is basically rock salt cubic, which is a very challenging problem to understand in terms of crystallography. So let's see what happened. So we have to like measure together the local structure versus global structure, okay, which can be done only by few techniques. One of the technique is synchrotron X-ray prior distribution function analysis, that we are expert in this. So we frequently visit to synchrotron, and this data has been taken in Petra, where this ripples tells basically the bond lengths at local scale. If you see this first peak is the tin tellurium or germanium tellurium distance, and the third peak is the second nearest one and third nearest near distance, and these ripples are basically explain the global structure. So now, if the local structure fitting is good, but the global structure fitting is bad, we can tell that local structure can be modeled by a particular model, whereas the global structure cannot be modeled by that model. Okay. So how to do that? I'll tell you. So when we have try to model this whole structure by cubic rock salt structure, the local structure cannot be fitted properly, but the global structure is fitted very well. But when you have distorted the germanium, which is predicted by DFT calculation of phonon, slightly, the local structure is modeled well, but the global structure cannot be modeled. So the actual structure of the system is basically locally distorted, which is local, having local rhomboidal distortion, but the distortion amount is so small compared to a clear structural transition. The average structure will be global cubic, but the local structure is rhomboidally distorted. So we have experimentally showed that locally the germanium is around 0.1 angstrom distorted, and 0.1 angstrom is basically around 15 to 20% of the bond length. Okay, so germanium is distorted, and this local germanium distortion actually, this is the room temperature and stays above around 2 Tc of this material, which is very important, and that's why Raman spectroscopy we see soft optical phonon modes. Okay, at very low energy. This is very low energy soft optical phonon modes, which is seen in 30% sample, which is having near room temperature ferroelectric instability, and this sample does not have ferroelectric instability near room temperature, so we don't see them. And due to this low energy optical phonon modes, which actually couples with the acoustic phonon modes and give rise to ultra low thermal conductivity in this material, which was very low value, without doing nanostructuring, without doing any mesostructuring on point defects. But this sample has having ferroelectric instability, and with this coupling with ferroelectric instability and thermoelectrics, it shows a really high ZT of 1.6, which is one of the record value that time in Tinkelwed in 2019. So we showed first time this ferroelectric instability can be coupled with thermoelectrics to show ultra low thermal conductivity. And another good thing about ferroelectric instability, near the ferroelectric TC, the dielectric constant will go high, and then it will have dielectric charge screening and screening, so you will not lose the mobility. So the mobility of this sample also retained to a good value, which is there in the paper. So with this, I will show you where we stand from Bangalore compared to the world state of art thermoelectric. So these are the material which we discovered from Bangalore. Like this is unpublished, which is going to publish very soon in February this month. And also these are some of the material I presented, which shows first generation lead-free third generation material discovered from us, and also this is one based on SNSE. And then these are all state of art taken from literature. So the mid temperature range actually we show one of the highest figure of merit from here, and some of the material showed record high single leg based thermoelectric efficiency based on germanium telluride base again, and we have a very good collaboration and research agreement with Tata Steel, because the steel plant will have a lot of low grade to several different grade of waste heat, and we are going to actually we are making a device for them, and they are going to put those devices in this kind of steel plant where the lot of waste heat can be recovered in terms of electricity. So I'll conclude my talk. So today I have showed low thermal conductivity is an attractive paradigm for developing high performance thermoelectrics. I showed like how to generate a homologous series in chemistry, and this 2D homologous series with a corrugated structure with van der Waals gap could show very low ultra low thermal conductivity and good mobility, and because some of them may have topological surface metallic surface states. And entropy, next example I showed like how to make a platform which can have competition between enthalpy of nanostructure formation and entropy of mixing. If entropy of mixing wins, you may have very low thermal conductivity and high thermoelectric figure of merit. And also I have shown how electronic structure modulation by n-type doping and alloying can make rare n-type thermoelectrics. And also at the last example, where I showed like a new field is beginning like where ferroelectric instability coupled with the thermoelectrics, and we have low thermal conductivity and high mobility to have high thermoelectric figure of merit. So I should acknowledge all of my excellent students. This is the few years back picture, and this is taken like last week. This is the current group, and I have excellent collaborators from different parts of India, and also generous funding from ACRB and DST, Tata Steel, Sheikh Shakal Laboratory, and my seed grant from my institute, New Chemistry Unit and JNCSR. So thank you all, and I will be happy to answer all the questions if you have.
Thank you, Professor Bishwas. That was a very exciting presentation. It's amazing how close you are into the application domain already. So with that, let's have a look at a few questions which we have received. I have 3 questions in the Q&A box, and I encourage other participants to raise their hands. Yes, I do have a hand raised. So the first question in the box comes from Vijay. Sir, in some compounds, we expect to reduce the lattice thermal conductivity by doping, but this also reduces the electrical conductivity. How do we find the dopants to reduce only lattice thermal conductivity?
So it's a very good question. Partly I have answered in the last example. So some of the doping of course can decrease the thermal conductivity by not only by point defect scattering, but also you can create local distortion, which can soften the optical phonon and decrease the thermal conductivity. But if you choose your doping properly, that may create ferroelectric instability or some other effect which can retain the mobility. So that's the challenge, how to optimize both at a time. This is one of the grand challenges in thermoelectrics, and not only our group, few other groups are also working in this direction, how to optimize both at a time. Okay, so but of course, like if you do the doping without much understanding of the system, you will of course lose the electrical conductivity.
Thank you so much. I have a couple more questions from Vijay again, but I would like to take a question by Suresh Perumal, who has raised his hand. Suresh, can you go ahead and ask your question?
Hello, sir. It was a very good talk. As usual, it's very nice to see you again. And my question is related to antimony doped germanium telluride. So, thing is that what is the feasibility of getting this kind of 2D intergrowth nanostructures? I mean to say that.
You see, basically, Suresh, you work with me, so you know better. Okay, so your picture is there also. So basically, antimony doped germanium telluride, we got intergrowth. We are about to write the paper now.
Yes.
Okay.
Good.
So we got intergrowth in this material.
Yeah. And one more question is that how stable are this kind of nanostructure, because it's a 2D intergrowth nanostructures?
Yeah. So these are very stable. Because you can see it sustains the cycling of the thermoelectric properties, and the thermal conductivity is pretty flat. Okay, so the nanostructures are quite stable. This kind of nanostructures, and any kind of nanostructures are very good to give good mechanical stability of that material. I think you know better this thing, because there will be crack propagation or many other things. So that can be arrested also by nanostructures. So nanostructure have multifold. Basically, it can different way it can improve the thermoelectric property or mechanical stability.
Good. Okay, sir. Fine. Thank you, sir.
All right, thank you. So I'll take the next question from Vijay, but I will advise Madhurima Deb, who has asked a rather non-specific question. Madhurima, if you can raise your hand, I'll make you audible. Till then, can we take the question from Vijay, which goes, what is the reason for the disorder in the systems like germanium telluride or AgSbSe2? Is that clear enough?
Yeah, Miss, I understand the question. So germanium telluride itself does not have a disorder, but AgBiSe2 or AgSbSe2 has an intrinsic disorder, because AgSbSe2 and AgBiSe2 is having the rock salt structure. Rock salt meaning a simple sodium chloride structure, where selenium takes the chlorine position, and Ag and Sb or Ag or Bi takes the sodium position. So the cations are confused. They don't know where to sit in the sodium position. So basically, these are crystallographically disordered positions. So this is intrinsic disorder in the system. Okay.
All right, great. So one more question from Vijay. How effective are the topological materials for thermoelectric applications?
Yeah, they are effective, because the best material known for thermoelectric is for low temperature application is Bismuth telluride, which is one of the best known strong topological insulator. And there are several other materials which are topological insulator at the same time good thermoelectric. Because we have written a review on that, actually 2 reviews on that, how topological materials are good for thermoelectric. But simply I can tell, because both are having heavy elements, and heavy elements will have good spin orbit coupling, which can give band inversion, which is the main criteria for topological material. And heavy elements can give like low thermal conductivity. So that is the criteria for thermoelectrics. And also heavy elements can give rise to low band gap, which is also is a criteria for thermoelectrics. So these two field crosses path when you do the research in heavy metal based chalcogenetics.
Thank you very much. So the question from Madhurima Deb is, I would like to know more about the device part. It's kind of non-specific. So if you can come on, you can raise your hand. I'll make you audible. You can directly ask the question. In the meantime, maybe I will go with one short question of myself. You said a phrase cyclable. ZT, which is close to 2 for germanium telluride, is highly cyclable. What does it mean? It's kind of technical. What is cyclable?
Cyclable means you have to go heating and cooling multiple cycles. Okay.
So that
yeah. So
it's not no hysteresis there.
see, hysteresis will be there with germanium telluride. It goes from a rhomboidal to the cubic phase, which is a first order transition. So you will see a slight hysteresis, but that is like good enough. It's not a problem. But the ZT value should reach at the like with different cycle. It should be reached in the error bar. That's the main point of cyclability.
Okay. Thank
because
you.
see, good about this like thermoelectric technology, because as you know, this is used by NASA for last 35 to 40 years for the spacecraft. Okay, because spacecraft, if you go deep space mission, how you power the spacecraft, right? So you cannot power by solar cells so effectively, because the solar cell efficiency will go will decrease if you go far and far from sun, right? So what they do, they have used this thermoelectric power generator, but they have a seal tube and they put basically radioisotope, and radioisotope decays and gives the heat. And this seal tube is basically covered by thermoelectric generators. And, the half-life of this radioisotope is 30 years. So you can get 30 years power for spacecraft. So that means it does not require much maintenance, this technology.
I see. Nice.
Because it does not have like moving parts, basically.
I see. Nice. Really nice. Very well. I don't see any more hands raised, no more questions typed in. So I think with that, I would like to thank Professor Kanishka Biswas for this really amazing presentation. And again, I would like to wish you all the best on behalf of ICON. And that also brings me to the end of my officiating session. So thanks, Abhay. I'd like to hand over the session back to you.
Thank you very much.
Yes. Yes. Thank you. Yes. Can you? Yes. May I request you to stop sharing your screen? Yeah. Yes. Yeah. Thank you. Thank you, Professor Muzumdar, for sharing this session and keeping it on time. So on behalf of organizers, I would like to thank all the speakers and conclude this session. Thank you.
So good afternoon to all. So I welcome you all to this next keynote lecture 14. So this session consists of two keynote lectures. Keynote lectures 14 by Professor Wolfgang Cook, Institute of Experimental Physics, Freie University Berlin, and keynote lecture 15 by Professor Colobrin-Maity, Tata Institute of Fundamental Research, India. So before you start the session, I introduce the chairperson, Professor Dr. C. Gopalakrishnan, Associate Professor, Department of Physics and Nanotechnology, SRMIST. So his area of interest is nanostructured materials, magnetic thin films for data storage applications, multiferroics, magnetic caloric materials for magnetic refrigeration, magnetic nanomaterials for drug delivery applications, sensors, and environmental nanotechnology. So he received several awards and achievements. So from April 2019 to September 2019, he is a visiting professor, Australian National University, Australia, and he is the founder of Nanotechnology Research Center with the state-of-art research facilities in SRMIT, around 20 crores approximate budget. And he received prestigious fellowship from Science Foundation, Ireland, 2002, Trinity College, and is a Dublin Editorial Advisory Board member for Material Advances, RSC, on 2020 onwards. He is a visiting scientist, Queen's University, Canada, 2006, and guest scientist from Max Planck Institute for Microstructure Physics, Halle, Germany, from August 2001 to November 2001, and is a member in the National Policy Document for DBT, Government of India, and he have 90 publications in peer-reviewed international journals, 2 patents in India and 1 patent in US on material science. So he is having 1045 citations and H index of 15. So with this brief introduction, I invite Dr. C. Gopalakrishnan to chair the session. Sir. Yes.
Good morning and good afternoon. This is my great privilege and honor to introduce 2 distinguished speakers in this session. One is Professor Wolfgang Cook, another one is Colobrin-Maity. So I have a great regard for Professor Wolfgang Cook, as I was a student for some time. I was working with him, and I know Professor Colobrin-Maity as well, with respect to Drocote committee members where I have interacted with him. I've been following his research work. So the first speaker will be Professor Wolfgang Hu, Institute of Experimental Physics, Free University, Berlin. So his research interests are magnetic ultra-thin films, multi-layer systems, who introduced ultra-thin magnetic films to me when I was a student. So he works on several areas in the magnetic materials, which include data storage, sensors, magnetoelectric devices, reversible switching of molecules, and also ultra-thin antiferromagnetic films. Professor Wolfgang Hu has a fantastic academic and research record with incredible capabilities for advanced research, which includes he is member of German Physical Society and visiting scientist at IBM, Vice Dean for Study Affairs in Free University Berlin, and he is a review member of the panel, especially in the synchrotron radiation source. He is in the scientific panel in Bessie and Hellman Zentrum Berlin for materials and energy. The head of the Master Examination Committee, Würzburg Physics, Free University Berlin. He is also a proposal reviewer of Swiss Light Source, which is one of the very big national facility. I would rather say it's an international facility as well. A member of Prometheus Prize Selection Committee, and he has got over 157 publications, which H index of 38, and total number of citations 4259. Professor, I welcome you for your distinguished lecture, and I am proud to say that you are my professor. Please go ahead, sir.
Yes, thank you very much. Thanks to the organizers for inviting me, and it's nice to see you again after that time, although it's only virtual. And with my talk, I want to take you to the world of magnetism. Just a moment.
Sir, you please share the screen, sir.
Yes.
Yes, sir. Yeah. Yes, sir.
Is it coming?
Yes,
Okay.
sir. Yes, sir. Yes, sir.
Yeah.
Yes.
Okay, I want to take you to the world of magnetism and to the ultra-fast timescales. And just as a first motivation, I want to show you the expected numbers of the global amount of digital data. And if you look at that photograph, you can imagine that these people are taking in a few seconds like gigabytes of data that might be mostly redundant in this case, but the prediction for the globally stored amount of data is that by the year of 2025, it would be more than 175 zettabyte. And to know what zetta means, one has to look it up. It's a 10 to the 21 bytes. And just to get an impression of how much data that would be, if you can write 1 bit in 0.2 nanoseconds, that is what in some storage devices is already very fast. That would mean 550 megabyte per second. Then it would take 10 billion years to write this on a single device. Or conversely, it would take 1 year on 10 billion devices, or and so on. So you have to really also care on the speed of writing this data. And on the fundamental side, we can ask the questions, what would be the minimum time to manipulate magnetism? Magnetic storage is still one of the still important devices for storing magnetic information, in particular in the large data centers where a lot of data is stored sequentially. It is the fastest, I think, up to now. And I have plotted here a time scale in seconds. So we start with microseconds, nanoseconds, picoseconds, and femtoseconds. And the traditional storage or the traditional means of reversing a magnetization is just when applying a field opposite to the magnetic moment. That happens here on the time scale of sub-microseconds. Domain wall motion, that would be like moving the domain wall to reverse the magnetization from one direction to the other, may happen on the time scale of nanoseconds. Even faster would be the precessional magnetization reversal. So magnetic moments are angular momentum, and applying the field perpendicular to the moment leads to this precession, and the precession happens in the time scale of several gigahertz, so that is sub-nanoseconds. Faster is all optical switching. So on the bottom here, I've shown the timescales of applications in experiments. So mechanical shutters, magnetic field pulses can be on the picosecond timescale. Electron bunches are here in this timescale, and laser pulses can be in the timescale of 10 to 100 femtoseconds. So all optical switching means that the magnetization is not reversed by a field, but just by laser pulse. And this has to be shown that it is effective. So these are static images of magnetic domains. White and black means opposite magnetization directions. And by shining a short laser pulse here, the magnetization can be reversed. In my talk, I will focus on these two. And I cannot switch to the next somehow. Okay, sorry for the disruption. So in my talk, I will focus on these two things, the laser-induced demagnetization. I will just show you what this means. And the fastest is electronic transitions. That means just by the absorption of a photon, the electron is excited into another state. And that happens here on the timescale of a few nanoseconds or 1 nanosecond. And for the experiments, I will rely on laser pulses, but also on sliced electron bunches for the generation of fast synchrotron radiation. Ultra-fast laser-induced demagnetization. Let me start in the late 90s with these experiments. So several experiments using different methods like time-resolved magneto-optical Kerr effect, time-resolved photoelectron emission and spin polarization, or time-resolved second harmonic generation, discovered that the demagnetization, and this is now the drop of magnetic signal in time, happens faster than 1 picosecond. That was not expected at that time. And it meant that the model of temperature in a sample had to be expanded by a shortcut between the electron and the spins. Let me just shortly explain that 3-temperature model. So the system is on the very short time scales, has independent temperature of the electrons. That is like the smearing out of the occupied states at the Fermi edge. The lattice, that would be the temperature of the lattice vibrations, so the phonon occupation. And of the spins, that would be the how many magnons we have in the sample. And it was known that, or it is known from electron-phonon coupling constants, that the transition from the energy, so the laser excites the electronic system, and then by electron-phonon coupling, this equilibrates with the lattice. And this is shown here on a time scale. So the laser pulse very quickly excites the electronic system to a high temperature, and it equilibrates with the lattice temperature after around 10 picoseconds. So that cannot explain this ultra-fast demagnetization. The magnetization, the relevant temperature for the magnetization is the temperature of the spin system. And it has to be that some strong coupling between the electrons and the spins happens on a faster timescale that comes from the experiments. And modeling a 100 femtosecond timescale here gives this result that the spin system equilibrates much faster or raises the temperature much faster than the lattice. And the suggested mechanisms for this coupling can be split into local mechanisms that have been discussed in literature or are still being discussed. Most important is a Elliott-Jaffet type of spin flip scattering, or the ultra-fast generation of magnons of spin waves. All mechanisms have to have a spin orbit coupling to dissipate the angular momentum from the magnetic moments to the rest of the system. Not so long ago, also non-local mechanisms for this coupling have been, so for the decrease of the magnetic moment, have been discussed. And this is superdiffusive spin currents. That came from that paper from the group of Peter Oppener in Uppsala in Sweden. And the idea here is that the angular momentum is not dissipated locally where it was, but that laser pulse excites also currents, spin currents, and their behavior is not just diffusive. That is why it's called superdiffusive. And in the magnetic material, the spin current of majority type has a longer mean-free path than minority type, and thus can go into an adjacent layer. And if more majority electrons are carried away by the spin current in the adjacent layer where they then dissipate, this helps to get rid of the angular momentum in the ultra-fast demagnetization. And it can contribute, or even, as they have shown in this theoretical paper, completely explain the ultra-fast demagnetization by this non-local mechanism. And even more recently, another mechanism has been suggested to be in certain samples important for the dump of magnetic moments. That is the so-called optically induced intersite spin transfer. Because this is a long word, it is abbreviated with this abbreviation oyster, which is usually pronounced like the oyster. And it came from the group of Sangeeta Sharma at that time in the Max Planck Institute in Halle, and now in the Max Born Institute in Berlin in this theoretical paper. And this graph is from an experimental verification of this process from the group of Stefan Eisepitt, also in the Max Born Institute in Berlin. And they compare the demagnetization, that is this one, so fully magnetized, zero-magnetized as a function of time in different systems. And the important point here is this is a cobalt film, and all the other samples are cobalt-platinum alloys, just measured at different energies. And the dissipation of angular momentum seems to be much more effective when platinum is mixed into the cobalt. And the explanation comes from this oyster. And now I have to explain it, what it means. Oyster means that on an ultra-fast timescale, the excitation of density of states or of electrons from occupied states in one atom to the unoccupied states, not in the same atom, but of a neighboring atom of a different species. And this is shown here in red, the platinum states or platinum d states spin split, and in blue, the cobalt d states. And the excitation of platinum minority carriers into the unoccupied states of cobalt minority type would dump the cobalt magnetization. So what is shown here is the cobalt magnetization that is going down. And in platinum, due to the heavier element, the spin orbit coupling is more effective. So then by spin flip scattering, also majority type electrons may contribute. And in my talk, in the following, I will show one example for each of these two mechanisms I just tried to explain. And I will use, or I will show how antiferromagnetic materials in these mechanisms play an important role. The first will be to show the optically induced demagnetization as presented before, how this can be accelerated by antiferromagnetism in one of the layers. And we will explain this by the exchange of transient spin currents, so by this non-local mechanism as before. And the second example is of this ultra-fast oyster effect I just showed, and how in antiferromagnetic manganese this can lead to a very short-lived transient ferromagnetic state. Why are antiferromagnets important? So in the moment, there's a certain higher interest into antiferromagnetic materials in spintronics because they are insensitive to fields. There's no disturbing dipolar interactions, so one can pack them closer together if information is coded in antiferromagnetic spin structures. Important for the ultrafast is that no net angular momentum has to be changed or dissipated or transferred to change the magnetization properties of an antiferromagnet. And also important is that there's a much larger choice of antiferromagnetic materials than of ferromagnetic materials. Now, before starting with the actual results, I just want to very briefly introduce the methods, because they might not be familiar to everyone in the audience. So we get element resolved magnetic information from the so-called XMCD effect. That means X-ray magnetic circular dichroism. And that is in the absorption of soft X-rays. Resonant absorption of soft X-rays happens by the excitation of electrons from a core level. In our case, it is the 2p 3½ level, into the unoccupied states just above the Fermi energy that in a metallic ferromagnet may look like this. We have a different density of states for the minority electrons than for the majority electrons. And by using circularly polarized light for the excitation, the probability for having a transition of the down spin and the up spin is different for one helicity and the other helicity. And then by changing the helicity, the different probability of these transitions is like probed by the different amount of empty states available. And that leads to a different absorption in a spectrum. So this is now the photon energy that can be swept in a synchrotron light source across the absorption edge. This is the absorption that is shown on the right-hand sketch, the L3. And then for the different circular polarizations, there's a different amount of absorption. And this can be used to element selectively probe the properties. So this shows now a sample that contains nickel and cobalt separated by a copper spacer layer, because the binding energies of the core levels is element specific and is higher for nickel than tuning to the binding energy of the nickel 2p 3½ one gets information on the nickel, and here one gets information on the cobalt. Now we have to do this at a synchrotron. Now we need short synchrotron light pulses to measure ultra-fast processes. And we do the experiments at the synchrotron light source BESI 2, that is here in Berlin also. And to have ultra-fast synchrotron pulses, one has to play special tricks, and the people of BESI provide this. They have set up an experiment that looks like this. So normally the electron bunches that circulate in the storage ring of a synchrotron light source have a temporal length of like 50 picoseconds. And for the ultra-fast experiments, this is not short enough. And then what one is doing is to overlap a laser. So this is a very short laser pulse. Laser pulses can be made shorter than 100 femtoseconds nowadays. And the laser pulse is split into two parts. One is overlapped with the electron bunches. So the electrons travel here around in a circle and then come back after one turn to interact with the electrons. And the second is used as a pump excitation in the experiment with a variable delay line. And this part is now shown magnified here. Here the laser pulse, the blue thing is the electron bunch. So there's electron bunches coming with like 500 megahertz. So every 2 nanoseconds, there's the next electron bunch. And this is an undulator to get the electrons on a kind of curved trajectory. And the photon pulse now interacts with the electrons and slices out. That's why they call it slicing. Like in a loaf of bread, when you slice out one slice in the middle, and displaces it to the sides. So the red part is now the displaced electrons in the middle, and they have the length of the laser pulse. And in the next undulator, they emit synchrotron radiation, and then there's a blockage here to only accept the synchrotron radiation of this red side wings of the sliced out electrons and not of the main pulse. And that is much shorter when it travels here. That has the same length as the laser. The disadvantage is that the intensity is much less because firstly, the slicing happens only with 6 kilohertz and the punches come with 500 megahertz. And then it's also by slicing out one slice of 100 femtoseconds out of 50 picoseconds, you lose again a few orders of magnitude. So in the brilliance, this is a loss of like 7 or 8 orders of magnitude. So the experiments are a bit difficult, and one has to collect enough statistics to get a solid statement from the data later. The samples in the first part I want to show are composed of a bilayer of a ferromagnetic material that is cobalt or nickel. Cobalt has an in-plane magnetization when grown on copper 001, nickel an out-of-plane magnetization. And they sit on top of a nickel manganese that is an antiferromagnet that can align its spin axis, its the L vector, either in the plane or out of plane. That is why these arrows are shown here like this angled. And in the end, it is kept by 20 monolayer of copper to prevent oxidation when we take the samples to the synchrotron light source. And the experiment looks like this. Now we have here the nickel manganese, the cobalt, and the cap layer that we pump the sample with the 800 nanometer that is in the near infrared and make the electronic transitions to demagnetize the magnetization of the cobalt layer. And we probe the magnetization by reflecting synchrotron light. So then also some light is absorbed. The same XMCD, magnetic circular dichroism mechanism, applies. But we have now a combined scattering and absorption experiment. So we have to tune the photon energy of the probing photons, this roughly 1.6 nanometer here, across the resonance of the cobalt L3 absorption. And we have to tune the angle under which we scatter, and both is done to have a maximum. So this shows the difference in the reflected intensity now as a function of the scattering angle for opposite magnetization of the sample that is reversed with a magnetic field, and the circular polarization helicity is kept constant. And this difference is then, this is a static measurement, the magnetic signal we get, and by optimizing angle and photon energy for the figure of merit of the measurements, the measurement conditions are indicated by these red lines here. And the time resolution comes from a pump probe experiment. So first the infrared pulse at 800 nanometer is going to the sample in nearly the same direction as the following X-ray pulse. And the X-ray pulse is then reflected in a specular scattering experiment into a detector. And by varying the distance between the infrared pulse and the X-ray pulse, the time resolution can be measured. And this is repeated 100 of million times or so to get enough statistics. Then the delay time is changed by 1 step, and again 100 million pulses are collected. And the result for cobalt, also what I forgot to mention is that the idea is to measure the demagnetization of the cobalt above and below the Néel temperature, that is the antiferromagnetic ordering temperature of the antiferromagnetic nickel manganese material, to elucidate the effect of the antiferromagnetic order in the nickel manganese on the cobalt. So first I show you the demagnetization traces of cobalt at 390 Kelvin. That is where the nickel manganese is not antiferromagnetically ordered, but just disordered or paramagnetic. And for different fluences of the pump pulse, one gets these traces, and that is what is known from other samples of the demagnetization. So increasing the fluence, the demagnetization amplitude increases, And for higher demagnetization amplitude, it takes longer time to remagnetize. And the demagnetization times are on the typical length scale, like I have shown you in the introduction, of 100, 200 femtoseconds or so. Now, the interesting question is, what happens if we go down in temperature to have the nickel-manganese layer antiferromagnetic? And this is shown now for the sample with the cobalt ferromagnetic layer. And you see that comparing the two temperatures, the time constant of the demagnetization, that for the analysis in the following slides, we just fit with the exponential phenomenologically to extract a time constant. The exponential time constant of demagnetization here is faster. So the blue curve decays faster to roughly the same demagnetization amplitude here. In nickel, since nickel has a lower Curie temperature, the start magnetization that is represented here by the XMCD in reflectivity is already higher at 80 Kelvin, because at 360 Kelvin we come already some way to the Curie temperature of the nickel film. That is also makes the demagnetization amplitude a bit different. And okay, with the bare eye, it is difficult to tell, but I can promise you that the demagnetization time here is also faster than here. So now we evaluate the demagnetization time constant and the demagnetization amplitude for cobalt and nickel samples as a function of the fluence of the exciting laser pulse. So this is now the fluence of the laser pulse. This is the demagnetization amplitude. So that is like shown before, the curves for the red data points I've shown you 2 slides ago. And there's not much difference between the two temperatures. So the blue is the cold and the red is the warm temperature, like in the water tap. And here I show the time constant of demagnetization. And we had seen these 2 data points before. So now this is for cobalt. The solid symbols are for the cobalt samples and the open symbols for the nickel samples. We have a clearly faster demagnetization at the lower temperature when the nickel manganese is antiferromagnetically ordered. And for the nickel sample, we also have this faster demagnetization here than here. Now, just to make sure that the temperature doesn't affect or that the temperature effect directly on the ferromagnet can be excluded, we now plot this quantity as a function of this quantity and not as the function of the laser fluence anymore, because a higher demagnetization amplitude, so a higher amount of demagnetization, means more angular momentum has to be dissipated, and that may take a longer time. So you see this general increase here. But even if we plot the time constant as a function of the demagnetization of the sample, we have in this region a clear difference in the cobalt sample, that is where the solid lines are, of acceleration by the antiferromagnet. In nickel, we don't have really overlapping data, but we have only these 2 data points and these 2 data points. I explained to you that the intensity in the measurements is really low and that the beam time didn't allow more data points. But one can see already, or one can guess that while having more data points, there would be maybe an even bigger difference here. And now our interpretation, and this was done together with Peter Oppener, a theoretician from Uppsala. I told you about this first paper on the transient spin currents. The explanation is also with the non-local mechanism of transient superdiffusive spin currents that go into an antiferromagnet. So the sketch is just that would be the ferromagnet and the blue would be the antiferromagnet. Now we have to concentrate a little. So we have the spin polarized current from the ferromagnet going into the antiferromagnet, like in the explanation before when they went into an aluminum layer. And this spin polarized current is majority type. Now what does the antiferromagnet do there? If the antiferromagnet is antiferromagnetically ordered and we have majority type electrons going into the collinear spin structure of the antiferromagnet, that is like this and this, then the spin current can enter with a higher transmission probability than for disordered spins, where the spins above the inhale temperature point in any directions. And that makes a more effective sink for dissipation of angular momentum in the case of a collinearly ordered antiferromagnet. So that is one mechanism that contributes to the dissipation and makes it faster. The other is that also a spin current from the antiferromagnet penetrates into the ferromagnet. So the laser, the exciting laser, goes through both and excites both of them. And this spin current will be unpolarized even if the antiferromagnet is ferromagnetically ordered, because we have as many electrons with a spin like this as with this. But it is collinearly ordered, and when this spin current, unpolarized but collinearly ordered, goes into the ferromagnet, then the minority type electrons can penetrate into the ferromagnet with a higher probability than the majority that will be more reflected because of the available number of states they can go into. And this minority current that goes into the ferromagnet also dissipates angular momentum, or it brings the opposite angular momentum for the dissipation, and also helps for a faster demagnetization of the ferromagnet. While when the antiferromagnet is disordered, then the spins are in any direction and this mechanism is less effective. Okay, now we come to the second part of the talk. And the oyster effect I showed you in the beginning originally was proposed in this paper for antiferromagnets. And in a pure antiferromagnetic material, let's assume manganese, we have one species that has, where in this sketch, the up spins would be the minority spins and the down spins would be the majority. And we have an oppositely oriented species with oppositely oriented moments, where the up arrows are the majority and the down arrows are the minority. Now the colored areas are always the occupied ones. This refers to, this is an energy axis on the right, and this would be the Fermi energy here. Now the oyster effect, this interside spin transfer, would be without spin flips. So no spin flips are required in this mechanism. That makes it so fast, because spin flips always require a couple of hundred femtoseconds. The majority electrons from this atom might be transferred optically into the unoccupied states of the same spin direction, which are the minority type then in this atom, and vice versa. And the result would then look like this. And in a pure antiferromagnet, that would just help for a very fast demagnetization, because the situation would be symmetric in both. So this filling and this filling are equivalent. And the demagnetization you see now, the occupied part of this spin and this spin is more equal, and the magnetic moment would go down. Now in our sample that is shown here, we interleave manganese, 3 monolayers, so very thin. It's epitaxially grown again on copper 001. And by medium energy electron diffraction, one can really control the thickness of this on the single atomic level. We interleave manganese with cobalt layers. And the cobalt layers are ferromagnetically ordered, or we orient them ferromagnetically with a field, and that breaks the symmetry of the situation shown in the previous sketch. And we kept this also to transport it to the synchrotron and then measure, like explained in the first example, with the resonant reflectivity in the soft X-ray regime. And we get now the element resolved information from tuning the X-rays to the cobalt absorption edge or to the manganese absorption edge. The result is shown here for cobalt and manganese. Both sketches, both graphs show time traces. Here's the delay time between the pump excitation that happens here at 0 and the probe pulse from the femtoslicing beamline. And in cobalt, we just see a demagnetization as before on similar time scales. This is the magnetic contrast in absolute numbers, is in percent of the XMCD. In manganese, we don't see an XMCD, at least not in the slicing experiment, at negative times. That means before the pump pulse arrives and excites the sample. But we see a clear peak very shortly or immediately in our time resolution, immediately with the occurrence of the pump pulse that then disappears. And it's not so small, also considering that not every manganese receives the photon in the pump pulse. So we have now a ferromagnetic signal, an XMCD signal here in the manganese, excited by this optical pulse. And that this is indeed due to the Oyster mechanism comes from theoretical calculations here. And the theoretical calculations are done also by Sangeeta Sharma and colleagues in the Max Born Institute. And here they show on a time trace, again in femtoseconds, the magnetizations or the magnetic moments in Bohr magneton of cobalt layers and manganese. So they calculated only 2 monolayers of manganese on top of 3 monolayers of cobalt. Our samples are a little bit different, but qualitatively the effect can be explained from here. And the manganese 1, that is the manganese layer that is in contact directly with the cobalt, has an opposite magnetic moment than the manganese 2, that are the 2 manganese layers. But you see already that this situation is asymmetric. This has a higher negative moment than this has a positive moment. And that is then what leads to this transient ferromagnetic state. The mechanism can be seen here. It's mainly the manganese 1. The manganese 1 changes the sign, and then the 2 manganese layers have their moments aligned in the same direction, leading to this transient state. And in electronic density of states, this is shown here. The gray curve is the total density of states for spin up and spin down, which in manganese 1 would be the minority and the majority. And the
Professor,
yes,
you have 3 minutes. I'm extremely sorry to interrupt you.
Yes. Okay, I'm 1 slide before the conclusion. No problem.
That's fantastic. I'm sorry for that.
Yes, no problem. So we filled states after a certain time are shown here, and you see now that much of these minority unoccupied states are filled transiently after a few femtoseconds only. And they come from the manganese atoms or the cobalt atoms from the other manganese layer and also from the cobalt. And that leads to this very fast, so in the calculation one sees how fast this can be on 10 femtoseconds of this transient ferromagnetic state we see. Yeah, and now I can conclude. So the conclusions are that firstly, we know that transient spin currents do play a role. There was a still ongoing debate in the laser-induced demagnetization process, and that furthermore, metallic antiferromagnets can assist in the dissipation of angular momentum for the ultra-fast demagnetization processes. And in the second example, we have seen that a transient ferromagnetic state can be excited in antiferromagnetic manganese by this ultra-fast optically induced intersite spin transfer. For this mechanism, no spin-orbit coupling is needed. It is ultra-fast because no spin has to flip to get this. They have just to transfer from one atom to the next. And our experimental timescale seems to be limited in the moment by the length of the laser pulse. And this is also discussed, at least by theoreticians, as a source of an ultra-fast magnetoresistive response in this manganese layers. So I should not stop without acknowledging the contribution of everyone contributing to this. That is in my own group in Berlin. It is main contributions to the first example was by Ivar Kumberg and to the second by Evangelos Golias, a PhD student and a postdoc. And then Rahel Hosseinifa, Ismet Gelen, Jendrik Gördes, Taukir Shinwari are all PhD students. Sangeeta Thakur is a postdoc, and Quentin Guillet and Karl Frischmuth were master students. In the Max Born Institute, that was the theory part by Sangeeta Sharma and Kate Dewhurst. On the second part, and the theory on the first part was from Peter Oppener in Uppsala. And the experiments at the Helmholtz Center Berlin were done with Nico Pontius and Christian Schüssler-Langeheine. And this was our group in last summer. And I thank you very much for your attention.
Thank you very much, Professor. It was an incredible talk. I have some experience of working with XMCD with you, I still remember.
Yes.
Understanding the majority and minority spins. We have quickly one question posted by Shamla SK. I will read out the question, Professor.
Mm-hmm.
Will there be any influence effect of exchange bias effect in cobalt nickel barrier?
Yes, yeah, that is a valid question. Actually, in the second example, in this sample, the manganese is antiferromagnetically ordered, but we do not yet see exchange bias effect. So the exchange bias effect, the blocking temperature for exchange bias is not always equal to the Néel temperature of antiferromagnetic order, because for exchange bias, besides antiferromagnetic order, also the pinning of the magnetic moments is necessary. And this 3 monolayer sample is too thin to have a sizable exchange bias effect here. So one can imagine this as if all the moments in the manganese would reverse along with the cobalt moments. In the first sample, in these samples, wait, why is it coming? No. Here there would be exchange bias, but we didn't field cool the sample. So here the nickel manganese layer is thick enough to introduce exchange bias. But in our case, we did not field cool the samples, and well, we cooled them in the synchrotron experiment, but the exchange bias in this case, let me think. No, it was relatively small, and for our experiments, for the reversal of the magnetization direction, we were fully saturating the cobalt or the nickel layers in the opposite direction. And the interesting question would be how the exchange bias effect would affect the demagnetization. That would be your question, I guess. Here it is more difficult to do the experiment. That would be indeed interesting. So we had to reverse the magnetization at each step to get the XMCD out. And for the exchange bias effect, one would need to reverse the helicity of the light. That in this beamline is a bigger effort and cannot be done quickly. That needs in the time scale of 10 minutes or so.
Professor, I have a small question. It's just a clarification. So you stated that the spin currents do have a role in the demagnetization process.
Sorry, you said the spin currents play a role for the demagnetization
process.
Yes. Yeah.
So my question is, when you have a situation there, you have an antiferromagnetic state where you have a spin up, and spin down. You stated that the lower spin population becomes a majority. Am I right? The spin, I think the spin up populate becomes a majority spins.
You mean in this explanation here, right?
No, I'm no.
Or general.
No. That my doubt is when you have this spin currents involved in the demagnetization process, or I'll put it in a simple way. When you do the XMCT measurements, is it possible to calculate quantitatively the spin up population and the spin down population?
What you measure in an XMCT experiment is the number of unoccupied states for each spin direction. And indeed, there have been some experiments where this is spectrally resolved. So it cannot measure the spin currents because this is on average not enough. This is not changing really the occupation of the states. What is changing the occupation is the Oyster mechanism, like this here. So this would change the occupation here. And the general XMCD measures the white part of the density of states. So compares this white part to this white part, or here wait, now my mouse pointer has disappeared. This white part to this white part. And there have been experiments. We have started experiments in Stefan Eisepitz's group. They have done experiments where this is spectrally resolved to prove, or they have published it to prove the effect of the filling here. But for your question, with the currents, with the spin currents, that would not significantly alter the density of states, except for what is already measured in the experiment. So you could not prove or disprove the mechanism of the spin currents by a simple XMCD time resolved measurement.
Sir, is it possible in your instrument to change the helicity of the X-rays, incoming X-rays, and measure?
Yes, the helicity can be changed in this beamline, but not very quickly, because there has to be some adjustments again to the experiment. And as I mentioned before, it will take a few minutes to change the helicity. So the experiment can be repeated with a different helicity. But for getting a zero line of the XMCD, it is necessary to flip the sample magnetization at each measurement point, like every 10 seconds or so. And this cannot be done with the helicity.
Oh, okay. Okay, thank you, Professor. Thank you for your presentation. There are no questions. We can just close this session.
Okay, yes, thank you very much.
Thank you very much, Professor, for accepting. I see you. Thank you. Thank you so much, Professor. The next distinguished speaker is Professor Kalabharan Maiti. He is the Dean of Natural Sciences, Faculty of Tata Institute of Fundamental Research. So his area of research institute includes topological insulators, whale semi-metal, superconductivity, correlated electron systems, magnetism and Kondo phenomena, properties of surface and interfaces, electronic structures, thin films and multi-layers, semiconductor nanostructures, and DMS, that is dilute magnetic semiconductors. So he has achieved several awards and achievements. He has received the P.K. Iyengar Memorial Award for Excellence in Experimental Physics, which is one of the highly prestigious award, I would rather say. He is a fellow of the Indian National Science Academy. He is J.C. Bose Fellowship in 2014, fellow of National Science Academy in 2012. He is Swanti Swarup Bhatnagar Awardee. That's very specific to mention. It's one of the greatest award given to any scientist in India. And he has also received other awards: Rajiv Goyal Prize for Young Scientist in Physics, Birla Science Prize in Physics, Swarna Jayanti Fellowship. He has got the title of Honorary DAT Advisor for Outstanding Commitment and Leadership in Indo-German Relations and Education, awarded by President of the Republic of Germany. He has a very huge citations of 3797 and H index of 32. Welcome, Professor. Now the stage is set for you for the presentation. Thank you very much.
Thank you for your kind introduction. Okay, okay, I'll share the screen now. You can see the.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay, so first of all, thanks, many thanks, the chairman for your kind introduction, and also the organizers for inviting me to this interesting meeting. I would have really liked to visit SRM. It's a very nice place, and I think I've been there several times, but somehow anyway we are doing well in this pandemic time. I think this online things. Of course, it has some advantage that we can talk from anywhere, but we miss out this personal presence of people there. Today, I'll be giving a brief introduction about our work on identifying local excitons in silicon germanium inverted quantum hertz embedded in silicon. So this, as you have seen, this semiconductor physics, although we have certain interest in this kind of field, but this is the first talk of the kind that I'm giving today. So, and the semiconductor industry, of course, in terms of physics as well as technology, it has grown up so much. I don't think it is easy to really give a brief summary involving the physics of silicon. So I'll try my best what we have been doing for the last few years. Okay. As you know that now the digital industry like data storage, data transmission has become, I think, one of the most important aspect of the technology or advances in technology that people have been thinking. I mean, we are producing so much of data. We need to really learn how to store them, how to transmit them, and so on. So in this regard, there is this famous Moore's law. So he's proposed, I mean, in one of the article, so he just mentioned that the number of transistors that can be packed into a given unit of space will roughly double in every 2 years, like 1.5 years to 2 years, something like that. Interestingly, if we look at this picture I have got from Wikipedia, you can see that it almost holds good for many decades. I mean, it's almost linearly going up. So now the advances in silicon integrated circuit allow us to really put micro electronic devices. I mean, in a single chip, you can put about 2 billion transistors and so on. But as we know that with the advancement in technology as well as nanoscience, we are trying to make the transistors as small as possible. But there is a limit, of course. So we know that we cannot really go down, even if we wish to go down further. So then there are thinking of new technologies that could be adopted. One of them is optoelectronics, of course, so that you can, a lot of people have been working on spintronics, like use charge and spin degrees of freedom to store data. Quantum computation is another thing that has been coming up well. So today I'll try to focus on this optoelectronic properties. So this is another field which has been tried for many years, but I don't think, I mean, it's successful yet. So the main idea has been that, as you know, the silicon actually has been ruling this whole digital industry because it's highly abundant and it has a right kind of band gap, which is important for digital industry. Like you don't have, you know, leakage and so on, so you can make transistors and so on. But the problem with silicon compared to other semiconductors that you can see here, so I have shown a band structure. I mean, these are, you can find anywhere, many people they have studied. So if you look at the band structure of silicon, so this is the valence band, these lines. Valence band means that the electronic states which are occupied by electrons in a solid. So usually the top of the band is the topmost band is called the valence band, and the bottommost unoccupied band is called the conduction. Now, if you have a metal, of course, these two are overlapping with each other, and in a semiconductor, there is a gap. Now, as you know that the optical excitation is, of course, all kinds of perturbations that we have there. Energy and momentum is conserved. So when you are exciting a system or electron using a photon pulse, you know that the photon has negligible momentum. So basically, you are having a transition from one of the occupied level to the unoccupied level. Now, because the top of the valence band and bottom of conduction band at a different momentum, so you cannot really excite an electron from one K point directly above it, where the gap is of the order of band gap. Okay, so here you can see that you need to change the momentum somehow to have a excitation across the gap. These kind of semiconductors are called indirect band gap semiconductor. Of course, germanium is a direct band gap semiconductor, gallium arsenide another. So here the band gap is much larger. Here it is much smaller than silicon. And of course, the abundance and other things, other concerns are there. People have been trying to find new semiconductors which could be used for this kind of technology. But if we are able to make silicon a direct band gap semiconductor, which is something like called type 1 semiconductor, there is nothing like that. And then, of course, we can really go ahead with the advanced technology that we have in place for the future. So that's the reason there are a lot of effort have been put up to make silicon a direct band gap semiconductor. So you can see that to bring these top of the valence band and bottom of conduction band to the same momentum, you require some kind of a overall change in the lattice. So people have been trying to introduce strain, people have been trying to introduce nanostructure inside this and so on. So there are a lot of efforts have been happening. So today I'll try to focus one of such kind of effort that I've been part of it. So this essentially, maybe I can just say a small story like how it has happened for me, because Professor Milan Sannal from SINP, he has been working on this kind of system extensively for quite some time. So we both were attending a meeting in Delhi in one of this project evaluation meeting and so on. And then we were having a evening walk. And so Professor Sannal was extremely excited that they have made a very nice kind of silicon where they have put inverted quantum hearts and the behavior looks like type 1 semiconductor. So that's the point. Then I thought that it's an interesting system to look at using electron spectroscopy. So that's the way the whole program on silicon inverted quantum heart kind of system that I have started with. So the kind of things that he was talking about is given here. So he has published a couple of papers on this, I think quite a few. So I'll refer here two papers. So here, what they have done, they use molecular beam epitaxy. The details is given here. So you take a silicon wafer and then clean it extremely well. And then what you do is that you can put a silicon buffer layer and then put deposit germanium and silicon alternately. And then you can put a cap layer. So they have done this cross-sectional TM image, and they find that so this bright part is the silicon and this somewhat dark part is the germanium. And you can see that it forms nice kind of a inverted heart. So most of the time when we grow nano dots or so what we do is that we deposit small amount of material on a substrate and they form a kind of a heart kind of structure or balls or ellipsoids kind of different kind of shape that you can generate on a surface. So here, actually, the interesting thing is that these hearts are embedded inside the material. So somehow it has diffused inside the material and formed this inverted heart. And there are several of them that has been formed. And you can actually study them well. What they have found is that if you look at the photoluminescence, so it shows strong photoluminescence at low temperature, and you increase temperature, the intensity goes down. At about 100 Kelvin or so, it dies down completely. Now you can plot the intensity of this photoluminescence as a function of temperature, and it shows like this kind of behavior. So they have fitted it with various kind of models, and they see that there are two energies, excitation energy or activation energy required to fit this curve, which is shown here. One is 7 milli-electron volt, another is 49 milli-electron volt. The 7 milli-electron volt is mostly related to the base area. So if I assume that this is the inverted quantum Hart, so the confinement effect at the base area is much weaker compared to the tip. So here the excitation requires something like 7 milli-electron volt, but the excitation required or activation energy required is about 49 milli-electron volt. The interesting thing is that if you do the elemental analysis, you find that around the tip region, so the distribution of germanium is like that. So this inverted Hart is not a purely germanium region. It's a silicon germanium alloy. So you have everywhere silicon, and somewhere you have a Hart kind of structure, which is an alloy of silicon germanium. So if you are at the tip, then the distribution of germanium like this. So maximum amount of germanium is here, and then it goes at the sides. But if you are around the other region of this Hart, so you see that it's an annular kind of region where the germanium is actually more dominant at the edges, and central region is less germanium. But anyway, what you can see is that there is a distribution of silicon germanium relative ratio, elemental ratio in the whole quantum Hart, which is showing interesting properties. Now, if you fit these photoluminations, so which this is the reference. So you can see that there are three distinct features. So corresponding to three different energies, 0.81 electron volt, 0.87 and 0.92. So you have three excitons forming in this. So they are actually of different energy, giving distinct feature, and there is a temperature dependence. The interesting thing is that if you change the temperature, the energy position of these excitons doesn't change. So they are almost flat. The intensity goes down, of course, if you increase temperature. And you can actually try to find out the dependence of intensity as a function of excitation power, and it's almost linearly dependent on the excitation power. So there are various kind of studies that they have done. All these kind of properties somehow indicate that the properties of these excitons they are not really highly mobile like that. They are local excitons. And this is a signature of a type 1 kind of behavior in a system. So this is the starting point where we thought that we can use spectroscopy to find out if they are really local. And so that would give an understanding like whether the silicon behavior is really a type 1 or something else. So that was basically the starting point. So whether they are really a local exciton. So the summary of this initial part is that so silicon germanium inverted quantum Hart seems to make the system like a type 1 semiconductor. And the interesting thing, there have been a lot of studies, of course. So the interesting thing is that if you incorporate germanium in silicon, it introduces large strain. And so there have been predictions that there can be, this strain can lead to enhancement of hole mobility. It can change the band structure, bringing it towards the type 1 kind of things. And there is a large shift in photoluminescence emission peak. So that also is another signature, like it could be like a type 1. So we have, for our studies, we have prepared one kind of, one type of such systems. So you clean silicon. This is a detailed preparation, sample preparation method. So you clean the silicon wafer using typical method and hydrogen fluoride etching and so on. Then anneal in ultra-high vacuum at around 900 degrees centigrade for about 24 hours or so. Then you heat up again at a much higher temperature. So once the silicon is clean, then you can deposit a silicon buffer layer, which is of the order of 100 nanometer at around 750 degrees centigrade. These are all done using a MBE system at Saha Institute of Nuclear Physics, SINP. And then one can grow successively 1.7 nanometer germanium, 8 nanometer silicon, and like that. And so for our kind of studies, what we have done is that we have this buffer layer, and then grow this 1.7 nanometer germanium. On top of that, we put a weighting layer of germanium, so which is very small. So that's the system that can be used for spectroscopy, and this is done at 420 degrees centigrade. This has been characterized, and we find that in this system, the inverted quantum hearts that form has a dimension of this. So the base area is of the order of 13.3 nanometer, and the depth is 6.6 nanometer. So this kind of quantum hearts, actually, these are, I mean, many other people have studied, but usually these inverted quantum hearts are bigger in size. So we have seen that if the size can be reduced to this kind of size, the behavior goes closer to the type 1. Now, let me give you, so this is the spectrometer that we have used at TIFR. I'm happy to say that you have seen the picture maybe in my talks earlier. So, but I'm happy to flash it again. So this is a spectrometer built using Indian companies and facilities. We have designed and fabricated it. Of course, the detectors, pumps, and so on are imported from abroad. And the good thing about this is that we can do experiment at extremely high resolution. So far, I mean, that's the best kind of resolution that is found in most of the high resolution labs. So the energy resolution close to 1 millivolt if you are doing RPS, and if you are doing XPS, which is about 300 millivolt. This is the kind of resolution that you get if you are using this XPS using a laboratory source, monochromatic laboratories. But if you go to synchrotron, of course, you can get even better resolution. But these all experiments are done using these laboratory facilities. Okay. Now, photo emission, as you know, that the electrons, of course, the light can penetrate the system quite a bit, but the electron has mean free path, which is quite small. So this is the universal curve that often people refer. This one is published in 1979. So, I mean, it's still, people use this kind of curve. So, which shows roughly the behavior of electrons' escape depth. So, you can see that the electron can escape from the material only about 6 angstrom or so if you are doing experiment between 40 to 100 electron volt. One can increase this escape depth if you reduce the energy, or if you increase the energy like high energy and so on. So we are doing aluminum K alpha source, which is somewhere here. So the effective escape depth is close to 15 to 20 angstrom or so. So it's basically limited to the top few layers of the system that we are studying. So we have actually looked at this using various material. For example, if you use a bismuth palladium and so on, we see that this curve actually looks similar. These are our results. You can use vanadates and so on, and we see that actually this curve. So, I mean, the minima can shift somewhere towards lower energy, depending on the kind of material that you are using. Like if you are using a good metal, that can go to much lower energy because of the excitation possible across the Fermi level. But the numbers that we see for the escape depth is quite small. So at aluminum K alpha is about 20 angstrom or so. So you can see that it's quite surface sensitive. So we actually wanted to exploit this kind of property. So this is the system that we have fabricated using MBE. And if you expand this, it looks like this. Okay. So our plan was this, that you have this quantum heart, remove this top layer by using sputtering, and then we can do a controlled sputtering and expose different parts of the quantum heart and do the experiment. That was the idea. Okay. So first we have we use this argon sputtering. So at low energy, the energy of the sputtering was always below 1 keV or so. So, and then we tried to sputter and anneal the system, and then study the exposed surface using TEM and cross-sectional, particularly. So, which is, and then, so that way we have confirmed the different level that we have exposed. So, for example, you remove this layer, top layer, and see what is there. Do the photo emission and see the layer, characterize the layer using TEM like that. So that way we have exposed different kinds of stages. So if you are at S10, means if you have sputtered, I mean, after removal of the top layer, so if you sputter for 10 minutes, you actually expose to the waiting layer, which is this. And then if you sputter for 17 minutes, it's you go to the bottom of the waiting layer. 42 minutes, this S2 is sputtering time. And this number actually tells you the how long we have sputtered. So if you do it for 42 minutes, it's like this. 72 minutes, it's like this. 100 minutes, it's here. You are close to the tip of this. Now, the interesting thing is that you have to see that the electrons which are localized or confined within this nanostructure. So this confinement effect also changes. For example, when you are here, the electrons are confined within this nanostructure and they also can move because of the waiting layer. But if you remove the waiting layer, the confinement is actually limited within this. And now you remove further, you see that you are making the size of this nanostructure much smaller. Okay? So that's the interesting part of this. Now let's look at the silicon 2p kind of spectrum. So core level spectrum. So here, I think I have to move a little faster anyway. So you can see that at different level like this S10 to S100 or S240, S240 is actually you have removed completely the nanostructure. You can see that 2p actually peak position changes significantly on this. So S10 is this black curve. Now you go to S17, the red curve, it shifts to lower binding energy. S42, it's somewhere at similar position. S72, it's at lowest energy. Then again, it starts going to higher binding energy. Now, if you are moving towards lower binding energy, it means that knocking out electron becomes easier, isn't it? The binding energy is lower means that. So that means that the silicon actually is losing its local potential. This can happen when you have a silicon germanium alloy. So there is a finite hybridization, and so silicon becomes more negative. And so the binding energy reduces. But of course, when you are knocking out more and more, so the amount of silicon that you have, which is hybridized with germanium, which we mark as silicon 2, reduces, and you are exposing more the pure silicon. That way, then it goes towards the higher binding energy, which is corresponding to the silicon 2p in pure silicon. So it shows, nicely how the silicon core level actually is reflecting the hybridization with germanium and so on. So this electronic structure reflects basically at different levels. That is very clear from this. Now let's look at the germanium spectrum. So this is germanium 3D. You can see that germanium 3D also shows interesting kind of a dependence. Now at different level. Now if I plot the binding energy, so the red one is the germanium 3D and this is silicon 2p. Initially, this germanium and silicon actually shifts in same direction. You can see that this is the S10 and the S17 is lower binding energy. It shifts in the same direction. So if you have core level shift in the same direction for both the elements, constituent elements, it means that the Fermi level has shifted because there is if there is a hybridization induced effect, then the binding energy of one will reduce, another will increase. Okay? Because of the effective potential change to make everything charge neutral. So here, since it's shifting in the same direction, so it means that there is a small shift in the Fermi level. But after that, we see that they're actually shifting in opposite direction. That shows the hybridization effect. And also how this silicon, the relative numbers, amount available for photoemission reflects the binding energies. For germanium, we can see that they are almost at similar kind of energy if you go beyond this level. So if you are really linked here, and germanium is essentially available within this structure, so all the behavior is quite similar. So this shows, so far so good. The most important, interesting thing happens here. If we go this germanium 3D, if we look at carefully the lower binding energy region, you see that there are many peaks which are there in photoemission spectrum. This is very unusual and never has been seen in any of the germanium-based systems. So we were quite surprised to see this and try to find out why these peaks are coming. So absolutely, silicon cannot give this kind of features. So one of the things that we thought that you see our sample is mounted like this. So this is the silicon wafer on which the sample is made. This is 10 millimeter by 10 millimeter. And these are actually mounted on the sample holder with tantalum strips at the corner. So this distance is extremely large. You can see the 10 mm. So this is 10√2. So you can see that this distance is huge. And our X-ray spot is about 1 millimeter. So which is at the center. Now you can see that, I mean, there is no way that tantalum can actually contribute, but we know that the tantalum core contribution comes in this region. So just to check whether this tantalum is really playing a role or not, because we are actually sputtering it, so some of the tantalum can actually fly in there and give the peak. So this is characterization. We can see that tantalum 4D is the most intense peak if you have from photoemission cross section. And you can see that when tantalum 4D is there, you also see a peak which is quite intense for tantalum 4F. But in these kind of systems, so there is no tantalum 4D. So still you have intense peaks here. So this shows that it's probably not from tantalum. Not only that, when you have not sputter, then also like after the initial preparation, this S10 level. So it shows this kind of peak. Okay, so this shows that actually this could not be linked to tantalum 4F. Okay, so this is one interesting thing that we observe. Not only that, if it is a tantalum really, so tantalum 4F, at different location, you couldn't have peak at different energies. They are so much shifted. So this shows that there is something else which is happening. Now, if we really try to fit these peaks with similar kind of germanium 3D spin orbit split peaks, you can see that they can be simulated there with that. So it looks like that there are 4 features coming up which probably are linked to this germanium 3D photo emission. Because if the germanium 3D peak is not there, then these features are also not there. Okay? So we have analyzed and find that actually there are peaks. So these 2 peaks are most intense when you are at the middle part of the quantum heart. If you are at the top, like if you just remove the weighting layer, then you have this peak, and this peak of course comes remains there when you are within the quantum heart and you are at the tip also. So this tells us actually to look at the process much more carefully. So this is our conclusion that this must be related to the germanium 3D core level. So now I'll give a brief introduction, the basics of photoelectron spectroscopy, what is happening. So I'll try to go a little quickly because I think I have 28 minutes I have already spent on this. As you know, photoemission spectroscopy is essentially based on photoelectric effect. So, I mean, Einstein got Nobel Prize. There are other 2 Nobel Prizes on this similar kind of techniques. So, anyway, so here what happens is that you have a sample, you radiate with the light, and if the energy of photon is strong enough or high enough that the electron can overcome the work function, which is of the order of 4 electron volt. So it comes out of the material, and you put a detector and detect the momentum, energy, and spin of the electrons. Use various conservation rules associated to this quantum mechanical process, and use that information to really learn about the system that the electron has left behind. So I'm not going into the details of this. So the main thing which I want to say relevant for this study is that, so assume that you have this material which has n electrons, you perturb by a photon, so which has an energy h nu. A electron comes out which is detected by the detector, leaving behind n minus 1 electron system here inside the sample. And so this excitation spectrum looks like that because of the absorption of energy. Now, any electron which has energy higher than this vacuum level, you detect in this detector and associate that property to the n-1 particle system that it has left behind. The important thing is that since this photo excitation process is very fast, happens in the order of time scale like attosecond or so, you essentially probe the local spectral function at an extremely fast time scale. So it's a kind of a snapshot of the electronic structure in an attosecond time scale. In this time scale, the lattice and all other like electron-electron interactions and so on, they don't have enough time to react. So you get a local electronic structure or spectral function. And of course, the orbital, it's sensitive to the orbital character and surface sensitivity, as I have talked earlier. Now, the process is even more complex. So let's think about it a little more about it. So assume that, so if you have any question, please stop me. I'll try to, because this part is important to understand. Assume that the ground state is a in-particle state. So the system, this is a good approximation that you are perturbing the system when it is in the ground state. Now, the electron has come out leaving this n-1 particle system. When you are detecting this electron kinetic energy, this n-1 particle system is an excited state. Okay, so it's not necessary that it will be in the lowest energy configuration of this excited state. So if you have a Hamiltonian that actually expresses all the interaction terms of this n-1 particle term system, then you can think of like the energy of this electron that comes out of this material will depend on what is the energy it has of this n-1 particle system it has left behind. I can write down a typical final state Hamiltonian in a transition metal oxides. Don't worry about these big equations. So, I mean, simply you see that this is the energy of, so it is a transition metal oxide. So for example, nickel oxide. So you have a cluster like this. So this is the nickel P electron energy. This is the oxygen P electron energy. This is the pore hole that has been created. This one is the hopping interaction term. Means if the electron wants to hop from this P to D level, so what is the energy? This one is the hopping term between P to P of oxygens. And this one is Coulomb repulsion term. So we are considering only on-site Coulomb repulsion. It means that if you have 2 electrons at nickel, their Coulomb repulsion is counted. If you have electron here and here, this repulsion energy will be much smaller compared to this on-site term, so we neglect it. And then this one is a Coulomb interaction term of the core hole that you have created by photoemission with the conduction electron. So this kind of a term. And then this one is spin-orbit coupling. Okay. So now what we are saying is that you have an initial state which is psi I. Now you have this final state Hamiltonian. If you just diagonalize it, you get all kinds of eigenstates and corresponding eigenenergies. Okay. So now you can think of that when the electron leaves this n-1 particle system behind, it can be in any of the eigenstate of this Hamiltonian. Schematically, we can represent it like this. So you have an particle system. This is the ground state. This is the n-1 particle system. Now, if it is the lowest energy state of that Hamiltonian, assume that the energy of the electron is here. Now, if the n-1 particle system is left at this eigenenergy state, the energy of the electron that comes out will be lower because the total sum of this energy is equal to the photon energy that you used. The energy of this plus this is same. So that means the electron kinetic energy becomes lower. If it leaves the system behind even at higher energy or excited state, this electron energy becomes even lower and so on. So like whichever state it has left
sir,
behind.
I'm sorry to interrupt. You have 3 minutes more.
Yes, okay.
I'm extremely sorry for that, Professor.
Yeah, I understand. Yeah. So now you can actually use this equation of energy conservation, and you can see that we always find out the binding energy. So H nu equal to binding energy plus kinetic energy plus phi. So I can find out the binding energy corresponding to a photoexcitation. You know H nu, you know phi. So the kinetic energy that you detect gives you the binding energy. So what I'm trying to say, you have knocked out an electron from one energy level, and it gives you 3 peaks depending on the schematic picture. Okay, so this is one thing. The second thing is that the peak which comes at higher binding energy for this excitation actually corresponds to an excited state of n-1 particle system. It's not highly bound. So normally, if the binding energy is higher, we say that it is actually more stable state or more bound state. But here in photo emission, you also have signature of states which comes at higher binding energy because of this final state effect where it corresponds to the excited state. So this is a very important thing which needs to be kept in mind when you do photo emission, because XPS is used by chemists, biologists, physicists everywhere to study this. But this one is extremely important to remember. Okay, I'll give you an example here. For example, nickel oxide. So nickel in different dimensions, you can see that you have knocked out an electron from nickel 2p, but you have so many peaks. So this is for nickel 2p3/2, this is nickel 2p half. And each spin orbit split peak give you multiple peaks and the relative intensities are different. This can be resolved, using that kind of Hamiltonian. The one which is at the lowest binding energy called the well screened peak, and the one at higher binding energy is called the satellites. So well screened because in this case, the core hole is screened by one electron, okay, from the neighboring sites. So that's the final state. And this one is the unscreened peaks. Okay, I'm not going into the details. The other interesting thing which I want to mention here is that this Q plates, for example, this gives you additional kind of degrees of freedom. Look at copper 2p3/2 peak. So this is the main peak and this is the satellite peak, okay, for the same copper 2p3/2 hole. And you see the main peak also has different features. So this actually happens. Why? Because if you knocked out, for example, if you have copper here, if you knocked out an electron from copper 2p, so this is positively charged. So electron can hop from oxygen to copper to screen this positive charge. Now, if you hop this electron here, this electron can actually, so you create a hole here, okay? This hole can actually create a singlet with another copper hole, and that's called Jang-Rice singlet. So if that is the case, then this hole becomes more stabilized and gives you another feature. So this kind of things happen. So depending on the character of the hole that you have created, because of this electron dynamics, you can get different kinds of peaks. This has been observed in many systems like manganites, for example. So you have a well-screened peak and also, this is a Q plate again, this Jang-Rice singlet is found. And manganites also you can find that the conduction electron that can screen in addition to this charge transfer kind of screening. So depending on the kind of screening you have, you can have multiple peaks. Okay. So this is the kind of things that we wanted to utilize to understand this spectrum. Now you know that semiconductors, there you don't have a mobile electrons to screen the core hole. Okay. So usually you get only one peak, which is the main peak often for silicon and germanium. But if you have excitons can actually move. So then what happens if you have excitons? You know that this is the valence band, this is the conduction band, and the exciton levels are actually formed like this. And if you have, these are all known textbook items, like two kinds of excitons, Frankel exciton, one-air excitons, and so on. I'm not going into the detail. So there can be core exciton when you have core excitons of excitation of the core holes. Charge transfer exciton is like one-air excitons where these two are in the near neighbors and so on. So these are all kinds of excitons which are there. What we are saying here, it's a completely new kind of scenario. Let's look at this structure here, the local cluster. So this is for germanium surrounded by 4 atoms. Now, this also has the exciton that we have seen in photoluminescence. Now, if you have the electron of the exciton is localized at the germanium site, this can also screen the core hole, okay? And the hole is somewhere else. Now, you can see that depending, so now we know that the band gap of silicon is of this order, germanium is this band gap. So the exciton energies are different when you have silicon and germanium. Now, if you have, say, silicon around germanium, because of this silicon germanium alloy, so the exciton energy will significantly change. Now, if you have a confinement effect, so that enhances the band gap. So the exciton energy will again increase. So that means that if you have done the photoemission at different levels, the corresponding exciton binding energies will be also very, very different. Okay. So that's the thing which is happening. So here, so you have a germanium core hole created, and depending on the surroundings that you have, the corresponding exciton energy will be different. And since these electron holes, they are bound, So it gives extra stabilization of the electron hole pair that actually is screening the pore hole, giving you additional peaks. Okay, so that's basically the thing which is happening. Typical Hamiltonian can be written down. This you won't find in the textbook because we have written down ourselves. So this is a new kind of concept that we are talking about, pore hole screening by excitons. And we have actually found out that the energy that you can calculate using this kind of interaction parameters. So here you have a pore hole, you have a hole in the valence band, you have an electron in the conduction band, their energies, and if you have an excitonic formation, then this reduces the energy, and then you have an interaction of electron with the pore hole, and these are the hopping terms. So these are the simplest model one can think of, and you can calculate the energy difference because of this exciton-induced screening, and we see that the kind of numbers that is required to calculate this kind of pore holes are in line with the kind of numbers we are familiar with this kind of interaction. Okay? So this seems that the model works well. So this is the last but one slide. I think so. What I'm trying to say is that this is a completely new concept of pore hole screening by exciton, which could be found in this kind of material. So now you have this germanium 3D core level spectrum, and you have the different features that comes out. So this peak corresponds to a germanium here core hole, which is surrounded by germanium primarily. Okay, so the exciton energy is not so strong, so that gives you this kind of peak. Now, if you increase the number of silicon around germanium in the silicon germanium alloys, so which corresponds to this B and C, which comes actually in the mid region of the inverted quantum Hertz, that gives you these two peaks, and you have this peak where you have actually germanium surrounded by all the silicons, which has the highest excitonic energy. This is our prediction from this kind of things. And when you have germanium surround, where whichever germanium you have, where the exciton is not really close to this core hole where you have created, then you have this unscreened peak that is coming. Okay, so this gives us two interesting conclusions. One is that, of course, so this is the conclusion that I want to say, that I mean, the one finding is that we are actually find new features in a photoemission spectrum XPS, where pore hole screening actually is happening or driven by excitons. This has not been observed earlier. And the second thing is that this kind of scenario can be utilized to probe the local character of the excitons. Why we call it local? Because you can see in this picture that depending on which part of the quantum hall you are doing experiment, you see a new feature. If the excitons are not really local, then you would have seen all the signatures wherever you do the experiment. Okay? So this tells you the local character of this excitons. And so essentially this can be used to probe the local character of the excitons in semiconductors. And in this silicon germanium inverted quantum Hertz, finding out local characters seems to say that probably this could be a good candidate for getting a type 1 semiconductor, which is extremely useful for optoelectronic kind of applications. I like to thank all the collaborators, particularly Professor Sanyan, because this actually, as I mentioned, that the project actually nucleated when we both were attending a project evaluation meeting in Delhi. I think it's a CSR meeting and so on, and we were having a evening walk, and slowly it has come to a very nice conclusion. Most of the work is done by Orko. So he is a joint student, did PhD with Professor Sannal primarily, most of the work, and I'm also his PhD supervisor for this work. And the experiment, photoemission experiment has been done by these four additional people in my group, Swapnil, Khadija, and Deep. They are all graduate students, and Sangeeta Thakur, which I think common to with this my group and the previous talk, Professor Koch. And so she was here when the experiments were done. And thank you very much for your kind attention. Yeah.
Thank you, Professor Maiti. I'm extremely happy for this kind of a presentation. It's one of the best presentation, I would rather say, in photo emission. I have a small request, Professor, to you.
Yeah.
In the photo emission, you are very well aware. You are a great expert on XPS. I know very well. For the benefit of the PhD research scholars and also the other students, can you just tell a few words about the OJ electron, which is one of the event taking place in the photo emission?
Yes. OJ electron, essentially, I mean, you can do it. OJ electron spectroscopy is very popular. I mean, you can do it using X-ray source or electron source, like when you buy a lead, low energy electron diffraction. So there also there is a OJ peak. So what you do is that you use photon or electron to create a core hole. Okay. So that is the initial excitation. Now what happens is that this core hole can be destroyed by recombination of an electron from the higher energy level. So when this electron from higher energy level jumps to this core hole, this energy can be utilized to knock out another electron from the, of course, the higher energy levels. So this second electron is called the OJ electron. So when you have this distraction of this core hole by an electron from the higher energy level, it can emit a photon or it can emit an electron. So if it is photon, of course, that's a different process, photoluminescence and so on, you can call it. But if instead of emitting a photon, if an electron comes out, then it's called OJ electron spectroscopy. Is used to identify, of course, elements in various materials, those who are doing chemistry or biology or even physics also. So OJ processes are used because these OJ signals are very unique, element specific. So it can be used to find out which elements are there in a material. But you can also do a lot of interesting physics. For example, say in a copper oxide, for example. So you knock out a copper 2p core hole. Now by a X-ray source or by a high energy electron. Now this core hole can be destroyed by an electron from the valence band. And so that energy that for the transition of an electron from valence band to the core hole can be used to knock out another electron from the valence band. So you are basically creating two holes in the valence band. Okay? So when you have two holes in the valence band, so their energy of this knocked out OJ electron can depend on, for example, single particle picture. Also, it can include the hole-hole interactions. Okay, so if you have a electron-electron Coulomb repulsion, that can be probed by looking at this OJ spectrum. So basically, you are destroying one hole, which is a core hole, creating two holes in the higher energy levels. Now, these two holes can be in the same energy level or it can be at a different energy level. Depending on that, you have the terminologies. But one of the most,
Professor, we call it as a doubly ionized material. Also.
Absolutely. This is a double ionization. So, but the ionization happens to destroy the core hole. That's it. Now, if you have these two holes in the same level, like valence band, you can have a additional kind of interesting things because of the Coulomb repulsion induced effects and so on.
Excellent. Thank you, Professor. I hope there are no questions from the audience. So I sincerely thank the two lectures which was just concluded right now. One is from Professor Ulganku and Professor Kulabran Maiti. And the two lectures were really distinguished lectures for the fact that one talks about ultra-fast detection of demagnetization process of magnetic spins. Another one is the core photo emission spectroscopy of materials, and he has discussed the in-depth science, I would rather say physics behind this photo emission. In fact, he has discussed about how the electron hole interaction, how can splitting takes place, and how, when I talk about the splitting, whether it's a satellite spot or the principal peak, how in the XPS, how can you understand the each different peak? This is very important for, especially for a PhD research scholars, because such lectures, we don't get it normally in any kind of a teaching courses or even in many lectures. I wholeheartedly thank you, Professor, for a wonderful lecture. And the session closed now. I request all the participants to join for the parallel session. Thank you, one and all.
On behalf of ICON 2021, I thank this person, Professor C. Gopalakrishnan, sir. Thank you, sir.
Thank you.
Thank you.
Okay, thanks a lot. Yeah.
Thank you.